Hello, again, my name is Gregory Plett, and I'm pleased to welcome you to this course on Introduction to Battery Management Systems. This course is the first in a specialization that investigates aspects of proper management and control of battery systems, especially for large, high-energy, high-power batteries that comprise many individual cells. To be able to manage a battery pack, we require algorithms or computer methods that continuously monitor the operation of the battery cells and provide information regarding the state and the health of the battery cells to the application that is being powered by the battery pack. And the overarching purpose of the specialization is to learn how to design and to implement these algorithms. This would normally be done using a special purpose computer known as a battery management system, or BMS. A BMS is an embedded system. That is, it is not a general purpose computer, but instead it comprises purpose-built electronics plus custom designed software for the battery management task. The photograph on this slide shows a battery management system that some colleagues at a partner university and we together designed and built for monitoring and controlling a battery system built from commercial plug-in hybrid electric vehicle battery cells. While it's not visible in the photo, the battery cells used by the vehicle are bolted directly onto the circuit boards and are mounted underneath these circuit boards. And the circuit boards that you do see in the photo comprise the electronics of the battery management system. The software or algorithms that we will study in this specialization are implemented on processors located on these electronics circuit boards. In this first course of the specialization, we do not yet look at the algorithms for a battery management system. Instead, we look at the battery management system itself. The primary functions of a battery management system are, first, to protect the human who is operating the battery-powered device, and that is our primary and ultimate concern. Under no circumstances should a human being ever be in danger from the battery pack. The BMS must be able to detect unsafe operating conditions and to respond to them in a way that warns the user and, if possible, eliminates the hazardous condition. A secondary concern for a battery management system is to protect the battery pack itself. We must ensure that the battery is maintained in a healthy operational window under all normal operating conditions. And we must also have fallback safety mechanisms in place in case of abuse of the battery system by the host application or other abnormal operating conditions leading to failure. Our algorithms must continuously monitor the state of health of the battery pack to be able to give guidance to the host application regarding the availability of energy and power such that the battery pack is never overstressed. That is, we desire to extend the life of the battery pack as much as possible, but we also at the same time desire to obtain as high a level of performance as possible from the battery pack. So we do not wish to be overly conservative in our guidance or overly free either. We want to optimize a trade-off between performance and life. Part of this task often requires that we maintain the state of the battery within some prescribed performance window. That is, we may not be permitted to allow the state of charge to ever exceed some level, or on the other hand, we may not be permitted ever to let the state of charge go below some level. So when computing power limits to inform the host application of the availability of power and energy in the battery pack, we must keep this kind of operational window in mind. As already mentioned, an important function of a battery management system is to provide information to the host controller regarding how best to use the battery pack. And this includes providing these energy limits and power limits estimates, but it often can also include telling a host controller what's the best way to charge the battery system right now, and in a vehicle how much range might be available, and many other possible things like that. Very simple battery-powered applications often do not require a sophisticated battery management system. For example, something like a flashlight simply uses its battery until all of the energy is expended, at which time you remove the battery and put in a new battery and throw the old battery into the recycle bin. Or if you were using a rechargeable battery like a nickel-cadmium battery, you would take that out of the flashlight and place it in the charger and charge it and then replace it into the flashlight. There's no need for a complicated battery management system to tell you when to do this. You simply recharge the battery when it's no longer fulfilling its requirement to provide energy to light the bulb in the flashlight. However, all lithium-ion battery packs need at least a minimal battery management system, even in a simple application like a flashlight. And the reason is that lithium-ion battery cells are extremely efficient. While some other battery technologies such as lead acid or nickel metal hydride can withstand some level of overcharging and still remain safe, lithium-ion battery cells cannot be safely overcharged. If a lithium-ion battery cell is overcharged, then at some point it will catch fire and explode. But even for lithium-ion battery systems, we don't necessarily require a complicated battery management system. In some cases, we might be able to get away with a very simple battery management system that merely ensures that the battery cell never has voltage exceeding some maximum level or that's below some minimum level. And this can be done with relatively inexpensive purpose-built electronics that integrated circuit manufacturers have designed for that exact purpose. So we might want to use a very simple battery management system for a low complexity, low cost application. Implementing a sophisticated battery management system requires a significant amount of processing, which means we need a fairly capable microcontroller to implement the algorithms. So there is a cost associated with sophisticated battery management algorithms. At the same time, it's important to understand that simple algorithms and inexpensive solutions will not usually be very good solutions. So there's an important range of applications for which we would like to implement more sophisticated battery management algorithms for better results. And how do we make that choice? And here's a simple rule of thumb or a principle from years of experience that might be helpful to you. I propose that your entire battery system, including the battery management system, is considered cheap enough, inexpensive enough, if when it comes time to replace it, you can no longer remember the last time that you replaced it. The idea is this: I cannot remember the last time I replaced the batteries in my television remote control. So I guess that means that the batteries for my television remote control were inexpensive enough for that application. If the batteries had been very expensive, you know I would have remembered for a very long time exactly when I replaced them most recently. So if you have a large battery, like for a grid storage application or for an electric vehicle, that battery will probably cost thousands of dollars or thousands of euro. And you know that if you had to replace this battery, you would remember for a very, very, very long time when you replaced it, how much you paid for it, and all of the details if you ever had to do so. So if your electric vehicle's battery pack failed, you probably would never buy that same model of vehicle again. So battery packs and battery management systems for electric vehicles should last the entire life of the vehicle. Battery packs and battery management systems for other large-scale applications should last a decade or more without servicing. In order to maximize the life of a large battery pack, it's not possible to use simple algorithms and simple ad hoc methods. We really must use the best methods that we know about, and we must use the best battery cells that we know about, and the entire solution must be as good as we can make it. So large battery packs represent a large investment, and so they motivate the best battery management electronics and the best battery management algorithms that we can afford. So this specialization will focus on teaching algorithms for managing large battery packs. Even so, the methods that you will learn also work for small battery packs. And it's simply a business decision, an economic decision regarding when you use the robust but somewhat more complicated methods instead of using a less expensive but less accurate and simpler method. There are many applications of large lithium-ion battery packs. My research team at the University of Colorado, Colorado Springs has focused for over 15 years primarily on automotive applications. We have looked at some other applications also, but our main focus has been on automotive. So that means that many of the examples that I will share with you in this specialization come from our experience in this automotive domain. If the application that you have in mind is different from this, then you can still gain from this experience, but there will be some distinctions almost certainly in some of the smaller details in how you implement the algorithms. Now, automotive applications for large lithium-ion batteries are a really growing market right now. When I started research in this field in 2001, there were no vehicles having lithium-ion battery packs. And in fact, there were only 2 hybrid vehicles in the United States, and both of these use nickel metal hydride battery systems. Both of those vehicles were hybrid electric vehicles. So they had both a gasoline engine and an electric motor that is powered through the battery pack. The gasoline engine provides the average power demand required by the vehicle, and the electric motor and associated battery system handles the difference between the average and some peak power demand, and also when the vehicle is coasting or braking, it can accept some power from the drivetrain to do some on-demand recharging of the battery as well. The reason that this is helpful is because the gasoline engine operates most efficiently only in a small range of speed and torque. And if we can maintain the engine within that small range of speed and torque, then we can get good fuel economy. The battery and the motor provide the excess power or absorb the excess power so that when the motor and the engine are combined, the power provided is able to meet the load demand required by the driver. The battery and motor operate efficiently over a much wider range of speed and torque than does a gasoline engine. So the overall efficiency of a hybrid electric vehicle can be much higher than an equivalent standard gasoline-powered vehicle. The battery pack for a hybrid electric vehicle can be relatively small. And the reason for this is that the battery pack is not required to provide an enormous amount of energy. It provides very little energy, usually in the hybrid electric vehicle, and the vehicle is not able to drive any distance at all on the battery pack power alone. The battery pack for the hybrid vehicle simply provides the differences between the average and the peak power. So the photograph I show you on the slide is the well-known Toyota Prius hybrid electric vehicle, which started out with nickel metal hydride battery cells, but I believe that in some versions they also are coming with lithium-ion battery cells at this point. Another hybridized vehicle is known as a plug-in hybrid electric vehicle. These vehicles have larger battery packs than a standard hybrid electric vehicle, and consequently they do have some all-electric range. That is, you can turn the gasoline engine off and drive simply with the motor that is powered by the battery system. Plug-in hybrid electric vehicles can get much better fuel economy than hybrid electric vehicles simply because they don't use gasoline as often. And plug-in hybrid electric vehicles usually operate in electric-only mode only at low speeds, and at high speeds we must turn on the gasoline engine in order to meet the demand. The plug-in hybrid electric vehicle on this photo is the Ford C-Max Energy, which has approximately 20 miles range, or about 32 kilometer range, in all electric mode without the gasoline engine running at all. There are a range of sizes for plug-in hybrid electric vehicles. Some have a range of about 10 miles or 16 kilometers. Others have a range of more than 50 miles or 80 kilometers. The larger range versions sometimes operate in electric mode even at high speeds and are sometimes known as extended range electric vehicles. That is, we consider them to be electric vehicles almost all the time because they have full power capability and a fairly decent range capability, but the gasoline engine can turn on in order to extend the range of your electric vehicle just like it does in a hybrid. For most people, an extended range electric vehicle makes a lot of practical sense as their primary vehicle. If your daily commute is less than 50 miles or 80 kilometers, then you can plug your vehicle into the wall outlet at home and never require going to the gasoline station at all. On the rare occasions where you must drive more than 50 miles or 80 kilometers, there's still no problem because there's still the gasoline engine and it will turn on and drive you as far as you want to go. From a battery perspective, extended range electric vehicles are very similar to plug-in hybrid electric vehicles, except they have larger battery packs to be able to store more energy for this longer range, and also to be able to deliver more power so that we can operate in electric-only mode even under full load. And the extended range electric vehicle in the picture to the right is the Chevrolet Volt, which has an all-electric range of about 53 miles. Or a little over 80 kilometers. So you can see that we're progressing from hybrid electric vehicle to plug-in hybrid electric vehicle to extended range electric vehicle, and in every step of the progression the gasoline engine is used less and the electric power from the battery is used more. So the ultimate conclusion is a pure battery electric vehicle where we remove the gasoline engine entirely and leave a vehicle that's powered only by its battery and electric motor. And so people call this an electric vehicle or sometimes a battery electric vehicle. These vehicles have the largest battery packs because they must rely exclusively on the battery energy for range and for power. The electric vehicle in the picture on the right is the Tesla Model S, which in many of its configurations has over a 300-mile range. And remember I said in 2001 there were only 2 hybrid electric vehicle models in the United States, and neither were lithium-ion? Well, the founder of Bloomberg New Energy Finance, Michael Liebrich, has said by 2020 there will be over 120 different models of electric vehicle across the spectrum. This isn't just hybrid electric vehicles or plug-ins. This is pure electric vehicles. These are vehicles that have already been announced by the manufacturers. He continues by saying these are great cars. They will make internal combustion look old-fashioned. So this market is seeing incredible growth, and there's a demand for engineers who can build battery management systems and who can write battery management system algorithms. All of these vehicle applications we've looked at use battery packs that are large in some sense. Clearly they are larger than the battery in your mobile phone. These applications also use batteries that are high voltage. For example, a laptop battery might be on the order of 15 volts. A cell phone battery might be on the order of 4 volts, but a vehicle battery is usually between 250 volts and maybe even 600 volts or higher. Vehicle applications also require high electrical current, often over 1,000 amperes under peak load. And this is very different from a portable electronics application where much less current is required. So even though there are some distinctions in design between the battery systems required for a hybrid electric vehicle versus a battery electric vehicle, the commonalities are more significant than the differences. So we're going to look at the distinctions in design only when we need to do so. But more often we will look at fairly generic battery pack design with fairly generic algorithm requirements that it can apply to any type of battery application. And so when I talk about a vehicle application where we don't really need to make distinctions between what kind of battery-enabled vehicle we're talking about, I will simply refer to the whole class of electrified vehicles as XEV, where X could be H for hybrid or PH for plug-in hybrid or ER for extended range and so forth. Of course, there are other large-scale applications. For example, there are emerging applications where the utility grid uses large batteries for different purposes. One is for storage. We can store excess generating capacity in a battery system for later use when the grid load exceeds generating capacity. Now, batteries may not really be the best choice for grid-scale energy storage. Something like pumped hydro might be a better large-scale solution. But there are still cases where grid storage does make sense, such as for remote locations where microgeneration is done. Another example large-scale utility application is for grid backup. Suppose some maintenance must be done on a local power distribution station. Normally, your entire neighborhood would be without power while the maintenance is being performed. But if a large mobile battery pack, perhaps on the trailer of a semi-truck, were to be connected to your neighborhood while the neighborhood is disconnected from the power station, then your neighborhood could receive power while the maintenance is being done, and you would never even know that there was a power outage at all. Another grid application is known as frequency regulation, which deals with relatively small amounts of excess generation capacity or excess load and buffers the grid against large power swings over a relatively short time scale of the order of minutes rather than of hours or days, as the grid is often scheduled. So all of these grid type applications are being investigated by utility companies, even though not very many have been implemented at full scale at this point. But it appears to be quite clear that there will be some future application of lithium-ion battery systems on the utility grid. This course is the first in the specialization on algorithms for battery management systems, and the primary purpose of this course is to give you an overview of what a battery management system is, what its requirements are, and how we might address designs to accomplish these requirements. The icon for this course shows a battery cell connected to some monitoring electronics to give you a visual image of this interconnection of a battery pack with a battery management system. This icon will be displayed in the upper right-hand corner of every handout slide for this course. Of course, the videos have my face in that location instead. And so the icon will be there to remind you of which course in the specialization this handout has to do with, and so forth. While I'm talking about slide format, notice a few other things. Every handout has the lesson number on the top left. So you can see that this is lesson 1.1.1. The first one is the course number, the second one is the week or module number, and the third one is the lesson number within that week. So you can keep a very organized table of contents of your materials if you wish. And then if you look at the bottom right of the slide, you see the course name and the module name, or the week topic name, along with the page number. And I use this format consistently throughout the specialization, and hopefully that will help you to stay organized with these materials. The specific topics that you will learn about in this course include 1 week of what I call a battery boot camp. In other words, a quick training exercise in battery terminology and battery composition. We also spend a week looking at lithium-ion cells and how they're different from standard electrochemical cells, and you will learn about how these cells are made and how they work. Then we'll spend 2 weeks looking at the primary high-level requirements and functionality of a battery management system, and this includes an overview of the algorithm requirements that you will learn about in much more depth in later courses in the specialization. And as a reminder, the specialization prerequisite requirements were introduced in the lesson 1.0, and a prerequisite quiz is provided for you this week for you to be able to judge your level of preparedness for undertaking this course and the specialization overall. Even though this first course in the specialization is an overview course designed to lay a foundation of knowledge that we will build on in the remaining courses, you are still going to learn some valuable skills. After completing this course, you will be fluent in battery terminology, and to demonstrate this, you will be able to list specific terms to a list of definitions. You will be able to identify the major components of a lithium-ion cell and state their purpose and understand the charge and discharge processes at quite a functional level. You will be able to list the major requirements that must be satisfied by a battery management system and know how these can be accomplished. You will come to understand how a battery management system measures current and temperature and voltage and isolation, and how it controls the contactors. You will be able to identify components that can provide protection and specify a minimum set of protections that are needed. And while we don't focus on algorithms yet in this course in the specialization, you will learn how to compute total energy stored in a battery pack and a simple method to approximate available power. And finally, if you choose to take the honors path in this course, you will be able to list the manufacturing steps of different types of lithium-ion cells and state some common aging and degradation modes and failure modes of these cells. In this course, we will study the topics covered in chapters 1 of both of the optional textbooks, Battery Management Systems Volume 1 on battery modeling and Volume 2 on equivalent circuit methods. Both of these books are available from Our Tech House and from many online booksellers. I again remind you that these textbooks are optional. It is not required that you purchase them, but if you choose to do so, I believe that they can furnish you with a more permanent, in-depth resource that you can confer with later on in your career for further study. So that brings us to the end of this lesson. That's the introduction to the course. And again, welcome. I hope that you find the material in this course really interesting and very valuable. In the next lecture topic, we will start to develop a common language of battery terminology that we will continue to use throughout the remainder of the specialization. That is, welcome to the boot camp. This week, our primary focus turns to studying topics regarding how electrochemical cells, otherwise known as battery cells, operate. And this is fundamental preparation for knowing how to use them optimally in an application. In this lesson, our objective is very quickly to introduce a lot of background terminology that will be absolutely critical throughout the rest of the specialization. It may seem like all we're doing is making a list of definitions, and in fact that's a big part of it, but doing so is necessary for us to come to a common language to be able to describe carefully and specifically everything that we study regarding battery cells and battery packs. In later lessons this week, you're going to learn qualitatively how battery cells function, and later we'll look at applications of these battery cells and so forth. So all of that is coming, but at this point we're not going to focus on that just yet. Even later in the specialization, in follow-on courses to this one, we're going to go into much more depth quantitatively, and to do so we will develop mathematical sets of equations known as models for even greater understanding of how battery cells work. We start at the very beginning with a definition of a cell. A cell is the smallest electrochemical unit. A cell delivers a voltage that can be used to power a load, and that voltage depends on the chemistry used to build this cell. Some cells are designed to be used only one time and then recycled. Others are designed to be rechargeable. The single-use cells are referred to as primary cells, and rechargeable cells are referred to as secondary cells. If we're being technical and careful and precise with our terminology, then it is important to note that a cell is different from a battery. Technically, a battery comprises more than one cell somehow connected together. Oftentimes, in common use, though, people use the term cell and battery interchangeably. I will try to be careful in this specialization to refer to the individual unit as a cell, or sometimes as a battery cell. And when I'm referring instead to connected cells, I will refer to that as a battery or a battery pack. If we connect individual cells together, we build what is known as a battery or a battery pack. It doesn't matter whether the cells are wired together in series or in parallel. A battery pack comprises cells wired either in series or parallel, or even in some combination of series and parallel. Batteries are sometimes packaged in a single physical unit. For example, the standard automotive 12-volt lead-acid battery is built from 6 2-volt lead-acid cells wired in series inside of a single package. Sometimes high-capacity lithium-ion cells are in fact batteries because internal to the packaging, multiple smaller cells happen to be wired together in parallel. So it's not always possible simply to look at the package and know whether it is a cell or whether it is a battery. In a high-capacity battery pack, such as the ones that we focus on in this specialization, there will often be dozens or even hundreds of individual battery cells that are wired together, and that wiring is usually then external to the cells. And large bus bars or thick wires connect the cells together in order to be able to carry the high electrical currents needed by the application. When we draw an electrical circuit that includes either a cell or a battery, we use schematic symbols to represent the cells and the batteries in the circuit diagram. The image that's on the right of the slide shows these schematic symbols for both a cell and for a battery. Notice that the symbol for a battery looks kind of like two cell symbols connected together, but this specific symbol for a battery is used without change, regardless of how many cells are actually connected together. The voltage of a battery depends on the combination of active chemicals or active materials that are used inside of the cells. As you will learn in the specialization, the voltage of a battery cell changes depending on whether it's fully charged or whether it's completely discharged or at some point in between. However, we need some kind of a voltage label to put on the cell when we market it and sell it, so we have some kind of an idea of what the voltage range is of this cell that we're working with. So we define something called a nominal voltage, which is a typical voltage or maybe an average voltage of a battery cell, and it's somewhere between the fully charged voltage of a cell and a fully discharged voltage of a cell. For many single-use or primary battery cells, this voltage is around 1.2 volts. For example, standard alkaline battery cells or dry cells have voltage of 1.2 volts. Even some rechargeable or secondary cells have a similar voltage. For secondary battery cells that have nickel-based chemistries like nickel-cadmium or nickel-metal hydride, the voltage is often around 1.2 to 1.5 volts. Most lithium-based cells have a nominal voltage of over 3 volts. And this is true whether it's a single-use primary lithium-based cell or whether it's a rechargeable secondary lithium-based cell. The photograph on the right side of the slide shows an example lithium-ion cell from a mobile phone. If we zoom in on this image, we can see that the nominal voltage of this cell is printed directly on the packaging, and in fact this is quite commonly done, especially with cells for consumer electronics applications. And if you look carefully, you can see that this particular cell has a nominal voltage of 3.7 volts. And as I've already mentioned, the nominal voltage is a kind of an average voltage or a typical voltage. The voltage of the cell at any point in time will be different from this nominal voltage. It could be higher or it could be lower depending on how the battery cell has been used over the past. Another important term to understand when talking about battery cells is the capacity of the battery cell, sometimes called the total capacity or total charge capacity. And either way of thinking about it, there are slight distinctions between what is meant by those terms, but the capacity is trying to specify a quantity of charge that the cell is rated to hold. Now, if you want to be precise and technical, the metric unit for charge is coulombs, but coulombs are very awkward units to work with when analyzing circuits, and they're also very small units of charge, and even a small battery cell would usually hold many thousands of coulombs of charge. So instead of coulombs, which is the same thing as ampere times seconds, capacity is specified often in terms of amperes times hours or milliamperes times hours instead. And we call that ampere hours and milliampere hours, or sometimes we are a little bit imprecise and we call it amp hours and milliamp hours. If a battery cell has a capacity of 1 ampere hour, then a fully charged cell can deliver 1 ampere of current for the period of 1 hour before it is fully discharged. Again, on this example picture of a battery cell, we see that its capacity is listed as 1,900 milliampere hours. Another way of saying it is 1.9 ampere hours. And note that the quantity that is printed on the package is once again a nominal quantity. At the beginning of life, most battery cells will actually have slightly higher capacity than what is printed on the package, and over life, for various reasons that you will learn about, the capacity will decrease. And for secondary battery cells, we usually consider them to have reached the end of life when their capacity is only 70% of the original capacity. That is, when the cell has lost 30% of its capacity. Electrical current is measured in amperes, or if we're being a little less precise, we might say amps. But the impact of 1 ampere of current to a small battery cell is quite different from the impact of 1 ampere of current to a large battery cell. So it's nice to have a relative measure of electrical current that is somehow scaled to the size of a battery cell. And this relative measure is known as the C rate. The C rate of a battery cell is the level of constant current charge or discharge that the cell can sustain for 1 hour of time. For example, a cell having a capacity of 20 ampere hours should be able to deliver 20 amperes of current for 1 hour, or 2 amperes of current for 10 hours. This relationship, as you'll find out especially in the second course in the specialization, is not a completely linear relationship. It's not quite that simple, but it's a pretty close relationship. It's a good approximation. So when we say that the cell should be able to deliver 20 amperes of current for 1 hour, we are saying that the C rate of a 20 ampere hour cell is 20 amperes. It's what we call the 1C rate. In this example, 2 amperes is what we would call the C divided by 10 rate, because it is 1/10 of the 1C rate. To compute the C rate of a battery cell from its nominal capacity, you simply write out the capacity together with its units, which might be 20 AH, where the A is for ampere and the H is for hour, and then you take your eraser and you erase the H, and we are left with 20A, or 20 amperes. So ampere hours becomes amperes, and milliampere hours becomes milliamperes. If we start with a fully charged battery cell and we discharge the cell at a 10C rate, the cell will be completely discharged in about 6 minutes. In the photograph to the right, you can see the same battery cell that I showed you on the previous slide. Remember, we said that the nominal capacity of this cell is 1.9 ampere hours. So therefore the 1C rate of the cell is 1.9 amperes. Or if you want to put it a different way, the nominal capacity is 1,900 milliampere hours, and so the 1C rate is 1,900 milliamperes. We use battery cells because they store energy that we can later release in controlled ways to do work. There are multiple ways to store energy, of course, and a battery cell stores this energy in an electrochemical form. Before the end of this course, you will learn how to compute the energy stored in a battery cell quite precisely, but for now it's sufficient to know that the total energy storage capacity of a cell is approximately its nominal voltage multiplied by its nominal capacity. The units for energy are then either watt-hours or possibly milliwatt-hours if we're talking about a small battery cell. It could even be kilowatt-hours if we're talking about a large battery pack. In the cell that I have been using in an example, you can compute the nominal energy storage capacity by multiplying its nominal voltage of 3.7 volts by its nominal capacity of 1.9 ampere hours and find that its energy capacity is 7.03 watt-hours. Energy and power are different things. Power is the rate at which we release energy from a battery cell. It's the rate at which the energy is used. Power is measured then either in milliwatts or in watts, or even sometimes in kilowatts. When battery cells are connected in series, the voltage of the battery pack is the sum of the individual cell voltages. However, the battery capacity is equal to the individual cell capacity. The reason for this is if the cells are connected in series, the same electrical current must pass through one cell as passes through all of the other cells. So all of the cells are charged and discharged at the same rate. For example, consider the battery that I've drawn to the right of this slide, constructed from 3 cells, where each cell has a nominal voltage of 3 volts and each has a nominal capacity of 20 ampere hours. The nominal voltage of this battery will be 9 volts because we are summing together 3 plus 3 plus 3, 3 volts from each of 3 cells. The nominal capacity of the battery pack will be 20 ampere hours because each one of the cells has a capacity of 20 ampere hours. So notice that if all of the cells start fully charged and we pass 20 amperes of current through this battery pack for 1 hour, that same current passes through all 3 cells, and so all 3 cells will be discharged after 1 hour. We can also compute the nominal energy capacity of this battery. The energy is simply the sum of the energy stored in each one of the cells. So we compute the energy as 3 volts multiplied by 20 amp hours multiplied by 3 cells to give us the final answer of 180 watt hours. When battery cells are connected in parallel to make a battery pack, the battery voltage is now equal to the voltage of the individual cells. However, the battery capacity is now the sum of the individual cell capacities, and this is because the battery current is the sum of all the cell currents. Or to think about it another way, the battery current is divided among all of the cells, and so each cell sees only a fraction of the total current. And so if I were to take a battery cell having a 20 amp hour capacity and put it in a battery pack with multiple cells in parallel, and I put 20 amps through the battery pack, less than 20 amps would go through that one cell, and so it would not be discharged in 1 hour. So for example, consider the battery pack that I've drawn on this slide. And this battery is constructed from 5 cells connected in parallel. Each cell has a nominal voltage of 3 volts and a nominal capacity of 20 ampere hours, just like on the previous slide. Kirchhoff's voltage law says that electronic components, including battery cells that are connected in parallel, must share the same voltage. Therefore, this battery pack will have a nominal voltage of 3 volts, which is the voltage of any one of the cells. The nominal capacity of this battery pack will be the sum of the capacities of the individual cells. Maybe you can see it more easily now that I've drawn this diagram. The total battery current is the sum of the currents passing through each one of the cells. So for every ampere hour of current that flows through the battery pack, only 1/5 of that current flows through each one of the cells. Since the capacity of each cell in this diagram is 20 ampere hours, then the capacity of the battery pack must be 5 times that, or 100 ampere hours. Put another way, if the battery starts fully charged and 100 amperes of current flows, then 20 amperes of current flows through each one of the cells, and this can be sustained for 1 hour before the battery pack is discharged. The nominal energy capacity of the battery pack is equal to 5 cells multiplied by 3 volts per cell multiplied by 20 ampere hours, which results in a total energy of 300 watt hours. So to summarize what you've learned in this lesson, a cell is the smallest electrochemical storage unit. Primary cells are not rechargeable and secondary cells are rechargeable. Cells have a nominal or a typical voltage and have a nominal or typical charge storage capacity. The C rate is a way of normalizing electrical current according to a cell's nominal capacity. Cells store energy that can later be released to do work, and the rate at which this energy is released is called power. We make batteries by connecting cells in series and/or in parallel. And finally, we can compute battery nominal voltage and nominal capacity and nominal energy ratings by knowing how the individual cells are connected. And that brings us to the end of this first lesson, and in the next lesson you will learn about how an electrochemical cell works internally. You will learn about its internal components as a first step to understanding how the cell functions, and that will give you a better understanding of what is happening inside of a circuit that contains a battery cell. In this lesson, you will learn what are the primary functional components of an electrochemical cell and what are their functional purposes. I will make a distinction in this specialization between what I'm going to call an electrochemical battery cell and what I will call a lithium-ion battery cell. Both of these are considered battery cells, but they work on somewhat different principles. And this week we're going to study electrochemical cells and how they work. Next week we will turn our attention instead to looking at how lithium-ion cells work a little differently. The focus of the specialization, of course, is on algorithms for managing lithium-ion cells, so we need to learn how they work. And fortunately, lithium-ion cells operate on many of the same basic principles as for electrochemical cells. So what you're going to learn about this week is still really foundationally important for understanding how lithium-ion battery cells work also. In particular, lithium-ion cells have all of the component parts that you're going to learn about in this lecture topic. And again, next week our focus will shift to understanding lithium-ion battery cells in more detail. On this slide I have included a drawing that you will see many times in the specialization that depicts a cross-sectional view of the internals to a battery cell. To the left of the drawing, the negative electrode is shown as a collection of green shapes, and to the right of the drawing, the positive electrode is shown as a collection of purple shapes. And throughout the illustration, you will see a light blue color in between these shapes that illustrates the electrolyte. In between the negative electrode and the positive electrode is something called a separator. And finally, on the edges of both sides of the illustration, you can see thin rectangles, on one side orange and on the other side gray, that depict the current collectors. The colors that I have used in this illustration are for illustrative purposes only. If you were to open up a battery cell, which by the way is not recommended because often they contain chemicals that can be toxic, but if you were to open up a battery cell, you would see that the compounds are usually black or gray. They're usually quite colorless. So I use these colors on the diagram simply for illustration, but I will use the same color scheme throughout the specialization. So whenever you see an electrode that's colored green, that will be a negative electrode. Whenever you see an electrode that's colored purple, that will be a positive electrode. Whenever you see a current collector that's colored orange, that will be a negative electrode current collector. And finally, whenever you see a current collector that's colored gray, that will be a positive electrode current collector. Over the next several slides, I'm going to go into more detail regarding what each of these components is and what its function is. But before we move on, I should mention that the diagram on this slide corresponds most directly to what you would see if you were to open up a lithium-ion battery cell. Some electrochemical cells have similar physical structure, but some of them also have quite different structure. But even so, regardless of the internal structure, all battery cells of whatever variety are going to have a negative electrode and a positive electrode and separators and so forth. Battery cells operate by moving charge between their negative and positive electrodes. So you can think of the electrodes as being charge storage reservoirs. In a regular electrochemical cell, the negative electrode is often constructed from a metal or an alloy of metals or even hydrogen itself. In a lead-acid battery cell, for example, the negative electrode is some kind of a lead metal or lead paste. And by the way, I think this is the first time I've shown you the acronym PBA for lead acid. The PB is the chemical symbol for lead from the periodic table, and A simply stands for acid. During a battery cell's discharge process, the negative electrode gives up electrons to the external circuit. It provides electrons to the external circuit. Technically, we say that the negative electrode is oxidized in this process. Oxidization is a process where a compound gives up electrons. So electrons are lost from the electrode, and if you want to remember what happens to electrons during oxidization, it's helpful to remember the acronym OIL. OIL stands for oxidization is loss of electrons. During a battery cell's charge process, exactly the opposite thing happens. The negative electrode accepts electrons from the external circuit. In fact, these electrons are forced into the negative electrode by applying a higher external voltage to the battery terminals than the battery itself wants to deliver. And that places an external electrical pressure on the battery cell that forces the electrons into the negative electrode. We say that the negative electrode is reduced as the battery cell is charged. Again, if you want a helpful acronym to remember this, think of the acronym RIG. RIG stands for reduction is gain of electrons. So together we have two acronyms, OIL, RIG, and I find that quite humorous myself because we're talking about a subject in this specialization that's supposed to be very environmentally friendly and green, but we remember how everything works by thinking of oil rig, which most people would say is not a very environmentally friendly subject at all. During discharge of the battery cell, when the negative electrode is giving up electrons, the negative electrode is also technically known as the anode of the battery. The anode is the electrode where chemical reaction produces extra electrons. However, during charge, the negative electrode consumes electrons, so during charge, the negative electrode is technically the cathode. And so it's very confusing to change your terminology, referring to as fixed, specific physical part of the battery cell, and to say that it's the anode during discharge and it's the cathode during charge. So most people still refer to the negative electrode as the anode even during charge. But I would like to be as precise as possible to avoid as much confusion as possible, I hope, in this specialization. So I tend to avoid terms like anode and cathode. Once in a while you may hear me slip up and the terms may come into my speech, but I try to instead use the terms negative electrode and positive electrode, even though it's a little longer to say, a little bit more cumbersome. But you should be aware when you look at the literature that when people talk about anode, they are most often talking about negative electrode, and when they talk about cathode, they are most often talking about the positive electrode. And this will help you connect what I teach in the specialization and what you learn here to what you read in the literature as well. So now let's turn our attention to looking at the positive electrode of an electrochemical cell. In a standard electrochemical cell, the positive electrode is often some kind of a metallic oxide or a sulfide or even in some cases oxygen. In a lead-acid battery cell, the positive electrode is made from lead oxide. During the discharge process, the positive electrode accepts the electrons from the external circuit, and since it's gaining electrons, we say that the positive electrode is reduced. Remember, reduction is gain. During the charge process, on the other hand, the positive electrode is forced to give up electrons to the external circuit, and so the positive electrode is oxidized. Remember, oxidization is loss of electrons. During discharge of the battery cell, the positive electrode is called the cathode because it's the electrode being reduced. The cathode, remember, is the electrode where reduction is happening. So technically, during charge, the positive electrode is really the anode because it's being reduced at that time. Again, this is confusing to refer to the same physical electrode as the cathode one time and the anode another time. So most people refer to the positive electrode as the cathode even during charge. Again, I bring this up mostly so you will have a level of comfort when you read the literature and you see the term cathode in some article, and you will understand that the authors are almost certainly referring to the positive electrode of the battery cell. And again, to be as precise as possible and hopefully to avoid confusion, I will refer to this part of the battery cell as the positive electrode and not usually as the cathode. I've talked a little about how electrons are sourced in one of the electrodes and consumed by the other electrode during charge and discharge, and how electrons flow in the circuit external to the cell from one electrode to the other, but we have not talked yet about what happens internal to the cell while this is happening. In fact, locally, we need to have a charge balance. So if we're giving up electrons, then we would tend to have a local net positive charge that somehow must be balanced by a net negative charge internal to this cell in the neighborhood of that location. And this is done by charged particles known as ions that are moving around inside of the battery cell. An ion with a net positive charge is called a cation, and during discharge of the battery cell, cations move through the electrolyte from the region of the negative electrode towards the region of the positive electrode. Similarly, negatively charged ions are called anions, and during the discharge process, anions move through the electrolyte from the region of the positive electrode towards the region of the negative electrode. Now, I believe it can be hard at first to remember what is a cation and what is an anion, so you will need to come up with some kind of a memory helping mechanism. And this is the one that I use in case that's helpful to use. I think of cats as being positive animals, and a cation is a positive ion. So cats and cations are positive in my mind, and anions therefore must be negative. Now, I suppose if you prefer dogs to cats, then my mechanism doesn't work for you, and you need to come up with something that will help you instead. Particles with a positive charge or a negative charge cannot simply jump from one electrode to the other. They need some kind of medium through which they can move. And this medium in a battery cell is called the electrolyte. It allows the positive ions and the negative ions to exist in a charged state inside of itself and to allow them to move back and forth through this cell. In a lead-acid battery cell, the electrolyte is sulfuric acid diluted by water. And in general, the electrolyte is some kind of solvent that contains dissolved chemicals that have balanced positive and negative charges. When the solvent that's used in the battery cell is water, then we say that the battery cell has an aqueous electrolyte. In the case of lithium-ion battery cells, we will find that it is inappropriate to use aqueous electrolytes because they just won't work, and instead we find that organic solvents are used. The chemicals that are dissolved in the solvent must dissociate into positive and negative ions. So sometimes acids are used, which tend to give off hydrogen ions with a net positive charge. Sometimes bases are used, which tend to give off hydroxide ions with a net negative charge. Or sometimes salts are used, which comprise elements or compounds with that easily dissociate into parts that have a net positive charge and a net negative charge. Another feature of the electrolyte is that while it must be a conductor of ions, what we call an ionic conductor, it also must be an electronic insulator to avoid self-discharge. That is, we don't want electrons moving from one side of the cell to the other side through the electrolyte, because then they would not go through the external circuit. So the electrolyte conducts ions from one side of the cell to the other internal to this cell, and the electrons are forced to go through a path external to this cell where they do work. The electrons do not pass through the electrolyte. Now, placed between the two electrodes is something known as the separator. The separator has the very simple function of mechanically and electrically isolating the negative and positive electrodes from each other. If the negative electrode were to come into contact with a positive electrode, then there would be an immediate short circuit where electrons from one electrode would flow into the other electrode and very quickly discharge the battery cell. Now, this separator is really a low-tech device in the sense that it is simply providing this electrical and mechanical isolation of the two sides of the battery cell. It's often made from some kind of a porous glass mat or a fibrous mat or a polyethylene or a polymer with micro pores. it really only keeps the two electrodes separated from each other, but it still has pores or openings inside of it that are large enough to let the electrolyte through, and therefore so ions can flow from one side of the cell to the other with very little ionic impedance. On this slide, I also mention the function of the current collectors. If the electrode is made of some kind of metal, then we can attach the external terminal of the battery cell directly to the electrode. But often electrodes are made from some kind of a powder, and we cannot attach the external terminals of the battery directly to a powder. There's just no mechanical way to do it. So instead we attach the external terminals of the battery cell to metallic foils that are called current collectors. And the electrode powders are somehow adhered to the current collectors to allow the electrons to flow from the electrode to the current collector to the outside circuit, and then on the other side of the cell from the outside circuit to the current collector and to that electrode. In this illustration, you see that the current collector of the negative electrode is drawn as orange, and the current collector for the positive electrode is drawn as gray. And this is a convention that I will use in my illustrations, and the coloring is primarily for illustrative purposes. But it does turn out that lithium-ion battery cells have negative electrode current collectors that are almost always made from a copper foil, and copper is orange, and lithium-ion battery cells very often have positive electrode current collectors that are made from aluminum, and aluminum is kind of a silver or gray color. So even though the colors on this diagram are for illustrative purposes, they do have meaning when we apply them to lithium-ion batteries. On this slide, I present a table showing components that are used for electrodes and electrolyte in some very commonly encountered electrochemical cells. Using the lead-acid battery cell on the top row as an example, we can see that the negative electrode is made from lead, which has the chemical symbol Pb. The positive electrode is made from lead oxide, which has the chemical formula PbO2. The electrolyte is sulfuric acid, which has the chemical formula H2SO4. And finally, the nominal voltage of a lead-acid battery cell is approximately 2.1 volts. Now, as you probably know, the voltage of a battery under load is less than the voltage of a fully charged battery cell that is simply resting open circuit. So the voltage depends on many factors, including temperature, and in the case of a lead-acid battery, it also depends on the concentration of the sulfuric acid used in the electrolyte. So you will sometimes see slightly different nominal voltages listed for a lead-acid battery cell in the literature, varying from around 2.0 volts to 2.1 volts. So this value is simply a reminder of a typical or average voltage, and remember that the nominal voltage is not the exact voltage of the cell, but a representative value of what you might see when you're using that battery cell. And it's also a reminder to us that the 12-volt battery that's used in an automobile, for example, is really 6 of these 2-volt lead-acid cells wired in series internal to a package. Looking at the table, you can also see something that is commonly known as a dry cell. It has a zinc negative electrode, a manganese oxide positive electrode, and a zinc chloride electrolyte. And the nominal voltage for the cell is 1.6 volts. In a lot of applications, we can replace a dry cell with an alkaline cell, and it will still work because the nominal voltages are very similar. An alkaline cell has a zinc negative electrode and a manganese oxide positive electrode, just like a dry cell, but the electrolyte is potassium hydroxide instead of zinc chloride. This electrolyte has less ionic resistance, and so it allows higher electrical current. So we often use alkaline battery cells for high power applications, whereas dry cells might be used for low power applications. Usually dry cells or alkaline cells are not considered rechargeable. It is possible to recharge alkaline cells a few times, but this is not usually recommended, and cells must be specifically constructed to allow for this by reinforcing them so that the electrolyte does not leak out of the cell while it is being charged. One type of rechargeable battery cell that's often used as a replacement for dry cells and alkaline cells is the NiCad, or the nickel-cadmium cell. These cells have a negative electrode made from cadmium and a positive electrode made from a nickel hydroxide. Nickel-zinc batteries are similar but have a negative electrode made from zinc. You can see that they have slightly different voltage characteristics, but many applications are flexible enough to allow using any of these cells. The final table entry is very interesting. It's a zinc-air battery. In a zinc-air battery, the negative electrode is made from zinc, and the positive electrode is oxygen, which is typically scavenged or harvested from air. This can reduce the weight of the battery because we don't have to consider the positive electrode as part of the weight. It does turn out that we require some structure to act as a current collector for connecting, if you will, to the air. But the zinc-air battery can have quite high energy storage for a particular volume or for a particular weight, and they make very interesting rechargeable batteries because of that. So summarizing, in this lesson you've learned that the major functional components of an electrochemical battery cell consist of the negative and positive electrodes, the electrolyte, the separator, and the current collectors. The negative electrode sources electrons when discharging, and it sinks electrons when charging. The positive electrode does just the opposite. It sinks electrons on discharge and sources electrons on charge. The electrolyte provides a medium for ion transport internal to the cell in order to maintain charge balance inside of this cell. The separator prevents an internal short circuit by physically isolating the positive and negative electrodes from each other mechanically and also electrically. However, it still has micropores in it that allow for a path for ions to flow through it. Finally, the current collectors conduct electronic current from the electrodes to the cell terminals. That is, they allow electrons to flow from the electrodes to and from the external cell terminals. When we were discussing the components of a battery cell, I most often use lead-acid cells as an example. A lead-acid cell has a lead negative electrode and a lead oxide positive electrode. It uses sulfuric acid dissolved in water as the electrolyte and often has something like a glass mat used for the separator. But we also looked at a table of all the components used in some popular electrochemical cell chemistries, and you can use that table as a reference. That brings us to the end of this lesson, but moving forward from here, our next topic is going to look at how an electrochemical cell stores and releases energy. In the previous lesson, you learned about the components that make up an electrochemical battery cell. You saw in a fairly abstract way how electrons move when the cell is charged and when it's discharged, but I didn't really explain why electrons move, and in this lecture topic I hope to talk a little bit more about that in detail. To understand how electrochemical cells store and release energy, we need to discuss the idea of potential energy. The picture of a skateboarder on this slide illustrates this idea of potential energy using a concept that we are all much more familiar with. We're all more familiar with gravitational potential energy and maybe not so familiar with electrochemical potential energy, but it really turns out that they're the same idea but just from different branches of physics. So if we think about this skateboarder on this skateboard ramp that's shaped a little bit like a parabola, we know that if the skateboarder is either at the top on one side or of the other side of the ramp, gravity wants to pull him downward. So if the skateboarder is stationary at either one of these two top positions, he has some potential energy that could be released to make him move. And we know that if the skateboarder is in the center position at the bottom of this ramp, that gravity is still trying to pull him downward, but there's no way on the ramp for him to go in a downward direction, so he will not be able to move. We can understand electrochemical cells in a similar way. Electrochemical potential energy can be stored in a battery cell just like gravitational potential energy is stored by the skateboarder at the top of the ramp. When we charge a battery cell, we're bringing it up to a higher state of potential energy. And when we discharge a battery cell, we're bringing it to a lower state of potential energy. And when the cell is fully discharged, it is at the lowest state of potential energy that it can be at, and it cannot be discharged any further, which is like the skateboarder at the bottom of the ramp. I bring back this cross-section illustration of a battery cell from a previous lesson to illustrate the discharge process. A charged battery cell holds electrochemical potential energy, and this potential energy at the negative electrode favors a chemical process that releases electrons into the external circuit and releases positively charged cations into the electrolyte. This is just the same idea as the skateboarder on the top of the ramp. Gravitational potential energy favors a process whereby the skateboarder would move down the ramp. So if the skateboarder may be stuck at the top of the ramp because of friction, and that friction is removed, then we know the skateboarder will start accelerating down the ramp toward the bottom. So in the same way, this electrochemical potential energy in the negative electrode is stuck inside the battery cell until an electronic circuit exterior to the battery cell is completed. You see, there's an electrical friction or a resistance that prohibits electron movement until the circuit is completed. But once the external circuit is completed, it's possible to release this electrochemical potential energy from the negative electrode by producing these electrons that go into the negative terminal of the battery and into the circuit, and also by producing positively charged cations that go into the electrolyte. In a similar way, the positive electrode stores up electrochemical potential energy, but in this case the potential energy favors a different chemical process whereby it accepts electrons from the external circuit and accepts positively charged cations from the electrolyte in order to reduce its potential energy. And again, it's only when the circuit external to the battery is completed that the resistance that prohibits this energy from being turned into useful electrical energy is removed. And it's the combination of the potential energy stored in the negative electrode and the positive electrode together with this external circuit that makes this entire discharge process possible. Now, while the circuit exterior to the cell is not complete, there's still an electrical pressure that has built up because of this electrochemical potential energy that wants to be released to do work. And this electrical pressure is called electrical potential. There's a potential energy stored in the cell that causes the electrical potential difference between one electrode and the other. And this potential difference is actually something that can be measured with a voltmeter, and it's called the cell voltage. When the external circuit is completed and electrons are free to flow from the negative electrode through the circuit to the positive electrode, then work can be done in the external circuit. And what happens is that this electrochemical potential energy is converted into electrical energy. Again, if you think back to the example of the skateboarder, in that case, gravitational potential energy was converted into kinetic energy as the skateboarder started moving. Work was done on the skateboarder by bringing the skateboarder from zero velocity up to some positive velocity as he went down the ramp. So while the process that occurs in a battery cell is an electrochemical process, and the process that occurs with the skateboarder is a mechanical process, a lot of the same ideas apply, and I believe it can be helpful to have this skateboarder image in your mind when you're thinking about how a battery cell works. So what about rechargeable cells? Remember that we've talked about two different categories of battery cells, primary cells and secondary cells. Primary cells are not rechargeable. The electrochemical reaction that occurs during discharge of a primary cell is not reversible. During discharge, the chemical compounds are changed permanently, and so the electrochemical potential energy is released until the original compounds are completely exhausted. And even if I try to recharge a primary battery, the compounds that have been formed during discharge will not recombine into the original compounds that were present before the discharge, and therefore it will not recharge the battery cell. And this is the principal reason that primary cells can be used only one time. Secondary or rechargeable battery cells, on the other hand, are special in the sense that their chemical reaction has been designed or chosen in such a way that it is completely reversible. The original chemical compounds that changed when we discharge the battery cells can actually be reconstituted in their original form by the application of an external potential between the electrodes that injects energy into the cell. Ideally, these secondary battery cells can be discharged and recharged an infinite number of times, but we know from our own personal experience that this is not the case. So we ask, why? What is happening? And it turns out that the simple understanding we have at this point of how a battery cell discharges and recharges is true for the primary chemical reaction that's happening in the cell, but it neglects the fact that there are other chemical processes happening and mechanical processes happening inside the battery cell that cause degradation or aging of the cell. So that is, inside the battery cell there are multiple chemical processes happening where only one of them, hopefully the dominant one, is the electrochemical reaction that we want to happen that's releasing energy into the load circuit. The other unintended chemical reactions can be parasitic in nature and cause materials in the battery to degrade. And there could be also mechanical processes causing stresses and strains that cause the materials in the battery to degrade. So the life of a secondary battery cell is not primarily determined by its main chemical reaction. Rather, the life is determined by how quickly these other degradation processes occur. I bring back the same diagram of the cross-section of the battery cell to illustrate the charge process for a secondary cell. As you might imagine, it's exactly the opposite of the discharge process. During charge, the cations move from the positive to the negative electrodes through the electrolyte, and the electrons move from the positive to the negative electrode through the external circuit. This action happens in response to an externally applied voltage that is greater than the rest voltage at the terminals of a battery cell. Because this external voltage is higher than the cell voltage, that means that there's a greater potential energy exterior to the cell than there is interior to the cell, and so energy is pumped back into the cell, and it's that energy that transforms the active chemicals back to their original state. And it's a lot like the skateboarder. If he's at the bottom of the ramp, but you apply a force, you can push him back up the ramp. So if you apply energy to the skateboarder, you can, again, reconstitute him in a recharged state at the top of the ramp where he can go back down again at a later point in time. When we're charging the battery, we often have to be much more careful than when we are discharging the battery cell. Manufacturers publish safe operating voltage limits for their battery cells. If we overcharge a battery cell, we can be forcing energy into the cell that the cell is no longer able to accept in a safe way. And by doing that, we can cause irreversible damage to the cell and in some cases even fires or explosions. Also, the ability of a battery cell to sustain a high level of health when it is overcharged depends a lot on the chemistry of the battery cell. For example, lead-acid battery cells can be slowly overcharged with no permanent damage. What happens when we slowly overcharge a lead-acid battery cell is that water in the electrolyte dissociates into hydrogen and oxygen gases. And if that's done slowly enough, the hydrogen and oxygen gases will actually recombine back into water. And so there's this kind of a process happening at the top level of state of charge that if the battery cell is sealed and these gases do not escape, can actually happen quite safely, and it doesn't cause degradation of the battery cell. This process at the top of charge is called a float charge, and many lead-acid battery chargers are designed to have a float charge to maintain the battery at a top state of charge. This is not something you can do with a lithium-ion battery cell. If you overcharge a lithium-ion battery cell, it does not result in a chemical process happening that is reversible. Often the electrolyte will decompose just as with the lead-acid cell, but in this case it does not recombine. And when the electrolyte in a lithium-ion battery cell decomposes, it turns into gases that cause the cell to puff up, just like this picture on the slide of the mobile phone battery. And once the cell has puffed up like this, it cannot be returned to its previous state. The electrolyte is permanently damaged. The ionic resistance of the electrolyte is increased because there's less functional electrolyte present. The gases that are produced are often flammable and can cause fires and explosions. And so you must be really careful when charging a lithium-ion battery cell to ensure that you do so safely. And there are also voltage limits for how much we are permitted to discharge a battery cell, but the risks associated with over-discharge are much often less serious than the risks associated with overcharge. And so they are not safety risks as much as they are lifetime risks. For example, if you do not maintain a lead-acid battery cell at a high state of charge, what happens is that hard lead sulfate crystals will begin to form on the electrodes, and these crystals cannot be converted by a standard battery charger back into lead and sulfuric acid. In some cases, it is possible to recover these lead sulfate crystals using a specialized battery charger that uses voltage pulses to try to break up these crystals, but this is a specialized topic and it's not even guaranteed to work in general. So most lead-acid battery cells are used in applications that must maintain a high state of charge. For example, the automobile lead-acid battery really should never be discharged below about 80% state of charge. Otherwise, it will start to age quite rapidly because of the formation of these crystals. For some applications, there are specialized lead-acid battery cells called deep cycle battery cells that can be used over a wider range of state of charge, and usually this is accomplished simply by using thicker lead plates that just take longer to age before the battery cell is considered dead. I would like to take a couple of minutes to illustrate briefly how a battery cell is charged in a very common scenario. So on this page I have 4 different diagrams corresponding to different ways of looking at the same experiment, and that is charging a battery cell. In this case, the example is for a lithium-ion battery cell, which is being charged from a mid-level 50% state of charge up to a fully charged state, 100% state of charge. In the top left plot, I show you terminal voltage of the battery cell versus time as it's charged. On the top right, I show you state of charge versus time. On the bottom left, I show you electrical current versus time, and on the bottom right, I show you charging power versus time. In the convention that I'm using to describe electrical current and power, negative values correspond to charging and positive values correspond to discharging. And in this experiment, I'm showing 2 different charging modes. One is called constant current, constant voltage, and the other is called constant power, constant voltage. In constant current, constant voltage charging, you regulate the charging current at a constant value until the cell's measured terminal voltage reaches some maximum manufacturer specified value. And at that point in time, you switch from a constant current operational mode to a mode where you simply hold the voltage of the cell constant at that maximum value, and you wait until current decays to a very, very small absolute level. Constant power, constant voltage charging is similar, except during the first phase, we don't apply a constant electrical current to the cell, but instead we apply a constant charging power to the cell until a charging voltage limit is reached. And then in the second phase, again, you simply hold that voltage constant until the charging power decreases to a small number in magnitude. So looking at the bottom left picture, the solid blue line shows current versus time for the constant current, constant voltage charge scheme. You can see that current is being held constant at a 9 ampere level until the maximum voltage of 4.15 volts is attained. Then, when we hold the voltage at that level, the magnitude of current decreases towards 0 until the battery cell is completely charged. If instead we do a constant power, constant voltage charging, we see that the current is slowly decreasing in magnitude during the constant power portion of the charge cycle, and that's shown by the green dashed line. And this is because power equals voltage times current. If power is constant and voltage is increasing, then current must be decreasing in magnitude. So now let's look at the bottom right picture, and we can examine the power versus time. And when we look at the constant power, constant voltage charging profile, we see that the dotted green line shows a constant power level for the first portion as expected, followed by decreasing levels of absolute power while we hold the voltage constant. And you can also see that if we're performing a constant current, constant voltage charging, that in fact during the first portion the magnitude of power is increasing because a constant current multiplied by an increasing voltage gives me an increasing absolute power. In the top right picture, you can see that during constant current, constant voltage charge, the blue line, that state of charge increases linearly over the first segment, until it reaches the voltage limit, and after that the state of charge gradually tapers and approaches the 100% state of charge level. The constant power, constant voltage line has a similar behavior, except that it is not strictly linear change in state of charge in the first section, but it's pretty close. You may already know that many battery chargers can quite quickly charge a battery cell up to about 80% state of charge, and sometimes even 90% state of charge, but that it can take quite a while to charge the battery the remaining amount up to 100% state of charge. And now maybe you can see from these graphs why that might be the case. It's possible to charge a battery cell quite quickly at the beginning without violating this maximum voltage limit, but as soon as we hit that maximum voltage limit, we have to turn down the charge rate in order to protect the battery cell, and therefore to protect the user also. And so the final 10% or 20% of the charge often takes as much time, or nearly as much time, as the first 80% of the charging period. Notice that on this slide, in recent lessons, you've learned about the components of electrochemical cells and how these components interact with each other while charging and discharging a battery. In this lesson, you will learn about the actual chemicals that are used inside of the negative and the positive electrodes in order to optimize how a battery cell works. In particular, when we're designing a battery cell, we desire to have high specific energy and high energy density. Now, specific energy has to do with how much energy we can store per unit volume, and energy density has to do with how much energy we can store per unit mass. So we would like to have as high a specific energy and energy density as possible for many applications, especially portable applications, which will mean that we would like to reduce volume, reduce mass, and increase energy. We also desire high specific power and high power density. Specific power has to do with how much power I can pull out of a battery per unit volume, and power density is how much power I can get per unit mass. Power is the rate at which we use energy, and so the energy capacity of a battery cell tells me how much work I can do in total, and the power capability says how quickly we can pull that energy out to do work. We also desire that our solution be low cost and have long life and have low toxicity and have high recyclability. High energy and high power capabilities of battery cells depend on an overall maximum cell voltage and an overall maximum cell current. Remember that voltage multiplied by current equals power, and voltage multiplied by current multiplied by time equals energy. So if I can maximize a cell's voltage and maximize the current that we can extract from that cell, we're going to be able to maximize these metrics. And ultimately, how much voltage I get out of a battery cell depends on the specific materials that I use in the electrodes, and how much current I get out of the battery cell usually depends on how the cell is constructed. In order to talk about battery cell voltage, we must first understand electrode potential. The propensity of or a natural inclination of one material to gain or lose electrons in relation to another material is known as its electrode potential. Compounds that have negative values for electrode potential with respect to some reference material are used for negative electrodes. And compounds that have positive values of electrode potential with respect to some reference are used for positive electrodes. And the larger the difference between the electrode potentials in the negative and positive electrodes, the greater the voltage that will be developed by the cell, and hence the greater the amount of energy that can be stored by the cell, everything else being equal. So it would be really nice if we could somehow tune the electrode potentials arbitrarily to be anything we wanted, but we in fact cannot do that. We have to work with the materials supplied to us by nature, and these are the elements in the periodic table. So the periodic table is a very powerful visual device for thinking about all of the elements found in nature. So we're going to spend a few minutes discussing how this table is organized. One of the important aspects of the table from our point of view is that the relative reducing and oxidizing capabilities of the elements are indicated by the arrow that is drawn underneath the table. In particular, you can see that the strong reducing elements are grouped on the left-hand side and that the strong oxidizing elements are grouped on the right-hand side of the table. So I might consider building a battery cell that has a negative electrode using an element from the left of the table and some positive electrode using an element from the right side of the table. And in fact, one of the most promising future technologies is known as lithium air. At this point in time, there are still quite a few developmental difficulties to be overcome before a real practical lithium air battery is a commercial success. But a lithium air battery could have one of the greatest energy and power densities of any known combination of elements at this point. A lithium air battery uses a negative electrode that's built from solid lithium metal, and you can see lithium in the far left-hand column of the table, from the second from the top. The positive electrode in the lithium air battery is oxygen that's harvested or scavenged from air, and you can see that oxygen is near the top right of the table. In general, however, lithium air or not, whenever we build an electrochemical cell, we desire to use elements from the far left and the far right of the table whenever possible, and as we'll see shortly, as far to the top of the table as possible, because that will end up with less weight, less mass. Let's take a look at a portion of this periodic table in a little bit more detail. The diagram that I've put on the slide zooms in on the top left part of the periodic table, so it's easier to see some of the details. Every element, whether it's human-made or if it's found in nature, has its own box in the table, and each one of these boxes lists quite a lot of information about that element. In the left column of each box, you can see that there's an integer number on top, then a symbol, then a name, and then a real valued number. To the right of the box, there's a sequence of integers. And you can also see that the symbols in the boxes themselves are color-coded, and all of this has meaning, so let's spend a few minutes looking at what all of these details mean. First, the integer number that's listed on the top left of each box is known as the atomic number of the element. The atomic number is equal to the number of protons in the nucleus or the core of the atom of that particular element. Underneath the atomic number, you can see the symbol that's used for that element when it's listed in a chemical formula. In this table, the symbols are color-coded. The coloring tells you whether the element is a solid or a liquid or a gas at room temperature. If the element is a solid, the symbol will be black. If it's liquid, the symbol will be blue, and if it's a gas, the symbol will be red. Next, the full element name is listed underneath the element symbol, and underneath the element name you can find the mean atomic weight. Now, the atomic weight of an atom is equal to the weight of all of its protons plus the weight of all of its neutrons plus the weight of all of its electrons. But the weight of an electron is really tiny compared to the weight of a proton or a neutron, and so it really doesn't have much impact on the mean atomic weight. So you can think of the mean atomic weight as being the average number of protons plus neutrons found in that element in nature. And while every element of the same type has exactly the same number of protons, which makes it that element, there is some variability in the number of neutrons that is found from sample to sample. And that's why this is a mean or an average atomic weight and not an exact atomic weight. Mean atomic weight is also equal to the number of grams per mole of that element. In chemistry, a mole of a material is equal to 6.022 times 10 to the power 23 units of that material. This unit is defined in such a way that 1 mole of protons is exactly equal to 1 gram in mass. And also 1 mole of neutrons has mass exactly equal to 1 gram. And the conversion factor, which is a somewhat unusual number, but 6.022 times 10 to the 23rd power, is known as Avogadro's number. Finally, the list of numbers on the right-hand side of the box indicates the number of electrons in each electron shell of that element. Describing where electrons exist in relation to the nucleus of an atom is actually quite a complicated subject, and it involves quantum mechanics. But for this course, it will be sufficient to think of the element in terms of a classic model where there are shells surrounding the nucleus, and each shell is capable of holding electrons. So each shell has a maximum number of electrons that it can hold, and this number depends on the distance of this shell away from the center of the atom. If you've studied quantum mechanics, you know that this model isn't quite right, but whether using the quantum model or the classical model, an electron shell corresponds to a possible set of electron energy levels. Continuing with our discussion of the entries of the periodic table, it turns out that the background color of each box in the table is also meaningful. It indicates whether the element is a metal or a non-metal, and if it's a non-metal, of what kind, or whether it's a metalloid. The organization of the table is important. The rows of the table are called periods. All elements that have that share the same row are in the same period and have the same number of electron shells. Therefore, we can say that the row or the period of an element is equal to the number of electron shells surrounding the nucleus of that element. The columns of the table are called groups, and all elements in any group generally have the same number of valence electrons, where valence is a special name given to the outermost shell. There are exceptions to this last rule, and the transition metals in the center of the periodic table often act a little bit strangely, and sometimes they do exactly follow this rule and sometimes they do not, which is one good reason to have these numbers listed in the top right of the box to tell you how that element actually behaves. So as we've just seen, elements within each individual group or column of the table have the same number of valence electrons, except for some special cases with transition metals. It turns out that the number of an element's valence electrons allows us to predict how that element will interact and react with other elements. So all elements that share the same particular group tend to have similar chemical properties. When the outermost electron shell is full, as is the case with all of the noble gases on the very far right column of the periodic table, then there are no free electrons available to take part in a chemical reaction. And so the noble gases are chemically non-reactive, and this condition is something we call inert. Noble gases are inert. But for some other examples, I've drawn the electron shells for three different elements. On the left, I've drawn lithium. And if you look at the periodic table, you notice that lithium has an atomic number of 3, which means that it has 3 protons in its nucleus, and the nucleus has a +3 charge. So for the lithium atom overall to be charged neutral, it must have 3 electrons. The first electron shell can hold a maximum of 2 electrons, so that there are actually 2 electron shells. And this remaining third electron is in the second shell, and that's the valence electron. In the center, I've drawn carbon. Carbon has an atomic number of 6, which means that it has 6 protons in its nucleus. So the nucleus has a net positive charge of +6, and to balance that, we need 6 electrons. So as with lithium, 2 of these electrons exist in the centermost shell, and the remaining 4 electrons fit in the second shell. And since carbon needs only 2 shells of electrons, the second shell is the valence shell, and there are 4 electrons in the valence shell. And finally, I have drawn cobalt, which has an atomic number of 27, so there are 27 protons, and to be charged neutral, there must be 27 electrons. And I've drawn the electron shell configuration here for cobalt, and you can see that in the outermost shell there are 2 electrons, so we say that cobalt has 2 valence electrons. So I chose these 3 elements not completely at random, but because they turn out to be extremely common in lithium-ion battery cells. You might imagine lithium to be an important element, given the name lithium-ion battery cell, but you might not know that carbon and cobalt are also really important. It turns out that the negative electrodes of most lithium-ion battery cells are made from some form of carbon, And it turns out that the positive electrodes of many lithium-ion battery cells contain a fair amount of cobalt. Thinking a little bit more about the valence electrons and how elements having the same number of valence electrons are listed in the same column of the table, we can talk about these groups as having similar chemical properties. So in the far left of the periodic table, we have the elements that are known as the alkaline metals. These are the group 1 elements, and they have only one valence electron. On the far right of the periodic table, we have the noble gases in group 18, and these are chemically inert, so they don't interest us very much in this course. However, in the column just before that, we find the halogens in group 17, which are lacking only one valence electron before that valence shell is completely filled. And it turns out that elements that have only one or two valence electrons are highly reactive because these electrons are very easily removed and cause the atom to become a positively charged ion. And these atoms are shown in the left two columns of the periodic table, and they're very strong reducing agents because these extra electrons are quite easily donated and becoming oxidized themselves. I use the term redox here, and this might be the first time I've used that term in this course. Redox is a term that's commonly used to describe any chemical reaction that involves the exchange of electrons. And redox is simply a shortened form of reduction oxidization. You put those together and you get redox. On the right side of the table, ignoring the noble gases, we see the elements that are lacking only one or two electrons before their valence shell is filled. And these are the strongest oxidizing agents because they have this deficit of valence shell electrons, and they strongly desire to steal or maybe accept electrons in a redox reaction, becoming reduced themselves. The energy level of an atom is determined by the configuration of electrons into shells. We talked in the last lesson about electrochemical potential energy. Well, this is how that energy is stored. It's by changing the configuration of electrons in shells. And so an atom's energy level can be changed by moving an electron from one shell to another shell, or by gaining or losing electrons from its valence shell. Most fundamentally, a battery stores this electrochemical potential energy by changing this configuration of electrons, as I said, in the electron shells in its electrode materials. So when charging a battery cell, the electrons move to higher energy configurations in both electrodes, and when discharging, the electrons move to lower energy configurations in both electrodes. The difference in electrical potential energy before and after an electrochemical reaction can be measured using a voltmeter because the voltage differences in the species before and after the chemical reactions are these changes. It's a direct measure. And electrochemists over the years have very carefully studied the difference in electrical potential energy before and after reactions for thousands and thousands of different reactions under highly regulated conditions. And these results have been recorded in tables that are called electrochemical series. And these are arranged according to the electrode half reaction standard potentials, denoted E with a superscript 0. So to clarify, battery cells undergo a full reaction that comprises two half reactions. The half reaction is what happens at one electrode. So a negative electrode has one half reaction and a positive electrode has a separate half reaction. And because it's possible to somewhat arbitrarily build your battery cell by choosing an electrode reaction for the negative electrode and a different one for the positive electrode, it's more convenient actually to list the half reaction potentials than it is to list all of the possible combinations, which would make for a much larger table. And so we can use these half cell reactions to compute what the total voltage of the cell is, as we'll see. The table to the right of the slide shows a short example of what an electrochemical series looks like. The top row shows the chemical reaction of a positively charged lithium ion plus a negatively charged electron becoming a charged neutral lithium. More specifically, the subscript AQ informs us that this lithium cation is in aqueous solution, which means that it is dissolved in water. And the subscript S informs us that the product lithium will be in solid metallic form. This half reaction is said to have an electrode standard potential of negative 3.04 volts. Now, voltage is a property that must be measured with respect to a reference. There's no such thing as an absolute voltage. So instead, there's a potential difference between two spatial locations that somehow can be measured. So in order to measure and tabulate standard potentials, we must establish some reference potential against which we measure all of the standard potentials that we're interested in finding. And in this table, the reference half reaction is shown in the fourth row. In this row, we see that two positively charged hydrogen cations plus two negatively charged electrons become hydrogen gas. And we see that this electrode reaction has a standard potential of 0 volts. And that's simply because we defined it to be this way. All other reactions are measured with this as a reference. And unfortunately, the laboratory setup and procedure for making this measurements is something that's quite interesting, but it's beyond the scope of what we really need to know in this course. So I suggest, if you're interested, that you look up a course in electrochemical methods. The numeric values in the electrochemical series are known as the standard reduction potentials of the reaction. Lithium at the top of the list has the most negative value, which indicates that it's the strongest reducing agent in this table. Fluorine, on the other hand, at the very bottom of the table is the strongest oxidizing agent because it has the largest positive value for its standard potential. So if we were to construct a battery cell where the negative electrode were lithium and the positive electrode was fluorine, we would be combining the half reaction from the top row and for the negative electrode and the half reaction from the bottom row for the positive electrode. And the cell nominal voltage then would be equal to the reduction potential of the positive electrode minus the reduction potential of the negative electrode. So in this example, the cell voltage would be 3.87 volts minus negative 3.04 volts, which gives us 5.91 volts. Now, I doubt you've ever seen a battery cell that's rated with a nominal voltage even close to 6 volts. And the reason is not because we don't know how to make electrodes for such a cell. In fact, we can just pull them out of this table. Instead, the reason is that we don't know how to make an electrolyte for that cell. There's presently no known electrolyte that will withstand this kind of a voltage without decomposing. So in summary, if we desire high specific energy and high specific power, then we desire light elements which come from near the top of the periodic table. If we desire high voltage, then we want to use strong oxidizing agents paired with a strong reducing agent so that one has an excess of valence electrons and the other has a small deficit of valence electrons, and that these match up together. Because the strengths of the oxidizing and reducing natures, this will result in a cell that has high voltage. Of course, these are not the only considerations when we're designing a battery cell. One thing that you learned in the previous slide was there needs to be an electrolyte that can support this voltage that's developed between the electrodes. We also require, of course, that the solution be low cost, which means that we need to use elements that are abundant in nature and which are easily isolated from whatever basic compounds we extract from the earth. Further, we desire that the battery cell has long life and low toxicity, and that it has high recyclability. So there are scientific aspects to cell design, as we've seen, but there are also economic and environmental aspects that need to be considered as well. And jointly optimizing all of these considerations makes for a very interesting design problem. So far this week, you've learned some fundamental principles of how battery cells are constructed and how they work, how they produce a voltage, and how we might consider designing them from elements in the periodic table. Now we start the last substantive lesson of the week, where we summarize a lot of what you've learned already by looking at 3 individual examples of electrochemical battery cells. We start with one that's very commonly found in introductory textbooks on electrochemistry, and this is called a Daniell cell. It's probably the easiest and the simplest to understand, and so it gives us a good starting point for our example. Each half cell in the Daniell cell consists of a solid metal electrode submerged into an electrolyte solution. The negative electrode is made from solid zinc, and the electrolyte in the negative electrode region is zinc sulfate, which disassociates into positively charged zinc ions plus negatively charged sulfate ions when dissolved in water. The positive electrode is made from solid copper. The electrolyte in the positive electrode region is copper sulfate, which dissociates into positively charged copper ions and negatively charged sulfate ions when dissolved in water. The figure on the right-hand side of the slide shows a schematic of a Daniell cell. It has all of the components that I've already mentioned, and it also shows the separator, which is made from some kind of a porous ceramic disc that allows the negatively charged sulfate anions to move back and forth from one side of the Daniell cell to the other. When the Daniell cell is being discharged, zinc from the zinc anode gives up 2 electrons to the external circuit, and it also gives up a positively charged zinc ion into the electrolyte. The positive electrode receives the electrons from the external circuit, and it consumes positively charged copper ions from the electrolyte in order to copper plate the surface of the copper electrode. Because a zinc cation is being produced at the negative electrode, there will be a local net positive charge in the electrolyte there at that point in time. And similarly, because copper cations are being removed from the electrolyte in the positive electrode, there will be a local net negative charge in that region. So this difference in charge at local points in the cell cause the negatively charged sulfate ions to migrate from one side of the Daniell cell to the other through the porous disc in the center of this cell. And when we're charging a Daniell cell, exactly the opposite happens. So that is, copper dissolves from the positive electrode into the electrolyte, and zinc plates onto the negative electrode, and electrons pass through the external circuit in the opposite direction as they are forced to do so by some electronic charging means. If we go to a table of electrochemical series, we can look up the half reactions that occur in each one of the electrode regions. We find that in the negative electrode we have a redox reaction of zinc 2+ combined with 2 electrons becomes zinc metal, and that this half reaction has a standard potential of negative 0.76 volts. In the positive electrode we have a redox reaction of copper 2+ combining with 2 electrons to become copper solid, and this reaction has a standard potential of 0.34 volts. So the overall reaction by combining the reactions in the 2 half cells is that zinc combined with copper becomes zinc 2+ combined with copper, as we see here. The overall reaction has standard potential computed as the standard potential of the positive electrode minus the standard potential of the negative electrode, or in other words 0.34 volts minus negative 0.76 volts, which gives the sum of 1.1 volt for the Daniell cell. We note that the standard potentials listed in the electrochemical series assume what are known as standard conditions, which has to do with a specified electrolyte concentration and specified temperatures and so forth. So in practice, you will find that the actual voltage of a particular Daniell cell will vary somewhat from the standard potential that we have listed here in practice. And in particular, the voltage will be somewhat higher when the cell is fully charged, and it will be somewhat lower when the cell is discharged. We now start to look at our second example, which is a lead-acid battery cell. Both electrodes in a lead-acid battery cell are made from some metallic lead-based plates, and the electrolyte is sulfuric acid in an aqueous solution, in other words, dissolved in water. When a lead acid cell is fully discharged, then both electrodes are lead sulfate, and the electrolyte is a dilute solution of sulfuric acid. If, however, the lead acid cell holds some charge, and we are in the process of discharging this cell, the negative electrode reaction is listed as shown. We see that solid lead combined with a sulfate anion becomes lead sulfate plus 2 electrons. We also see that the positive electrode reaction has lead oxide in solid form combining with sulfate anions plus protons from the external circuit to form lead sulfate plus water. When we combine the two half reactions, the total reaction is lead plus lead oxide plus sulfuric acid becomes lead sulfate plus water in liquid form. And the opposite reaction occurs when charging a lead acid battery cell. When fully recharged, the negative electrode is solid lead and the positive electrode is solid lead oxide, and the electrolyte is a more concentrated solution of sulfuric acid. The standard potential of the reaction that happens in the negative electrode is negative 0.356 volts, and the standard potential of the reaction that happens in the positive electrode is 1.685 volts. So when we combine these two values together, we find that a lead acid cell has standard potential of 1.685 volts minus negative 0.356 volts, which comes out to 2.041 volts. Again, the voltage of a lead acid cell will vary with the concentration of the sulfuric acid. In fact, it's possible to measure the concentration of the sulfuric acid and use that as an indicator of the state of charge of the battery cell. We also find that the voltage changes with temperature, so we sometimes see slightly different values listed as the nominal potential of a lead acid battery cell in the literature, but these values are almost always between 2.0 volts and 2.1 volts. Again, we note that vehicle lead acid batteries, also known as 12-volt batteries, are built from 6 individual lead acid cells packaged in series in a single container. And similarly, some motorcycle batteries are 6-volt batteries that comprise 3 individual lead acid cells internally wired in series. When we charge a lead acid battery, it's important to protect against overcharge. If we overcharge a lead acid battery, then water in the electrolyte will decompose into hydrogen and oxygen gases. Under some circumstances, other compounds in the electrodes can be electrolysized as well to create poisonous gases, and all of these gases can cause bulging and deformation of sealed lead acid batteries. It's also important to protect a lead acid battery against over-discharge. If we discharge a lead acid battery too far, then lead sulfate crystals will form, and these crystals often cannot be decomposed, which means that we lose some of the lead that could otherwise be cycled back and forth in our battery cell, and therefore some capacity of the battery cell is permanently lost. So if you were designing a battery management system for a lead acid battery, it's important to limit the depth of discharge. Also note that lead acid batteries have a property that's somewhat unusual. It's possible to trickle charge a lead acid battery cell. That means that when the cell is fully charged, we can hold the terminals of this cell at a fully charged voltage, which continuously forces a very small amount of current to continue to flow into the cell and through this cell. The water in the electrolyte at this full charge point decomposes into hydrogen and oxygen gases, but if the trickle charge is at a slow enough rate, these gases then can recombine back into water at the same rate. So I form gases and then I form water again at an equilibrium rate overall. And so by doing this trickle charging or float charging, the battery cell is maintained in a fully charged state while not causing any permanent damage while we're doing so. And this counteracts some natural self-discharge processes that would otherwise cause the battery cell to slowly discharge over time, leading to the problem that we just talked about of lead sulfate crystals forming. If a lead-acid battery cell does happen to over-discharge, in some cases it's possible to use pulses of current to break up the lead dioxide crystals and to restore some of the capacity. And this is a feature in many battery management systems and chargers for lead-acid battery cells. Also notice that this trickle charge that I mentioned can be used to equalize battery cells when they're connected in series at a top state of charge point. That is, if the cells have slightly different characteristics, one cell may reach a fully charged point before the other cells in the battery pack reach that point. And if I stop charging when the top cell has reached the top state of charge, then my overall battery pack is not balanced, it's not equalized, and not all cells in the battery are holding as much energy as they could. But because it's possible to trickle charge a lead-acid battery, if I continue to charge when one cell is at the top, it simply remains at the top and the other cells slowly come up and balance with that top cell. And so trickle charge is very practical, very important in a lead-acid battery cell, and you're going to find out that next week when we look at lithium-ion battery cells that we cannot do trickle charging with lithium-ion battery cells because they are too efficient and they will just keep on charging forever and ever until they catch fire and explode, and of course we have to avoid that. So the trickle charging in a lead-acid cell allows cells that are already fully charged to remain in that state, while the remaining cells in the battery continue to charge until all cells are fully charged. Now, lead-acid battery chemistry was invented more than 150 years ago, so the technology is very mature. Even so, there are some variations in how lead-acid battery cells are constructed depending on the application for which the battery will be used. For example, the lead-acid batteries are not usually built using solid lead plates like you might think at first. Instead, the electrodes are usually constructed from some kind of a grid that looks a little bit like the screen mesh you would put over a window in your house or over some doorway to keep the insects from flying in. And this grid is made from a lead alloy for strength, but it's covered with a sponge-like lead paste, which is the actual electrode material. And this is done for a very interesting region. If we simply used lead plates for the electrodes of the battery, then the surface area of the lead plate over which the charge and discharge reactions occur is simply equal to the length of the plate by the width of the plate, and maybe multiplied by 2 if we're using both sides of the plate. The interior of the plate does not participate in the reaction, it's only the surface, and so the surface area is what matters. If we use a sponge-like substance instead, then there can be enormous surface area due to all of the holes and the porous nature of the sponge, and the discharge and charge reactions can happen over the entire surface area, including all the surface inside of the sponge-like material, which means that if I'm limited in how fast a reaction happens per square meter, if I increase the number of square meters of electrode, then I increase the rate at which we can charge and discharge a lead-acid battery cell. So fundamentally, this means we can get much more power out of a battery cell that uses these sponge-like electrodes, because power is the rate at which energy can be added and removed. Some types of lead-acid battery cells are called flooded cells, and in flooded cells the separator is just a mechanical spacer and the electrolyte is liquid sulfuric acid, but flooded cells are relatively uncommon anymore. Another type of lead-acid cell is called an absorptive glass mat, or an AGM cell. In these cells, the separator is a porous material made from glass fibers that forms a mat that is saturated with a minimal amount of electrolyte. These AGM cells, because they use a very small amount of electrolyte, do not create large volumes of gases when they're overcharged, and so the cell can have a sealed construction instead of a vented construction, and it makes the cell maintenance free, which can be a huge advantage in a lot of applications. And sometimes silica is added to the electrolyte to turn the liquid electrolyte into more of a gel. And this also allows for a sealed construction, and it allows for less variation in the concentration of the sulfuric acid at different parts in this cell. You see, if I had a purely liquid electrolyte, the electrolyte tends to stratify with higher concentrations in one part and lower concentrations in another, and this causes the aging of the cell to vary depending on whether you're at the bottom of the cell or at the top of the cell. And by adding this silica, you can actually improve life by making aging more uniform. When we add the silica and create this gel, the resulting lead-acid battery is often called a gel cell because of that. So when we make this gel cell, we often have longer life, but also the trade-off is we often also have lower power because the electrolyte has a higher ionic resistance than the liquid electrolyte. Our third and final example for this lesson is nickel metal hydride battery cells, and these are really interesting. The principle of operation for a nickel metal hydride cell is quite different from what we've seen already this week. Metal hydride cells depend on the ability of some metallic alloys known as hydrides to absorb large amounts of hydrogen like a sponge absorbs water. So it absorbs this hydrogen in pores in the metallic material. Now, hydrogen can decompose into an electron and a proton, and so hydrogen can be used as the charge carrier inside of a battery cell. So if an electrode has the ability to absorb hydrogen and release hydrogen as separate protons and electrons, then it can act as a negative electrode. And you're going to learn next week that lithium-ion cells work in a very similar way to this, except that in that case both electrodes work in such a way that lithium is absorbed into the electrodes a lot like water is absorbed into a sponge, instead of performing a standard redox electrochemical reaction at the surface of the electrode. So metal hydride cells use these metal alloys and their negative electrodes, and they use a nickel hydroxide as the positive electrode. And the distinction between what's happening in the negative electrode versus what's happening in a standard traditional redox reaction is that we don't really have a standard electrochemical redox reaction happening in the negative electrode at all. We're simply taking the proton from the electrolyte and the electron from the external circuit, combining them into an uncharged hydrogen that gets absorbed in this material when we're charging the electrode, and when we're discharging, the opposite happens. So no standard chemical reaction takes place that could deform the electrode. We're not causing products to build up at the surface or to be removed at the surface. Instead, hydrogen simply goes into the electrode and comes out of the electrode. And this is why metal hydride cells often have much, much longer lives than a standard electrochemical battery cell. And as I mentioned a minute ago, lithium-ion cells work in a very similar way, which is why lithium-ion battery cells tend to have much, much longer lives than standard rechargeable cells do. Inside a metal hydride battery cell, the electrolyte is some kind of a hydrogen-absorbent aqueous solution, such as potassium hydroxide, and it really takes no part in the chemical reaction at all. It simply serves as a way to transport the hydrogen ions, the protons, between the electrodes. So the magic, if you want to think of it that way, of a nickel metal hydride battery cell is how the negative electrode works. The electrode is some kind of a rare earth hydrogen absorbing metal alloy, and there can be different structures used. For example, a structure in an AB5 format where A can be lanthanum or cerium or neodymium or praseodymium, and the B can be nickel or cobalt or manganese or aluminum. Or the structure in some cases has an AB2 form where A can be titanium or vanadium and B can be zirconium or nickel doped with chromium or cobalt or iron or manganese. These details are not at all the focus of the course, but it's interesting to think about how the electrode structure is built. The key point is that hydrogen is absorbed into this metal alloy without changing its chemical formulation in any way, and more importantly, without changing its physical structure. And the picture on the right shows an example of what I mean. The dark colored spheres indicate atoms in this metal hydride alloy, and the gray colored spheres indicate hydrogen atoms. these hydrogen atoms can fit into the vacancies, into the openings in the crystal structure of the metal alloy without changing its chemical composition and without changing the structure in any way. And it's exactly like water absorbed in a sponge. I can take a dry sponge and I can place it in water and it absorbs the water, and then I can squeeze the sponge and the water goes back out. And at least ideally the sponge itself has not changed in any way by adding or removing the water. And if I allow the sponge to dry out on the counter, it retains exactly the same form that it had to begin with. So this mechanism by which hydrogen gets inserted into the electrode, which is called intercalation, and the mechanism by which it is removed from the electrode, which is called deintercalation, is very gentle when compared with a standard redox reaction, and so nickel metal hydride cells tend to have very long lives. We'd like to, for this example, also compute the voltage of a nickel metal hydride cell like we did for the other two battery chemistries. And so once again, we need to look up the standard potentials of the half reactions that occur in each electrode. In the negative electrode, we have M, which stands for the metal hydride, plus a proton plus an electron becomes the metal combined with hydrogen. The standard potential for this reaction depends on what we use for M, but it's generally around negative 0.8 volts. The positive electrode, which is nickel hydroxide, has a half reaction of nickel hydroxide plus hydroxide becomes nickel oxide hydroxide plus water plus an electron. And this half reaction has a standard potential of 0.5 volts. Therefore, the overall reaction is nickel hydroxide plus metal becomes nickel oxide hydroxide plus a metal combined with hydrogen, having a potential of 0.5 volts minus negative 0.8 volts, or around 1.3 volts. When charging a nickel metal hydroxide battery cell, we must again be careful to guard against overvoltage. If a nickel metal hydroxide cell is overcharged, then oxygen gas evolves when the positive electrode is no longer able to provide nickel hydroxide to react with the hydroxide in the electrolyte. But if a nickel metal hydroxide cell is charged very slowly, then oxygen gas can diffuse from one electrode to the other and combine safely with hydrogen to form water. So it actually is possible to slightly overcharge a nickel metal hydroxide battery cell a little bit if it's done, again, very slowly. And we must also guard against over-discharge when hydrogen gas is evolved. So to summarize this lesson, you have seen examples of three types of electrochemical battery cells: the Daniell cell, a lead-acid cell, and a nickel metal hydroxide cell. In each case, we investigated the individual half reactions that take place in the positive and negative electrodes, and from those we're able to predict an overall cell nominal voltage. Despite the fact that these three cells have a lot of similarities, we also saw that there were some pretty significant distinctions between how they operated. The Daniell cell is unique in that it uses different electrolytes in the positive and negative electrodes. The lead-acid cell was unique in that it uses a sponge lead paste spread out over a lead alloy grid in order to increase the power that it can deliver. And the nickel metal hydroxide cell uses a hydrogen-absorbing metal hydride for its negative electrode, and this extends life. So while the battery management system algorithms that you will learn about in this specialization are quite general in nature, we are going to apply them specifically to lithium-ion battery cells, which have further distinctions from what you've learned about so far. So as we end this week and we start to turn our focus to what we will study next week, we're going to begin to look in particular at understanding how lithium-ion battery cells work in preparation to understand how to write algorithms to manage them properly. At the end of every week in this course and in this specialization, we will quickly summarize the progress that has been made during that week. My hope is that this can help give a bigger picture overview of all of the topics that you've learned so that you will be able to put them together into the overall concept of what's going on. So we will also quickly preview the topics that we plan to study in the following week of material. This week we began by introducing the primary functions of a battery management system, or a BMS. You learned when a BMS is needed, and you saw some example applications of battery packs that require a BMS. You also learned some important definitions that we will use when we're talking about cells and batteries, and how to design a battery pack from cells wired in series and or in parallel to meet some given requirements. You also learned about how a standard electrochemical battery cell operates, including how it produces a voltage and some internal details of the discharge and charge process. And you learned some overall concept related to how electrochemical battery cells are designed. You saw some considerations that have to be taken into account when we are designing a battery cell. And finally, you saw 3 examples that brought all of these details together and showed that even though there are many similarities between different types of battery cells, there's also significant distinctions between them that often require that we know something about the internal details of the cells that we wish to manage. Moving on from here, I would like to remind you that the focus of this specialization is on how to implement algorithms or computer methods for battery management for battery packs comprising lithium-ion battery cells in particular. And it turns out that lithium-ion battery cells work a little differently from the standard electrochemical cells that we have studied this week. They work a little bit more like the nickel metal hydride battery cells that you saw in the final example that we looked at. So next week, we're going to turn our attention to thinking about lithium-ion battery cells in particular and studying how they work. We will ask and answer the question, why should you be interested in lithium-ion battery cells instead of, for example, one of the chemistries that you've seen this week? What are the advantages of lithium-ion battery cells compared with other types of battery cells? We will also investigate how their operational mechanism at an internal physical level differs somewhat from those found in the standard electrochemical cells that we focused on in this particular week. You will see what materials are used to build lithium-ion battery cells, what materials we use for the current collectors and for the electrodes and the separator and the electrolyte in different varieties of lithium-ion cells. And finally, we will consider a very fun thought experiment that's also a very important thing to think about, which has to do with whether the global supply of lithium is sufficient to meet the possible future demand for lithium-ion battery cells from electric vehicles and grid storage applications and consumer electronics and things like that. So congratulations for finishing week 1 of the course, and I look forward to talking with you again in week 2. Welcome to the second week of the course. Last week we spent most of our effort studying background topics related to standard electrochemical cells and how those work in general. To sum up the week, we looked at 3 specific examples. The first 2 were the copper-zinc Daniell cell, and then the lead-acid battery cell, and finally we looked at nickel-metal hydride cells. The Daniell cell and the lead-acid cell are standard electrochemical cells, but the nickel-metal hydride battery cell worked on a slightly different principle from a redox scheme in its negative electrode. Remember that the metal hydride in the negative electrode absorbs hydrogen a lot like a sponge absorbs water. It does this without changing its structure or its chemical composition. And we discussed how this is a far more gentle process than a standard chemical reaction. And so nickel metal hydride cells tend to have much longer lifetimes than lead acid cells, for example. This week you're going to learn that in lithium-ion battery cells, both electrodes work on this principle, which is one reason that lithium-ion cells tend to have much longer lifetimes than lead-acid cells. For example, you're fortunate if the lead-acid battery cell in your automobile lasts for more than 5 years. On the other hand, it's very likely that most lithium-ion battery cells that are being used for automotive applications will last the life of the vehicle at least 10 years. Nickel metal hydride cells work really well for hybrid electric vehicle type of applications where there's not a huge need for a lot of energy storage, but where we do need to have high power. But if you remember our discussion of the periodic table last week, you might remember that nickel is quite a heavy element. It's in the 4th row of the table, and that means that the nickel metal hydride type of battery pack is going to be quite a heavy battery pack. It would be nice if we could use lighter elements. In order to discuss the relative sizes and weights of otherwise similar battery technologies, we often use the terms specific energy and energy density, which measure the maximum stored energy per unit weight or per unit volume, respectively. So, for a given weight, a higher specific energy cell stores more energy. For a given storage capacity, a higher specific energy cell is lighter. For a given volume, higher energy density cells store more energy, and for a given storage capacity, higher energy density cells are smaller. In the figure on this slide, the vertical axis is showing energy density and the horizontal axis is showing specific energy. The boxes on the plot show a rough description of the characteristics of battery cells having different chemistries. So chemistries that you see plotted on the lower left of the plot are the largest and the heaviest for a given capacity. And as we move right on the graph, that indicates lighter cells, and moving up on the graph indicates smaller cells having the same capacity. So we would like to move both right and up. And you'll see that the lead acid, which is indicated as PBA, PB for the element lead and A for acid, lead acid is the largest and the heaviest of those that are shown on this plot. Nickel cadmium, NiCd, and nickel metal hydride, NiMH, are both better. But lithium-ion battery cells are smaller and lighter than these historic chemistries, and that's the main reason that we prefer them in applications such as powering different types of electrified drivetrain vehicles where both size and weight must be minimized. Notice that the plot also shows lithium polymer. Lithium polymer is a type of lithium ion. Sometimes it's just used as a marketing term, and sometimes it's used to talk about a cell that has a solid polymer electrolyte instead of a gel electrolyte. So just think of both of them for the time being as both being lithium ion types of battery cells. You will notice that there are some other chemistries that are shown here that are even smaller and even lighter than lithium ion, such as zinc air and lithium air. In both of those two chemistries, the negative electrode is a solid metal, either zinc or lithium, and the positive electrode is oxygen that is scavenged from air. And because air is around us everywhere, the weight of the air is not really included in the weight of the battery cell, and that's one reason why they can be smaller and lighter. The ultimate battery technology, as far as I understand, is lithium air, because you're taking lithium metal as your negative electrode, and lithium is the third element in the periodic table. It's very small, very light. But at this present time, there are difficulties making it work robustly and repeatedly in real-world applications. And there's an enormous amount of scientific research going on right now to attempt to perfect lithium air technologies. Similarly, zinc air has a lot of research going on right now too, to make it very repeatedly rechargeable. And so you're likely to see a lot of news releases in the future as scientists and material scientists and engineers work on perfecting that technology. So you've now learned about one possible set of advantages of lithium-ion cells versus cells having different chemistries. That is, lithium-ion cells have higher energy density and higher specific energy than most other types of secondary cells. We now look at a few other advantages. One is that lithium-ion cells typically operate at higher voltages per cell than other rechargeable cells. A lot of lithium-ion battery cells operate at around a nominal voltage of 3.7 volts versus about 1.2 volts for nickel metal hydride or NiCad cells. What this means is that often in an application that requires maybe 3-volt power source, I can use one lithium-ion battery cell instead of several nickel metal hydride or NiCad cells in series. Further, lithium-ion battery cells have lower self-discharge rates than other types of rechargeable cells, which means if the cell is not connected to a load and it's just sitting there, the level of charge in a lithium-ion cell will slowly decrease over time due to self-discharge, but it will not decrease as quickly as it does in some other technologies where the self-discharge rate is higher, and so that is an advantage of lithium-ion. Nickel metal hydride and NiCad cells can lose anywhere from between about 1% to 5% of their charge per day, even when they're not installed in a device, and many lithium-ion cells will retain most of their charge even after months of storage. We have some in our lab that have been stored for years, and we pull them off the shelf and they are still at least 50% state of charge. Finally, lithium-ion cells have a long life, as we've talked about, because of this much gentler intercalation mechanism that they use in charging and discharging in each electrode instead of a more standard and more harsh redox reaction. But to be fair, there are also some disadvantages to using lithium-ion cells. For example, lithium-ion batteries are presently at least more expensive than similar capacity nickel metal hydride and NiCad cells. Lithium-ion cells are more complicated to manufacture and are presently manufactured in much smaller numbers than nickel metal hydride and NiCad batteries, but that is something that is changing. For laptop and consumer electronics, they are manufactured in very high volumes, and for larger scale applications like automotive, they're beginning to be manufactured in much higher volumes too, and that is bringing the price down. Lithium-ion cells tend to be less stable electrochemically, which means that if you overcharge a lithium-ion battery cell, it's possible for that cell to catch fire. Other chemistries are usually a little bit more benign if you overcharge them, and so for a lithium-ion battery pack we require special safety precautions. They will need special circuitry to protect the battery from damage due to overcharge and to over-discharge. Of course, that's something that you are learning about in this specialization. You're learning about battery management, and so this is something that you will be able to bring to any project involving designing a battery management system for lithium-ion, and that will be something great for your resume. Something also which is maybe less obvious is that when you select a lithium-ion cell for a particular application, you should be aware that there can be a great diversity in the quality of cells that you find in the market. And the quality of cell materials that are used in the construction and exactly how that cell is constructed in the factory makes an enormous difference in terms of the cell longevity and the safety and the performance. And so if you are part of a project that is looking at a large-scale application, it will be very important for you to visit the customer site, see how the cells are prepared, the manufacturer site, see how the cells are made, look at their quality controls, and investigate a lot of these particular performance indicators. So impurities in the cell can limit the performance that can be achieved, and cells from different manufacturers that on the data sheet seem to have similar chemistries and similar construction may in fact yield quite different performance over the long term. So to summarize this lecture topic, we've discussed in a general way the advantages and some disadvantages of lithium-ion battery cells compared to cells having different chemistries. When we talked about the benefits offered by lithium-ion cells, we introduced this idea of energy density, which is the amount of energy per unit volume, and specific energy, which is the amount of energy per unit mass. you learned that lithium-ion cells have higher energy density and higher specific energy than most other types of rechargeable cells. Also, because of the gentler intercalation mechanism that's used in the electrodes of these cells, than compared with, say, a violent redox reaction in an electrochemical cell, the lithium-ion cells tend to have longer life than other rechargeable cells. And finally, they also can have higher per unit voltage, higher voltage per cell, which makes the electronic designs and the battery pack designs simpler. And they also have lower self-discharge rates, which means that they can be used in applications where the battery pack must be stored for a period of time. And that will work better than for other types of rechargeable cells. There are some disadvantages. The primary disadvantages are that we need to manage them very carefully to guarantee safety. But as I mentioned, the good news is that this is what you're learning about, and this is a big part of what this specialization is all about. And when you've completed this specialization, you will be able to construct battery management system algorithms that are able to keep battery cells safe and to extend their lifetimes. A second disadvantage of lithium-ion is the cost of the battery pack as compared to the cost of an equivalent capacity pack using another chemistry. This cost includes the cost of the cells plus the supporting electronics. But it seems that lithium-ion cells and electronics are becoming less expensive, and over time we should see their price decrease significantly. And that brings us to the end of this lecture topic. In the upcoming topics this week, you're going to learn in much more detail how a lithium-ion battery cell works, starting with a closer look at the intercalation process itself, and then looking at some of the materials and how intercalation combines with those materials in this cell. And so that's what's coming next. In this lesson, you're going to learn how lithium-ion battery cells work in contrast with how standard electrochemical battery cells work. In a lithium-ion battery cell, both electrodes depend on an intercalation mechanism rather than a standard redox chemical reaction. Remember, this is also how the negative electrode in a nickel metal hydride battery cell worked. However, while a nickel metal hydride cell stores hydrogen in its negative electrode, lithium-ion cells are able to store lithium in either one and both of the electrodes. Also remember that the lithium that intercalates into the electrodes is stored in the electrodes a lot like water is stored in a sponge. It doesn't change the structure of the electrodes themselves. In the picture on the right, I have illustrated how this works. I've drawn both the negative and the positive electrodes as sets of parallel plates, and I've represented the lithium by purple spheres. This drawing shows lithium being stored in the vacancies between the plates that form the electrodes. Now, this is a somewhat simplified illustration, but you're going to see this week that when we study the actual materials that can be used to make the electrodes, that this is pretty close to what's really happening in some of the electrode materials. This is close to what's happening at the microscopic scale. So for now, you can simply think of the electrodes as being materials that somehow have spaces built into their structures, vacancies, into which lithium can intercalate and enter into and move about, and from which it can exit as well. And this is done in such a way that the electrodes don't ever participate in a standard chemical reaction that would alter their structure. The structure remains intact. So lithium atoms are stored in the electrodes, and when a lithium atom leaves an electrode, it gives up an electron, and at that point it becomes a positively charged ion in the electrolyte. And this positively charged ion can move through the electrolyte from one electrode to the other. And the electron at the same time then moves through the external circuit, and it powers the load. And also the positively charged lithium ion from the electrolyte can enter into these electrode materials when an electron is available from the external circuit to allow that to happen. And when it does that, it forms an essentially neutrally charged lithium atom inside this structure of the electrode that can move around quite freely. As I mentioned on the previous slide, this intercalation process involves inserting lithium ions into a structure of the host electrode without changing that structure. So in order to be able to do that, the electrode materials are chosen for a lithium-ion battery cell to have two key properties. First, the electrode must have this kind of a structure where there are openings and pathways into which the lithium can enter and through which the lithium can move. And secondly, there must be an ability for the material to accept compensating electrons from the external circuit or to give up electrons to that external circuit. In other words, the material must somehow be electronically conductive as well. When a lithium atom is stored inside of the electrode, it is essentially uncharged, neutrally charged. In actual fact, researchers have been able to measure the charge on the lithium atom inside the materials using very specialized laboratory equipment. They found that these lithium atoms do possess a slight positive charge, not a unit charge, but a fractional positive charge. What's happening is that the lithium has an electron associated with it in its outer valence shell, and this electron is being loosely shared with the crystal structure surrounding the location of that lithium atom. And so this electron is slightly ripped away from the atom, but it's still pretty much associated with that lithium atom. So there's a slight positive charge on the lithium and a slight negative charge in the surrounding region in the crystal structure. But for our purposes, we can think of the lithium as being neutrally charged and moving through this crystal structure quite freely. So let's think about what happens when we discharge a lithium-ion battery cell. We already know that during discharge, the negative electrode must give up an electron to the external circuit, and it must give up a positive ion into the electrolyte. And this positive ion, remember, is called a lithium cation, and this cation then can move through the electrolyte. Let's think about what's happening in the particle. When lithium leaves the particle, it leaves behind a vacancy at the surface of this negative electrode particle. This vacancy could be filled with another lithium atom. And what happens is that lithium inside that particle, at a more central part of the particle, where lithium is at a higher concentration, moves through a diffusion process from this higher concentration in the center of the particle toward the outside of the particle, so that over time we have a more equal concentration of lithium throughout the particle. And so this process replenishes the availability of lithium at the particle surface. Diffusion is illustrated in this diagram on the right. This is something you've seen many times in your life, I'm sure, whether it was a scientifically conducted experiment or just something you happen to notice. This example shows a glass of water to the left, and in the second image in the sequence, a drop of purple coloring has been added to that water. In the third and fourth images, you see a progression over time of what happens due to adding that single drop of purple coloring. The coloring starts at a very high localized concentration in one location and zero concentration at other places. But due to the random motion at the molecular level, this purple dye slowly spreads through the water until there's an equal concentration throughout the entire mixture. And this is exactly what's happening with lithium inside the electrode particles. When I add lithium to an electrode that starts out with no lithium in it, the lithium I have added makes a high concentration at some places, but there's low concentration or zero concentration elsewhere. And over time, due to the random molecular motion, the lithium I have added will diffuse until there's an equal concentration of lithium throughout this particle. Now, the same thing happens when I remove lithium, but it's more difficult to conduct an experiment like the one I've illustrated on the slide that can show that. But you can imagine that if we were to take the water solution with purple dye in it on the right side of the slide and somehow remove the dye rather from the top layer, and so we've got clear water and then this purple colored water, that over time the purple colored water would diffuse into the clear region, and you would have a new equilibrium where there was a lower concentration overall. So similarly, when I'm discharging a lithium ion electrode, when I'm removing lithium from it, lithium from higher concentrations interior to the particle will diffuse outward to replenish those low concentration areas until there's an equilibrium throughout. When lithium exits the surface of the electrode, it gives up an electron, and that electron travels through the external circuit from the negative electrode across through the circuit to the positive electrode, and it powers the load. And then at the surface of the positive electrode particles, a positively charged lithium atom from the electrolyte and an electron from the external circuit join together to make a neutrally charged lithium atom, which enters into the electrode particle. Then the lithium concentration at the surface of that positive electrode particle is higher because of added lithium there than it is in the interior to the particle, and so lithium diffuses over time throughout the positive electrode particle to equalize the concentration throughout that particle. When we charge a lithium-ion battery cell, exactly the same process happens but in the opposite direction. Ideally, this discharge and charge process is completely reversible. So a lithium-ion battery cell could be charged and recharged and discharged an infinite number of times. We know that's not true. We'll discuss why that's the case over the course of the specialization. There are side reactions and other degradation processes happening, but at least the ideal situation is that this can happen infinitely often. And lithium is able then to pass back and forth between the electrodes during charge and discharge. So during charge, lithium exits the surface of the positive electrode particle now. It becomes positively charged in the electrolyte. It gives up an electron, and this electron is forced by the charger through the external circuit across to the negative electrode. At the negative electrode, a positively charged lithium cation from the electrolyte joins with this electron, forms a neutrally charged lithium atom, which then enters the negative electrode particle at the surface. And again, there will be a higher concentration of lithium at the surface of the negative electrode particle when we do this than there is at the interior of the particle. And so lithium will diffuse inward, and that over time we will get an equilibrium concentration. And similarly in the positive electrode particle, because I've removed lithium from the surface, there will be a higher concentration on the positive electrode center than the surface, and lithium will diffuse over time to equalize that concentration a few times. Now, I've mentioned a few times in this course so far that electrodes consist of particles of material. They are not homogeneous, just blocks of materials. And here I show some scanning electron microscope, or SEM, photographs of electrode materials to give you a better visual understanding of what this really looks like. In the left photograph, you can see an SEM image of a graphite material that's used in the negative electrodes of many lithium-ion battery cells. And in the right image, you can see an SEM image of lithium manganese oxide material that's used in the positive electrode of some lithium-ion battery cells. And so you can see that the electrode really has many, many, many small particles instead of one single homogeneous block of material. The reason for this is to increase the overall surface area of the electrode as much as reasonably possible. Because as we've seen, lithium enters and exits the electrode through the surface. And this process of lithium entering and exiting the particles is actually fairly slow per unit surface area of the electrode. But if we increase the surface area, even though the process is slow per unit surface area, if we increase the surface area, the total rate of lithium entering and exiting can be quite fast. So if we want high rates of charge and discharge, if we want high power lithium-ion battery cells, we want to increase the surface area as much as possible. And this is done by making small particles. If you look at the amount of surface area per unit volume, when I make small particles, that greatly increases the surface area and therefore greatly increases the current rate capability of a cell and the power level of a cell also. So why don't we take this to extreme, just grind these particles down until they're just super, super small. The reason that you're going to learn about in the fourth specialization course is that while the ideal desired chemical reaction is rate dependent on surface area, some of the side reactions that cause a cell to fail also depend on the surface area. And so there's a trade-off. I want the cell particles to be small to get high power, but I also want them to be large so that the cells degrade more slowly. And this is an engineering trade-off that must be optimized when we design the battery cells. The image on this slide shows you a different view of an electrode. On the previous slide, the electrodes were prepared by taking an electrode from a cell and slicing it with a razor blade to make a cross-section that could be photographed. But while you might imagine that a razor blade is very, very sharp and can make a very nice sharp cut, it's not sharp enough or thin enough to cut through the particles that we're talking about in the electrodes. The image on this slide was prepared in a different way. This image was created by taking an electrode and using a focused ion beam or an FIB device to slice through the electrode. And this technology is able to actually cut through all the particles as well. So instead of pushing the particles to one side or another like a razor blade would do, we're actually slicing down the middle of the particles, and this gives you a better idea of what that really looks like in the electrode. In the image you can also maybe more clearly see the spaces between the particles, the voids, and these voids are filled with electrolyte inside an actual electrode. There are some other materials in the electrodes that we can't see in these photographs. There are binders that glue things together, glue the particles together so that the particles remain in contact with each other and don't easily separate. And that's important so that there is a pathway for the electrons to flow to the external circuit. There are also conductive additives that coat the surfaces of particles to enhance their ability to conduct electrons, because some of the materials that are used in lithium-ion battery cells do not conduct electrons very well. These extra materials, the binders and the conductive additives, are not active in the sense that they don't participate in the normal chemical reactions of the battery cell. So if you read articles about lithium-ion cells, these binders and additives are not often mentioned, even though they are always present in a practical cell. There are also often things added to the electrolyte in order to inhibit some of the side reactions which otherwise cause the cell to age and degrade. These additives in the electrolyte are not often talked about either, but they are always present in a practical cell. So in summary, in this lesson you've learned that a lithium-ion battery cell has a positive and a negative electrode, both of which are made of small particles in order to increase their surface area and therefore to increase their power capability. You've learned that these particles are made from compounds that internally have an open crystal structure that can accept lithium into them without changing that structure. You've learned that lithium can intercalate into these particles and can de-intercalate out of the particles, and this is something that happens at the surface. Inside the particles, lithium diffuses over time to equalize the concentrations of lithium. During discharge, lithium moves from the negative electrode particles to the positive electrode particles through this intermediary electrolyte where positively charged lithium cations are the charge carriers. During the charging process, the same thing happens but in the opposite direction. And you've seen that electrons move through the external circuit. When I'm discharging, they move from the negative electrode to the positive electrode, and charging, they go the other direction. Over the rest of this week, you're going to learn about materials that are used in common lithium-ion battery cells. And this will give you a better idea of how the lithium-ion battery cell works at a microscopic level. And you will then have the ability to conduct an intelligent conversation with people regarding the different types of materials that are used, and you'll understand why lithium-ion battery cells sometimes have slightly different names from each other, even though it's the same basic principle at work. So in particular, in the next lesson, you're going to learn about materials that are used in negative electrodes for lithium-ion battery cells. In the previous lesson, you learned that lithium-ion battery cells are constructed from particles having a regular crystal structure, and that these particles are able to accept positively charged lithium ions from the electrolyte plus electrons from the external circuit, and are also able to insert the resulting neutrally charged lithium atom into vacancies in their structure without changing that structure. In this lesson, you're going to learn about different materials that can be used for these particles in the negative electrode. However, before we do that, we're going to look at different overall cell form factors to give a better understanding of how a cell is built, and therefore how the electrodes are packaged inside of a cell. There are three basic form factors that are used for lithium-ion battery cells. In the photograph below, I show you several examples of cylindrical format cells. There's not much to say about why they're named that. Of course, they're packaged inside of cylinders. In the second picture, I show you several examples of what are known as prismatic format lithium-ion battery cells. Again, these cells have that name because the cell is packaged in metal rectangular prism cases. In the third picture, I show you several examples of pouch cells. These type of cells may look quite similar to you to the prismatic type of cell, but we're going to see that they're packaged quite differently internally. And while the cylindrical and prismatic cells are usually packaged in thin aluminum cases, the pouch cells are packaged in a material that looks more like a thin plastic bag. It's actually a little stronger than that, but that's what it appears like to the eye. And since this bag or pouch contains the internal components of the cell, that's why we call it a pouch cell. Even though the external form factor of different lithium-ion battery cells can be quite different, it turns out that the electrodes that make up the active parts of this cell are manufactured by very similar processes regardless of how the final cell is packaged. The particles that comprise the electrodes are coated onto both sides of metallic foils that act as current collectors. And these current collectors then conduct the electronic current into and out of the cell. The diagram illustrates this by showing in the top part a positive electrode with active materials coating both sides of an aluminum foil current collector. And in the bottom part, we see the negative electrode active materials coating both sides of a copper foil current collector. By now, I think you realize that the purple color is used in illustrations to indicate the positive electrode active materials, and the green color is used in my illustrations to indicate negative electrode active materials, and this is simply for illustrative purposes only. In the actual electrodes, the materials are usually a gray or almost black color, and they're hard to tell apart by eye. So even though the electrodes themselves for different form factors of lithium-ion batteries are made in very similar ways with similar processes, the way that they're actually assembled into the battery cell differs depending on whether we are constructing a prismatic or a cylindrical or a pouch cell. Inside of a pouch cell, the electrodes turn out to be stacked on top of each other, whereas inside of a cylindrical or a prismatic cell, they are wound in some kind of a spiral. Pouch cells are increasingly being used in battery applications because they minimize the amount of space wasted by the packaging. The image on the right illustrates the structure internal to a pouch cell. To build a pouch cell, you take a positive electrode, and then you put a layer of separator material on top, and then you put a negative electrode and a layer of separator, and you repeat that until you have stacked up enough of these electrode structures to have the total capacity that you desire in your cell. The separator may be cut to essentially the same size and shape as the electrodes, probably a little bit larger to make sure that there's no opportunity for shifting of this separator and causing a short circuit between the plates, or it may be cut and zigzagged between the electrodes for maybe even a more robust design. The electrodes themselves are stamped or cut into these individual plate shapes out of a longer roll of electrode material, and they are stamped to all have exactly the same size to fit on top of each other neatly. The current collectors in the electrodes have little tabs, as you can see on the right side of this figure, and they're designed so that all of the tabs of the negative electrode current collectors come out at the same place, and all of the tabs of the positive electrode current collectors come out at the same place as each other, but a different place from where the negative electrode tabs come out. On the diagram on this slide, you can see that the tabs are drawn as all coming out of the right side of the cell. Some of the newer designs that are being manufactured have all of the negative electrode tabs coming out of one side and all of the positive electrode tabs coming out of a different side. There are some advantages to the newer design in that you have a more uniform usage of this cell and more uniform temperature distribution in the cell, but there are also some manufacturing challenges because it turns out to be somewhat difficult to reliably seal the pouch where those tabs exit the cell. So inside of this pouch packaging, you see that there are really many negative electrodes and many positive electrodes. All of the negative electrodes are welded together at their tabs and are furthermore welded to the negative terminal of the battery cell. And all of the positive electrodes are welded together and furthermore welded to the positive terminal of the battery cell as well. Cylindrical and prismatic cells are built quite a bit differently from this. In these cells, there's a single long negative electrode and a single long positive electrode. And these electrodes are cut into these long strips of material, and then separator is placed in between them. And then we take this sandwich of positive electrode separator, negative electrode separator, and we wind it in a spiral around a mandrel. In the cylindrical cell, we wind it around a very thin rod or a cylindrical mandrel. And overall, we say that a jelly roll is constructed by analogy to the sugary confection where you take dough and jelly and you wrap it all up and you cook it, and it's called a jelly roll. If the central mandrel is not a rod or a cylinder but is a rectangular plate, we end up with a prismatic cell. And that's really the only difference, is that it's a squashed cylinder that's longer and thinner. Historically, cylindrical cells have been very popular because they're the easiest to manufacture, and they're still the cell of choice in Tesla automobiles. But when you try to pack cylinders together to make a battery pack, there's quite a bit of wasted space between the cylinders. Just try it and you'll see that there's a lot of vacant space between the cylinders. Now, we can use this space to advantage if we design our battery pack in such a way that the space provides a pathway for coolant, such as forced air or forced liquid. But often there's more space left between the cells than is actually needed to cool the battery pack. So prismatic cells are a little bit better in that respect. There's not really necessarily any space between the metal cases when we pack them together, kind of like Lego in a battery pack. In fact, sometimes we find that we have to add a little bit of space between the cells in order to leave a pathway for coolant flow between them. So even though it looks like there's no wasted space in a prismatic cell battery pack, there actually is, because if you were to open up the prismatic packages and look at the jelly roll inside, you would find that at the four corners, there's where the jelly roll is rounded but the case is rectangular, there is a little bit of wasted space. This amount of space is not as much in a cylindrical cell. design, because the prisms can be quite a bit larger, but there still is some space that is not occupied. Essentially, all of this space in a pouch cell design is used by the necessary cell components, and these pouches can be packed together for a very compact overall battery pack. Again, we need to make sure that our design has room for coolant to flow, so sometimes we have spacers between the pouch cells. But overall, we can pack the pouch cells a little bit more densely than the prismatic, and the prismatic a little bit more densely than the cylindrical, usually. If you are interested in more details about how lithium-ion battery cells are constructed, you can pursue the optional honors track to this course and to the specialization in general. And in the 5th week, or the honors week of this course, you will study these details in more depth. If you're not planning to take the honors track, then I think that what you have learned so far is sufficient to really understand what's going on inside of that battery cell enough to proceed and succeed at this specialization. So now I'm going to turn my attention to teaching about the actual materials that are used in a typical lithium-ion battery pack. And we start by looking at the materials used for the particles that form the negative electrode. At this point in history, essentially all commercial lithium-ion battery cells use some form of graphite for their negative electrodes. Graphite is very common. Graphite is the material that is used inside of your pencils, and graphite is one form of carbon, and it's formed by layers of graphene stacked together. The picture on this slide tries to illustrate this, where we look at the structure of graphite at the atomistic scale level, the molecular level. The gray meshes on this slide depict layers of graphene, and graphene is internally comprised of repeating patterns of rings of 6 carbon atoms in a hexagonal shape that overall form a kind of a honeycomb structure. Graphene is extremely strong, and these honeycomb structures are very difficult to break apart. However, the bonding between one layer of graphene and its neighboring layer is quite weak, and this is why graphite is used in pencils. When you write with a pencil, it's these layers of graphene that flake off and stay on the paper. The graphene does not get broken. It's in between the layers of graphene that the graphite fractures and leaves some graphene on your page. And it's also this weak bonding between the layers that makes graphite useful for an electrode material. The purple spheres on this diagram illustrate lithium atoms, and these lithium atoms can intercalate in between these layers of graphene. In graphite, there's room for 1 lithium atom per 6 carbon atoms in this honeycomb structure. I note that when the negative electrode is constructed, there's no lithium in it. All of the lithium is in the positive electrode when the cell is first constructed. And when the battery cell is charged for the first time, lithium from the positive electrode moves through the electrolyte and enters into this graphite and lithiates the graphite. On the previous slide, you saw the microscopic or even nanoscale view of lithium and graphite. On this slide, we look at a somewhat larger scale, and if we do that, we find that the layers of graphene are not uniform large planes that span the entire electrode or even an entire particle. Instead, there are small regions where the graphene that forms the graphite occur with parallel plates, and then there's other neighboring regions where these parallel plates are aligned in a slightly different orientation. We call the individual regions where the graphene is aligned the grain of a particle, and the boundaries between different alignments, the grain boundaries. So if we look at a particle overall, the grain boundaries may be fairly well aligned, or they may be completely random. In natural graphite or human-made graphite, which is called synthetic graphite, the grain boundaries are fairly close to parallel throughout the entire structure. But in some forms of carbon that are usually known as hard carbon or coke, the grain boundaries are quite randomly oriented, and both of these are illustrated on the diagram that you see on this page. So lithium enters into the regions or layers between the graphite, but it does so in slightly different ways depending on whether the electrode is made from natural or synthetic graphite or whether it is made instead from hard carbon. As a result, there are somewhat different voltage properties and lifetime properties for cells built from these materials. Often manufacturers will use some proprietary blend of graphite and hard carbon in their negative electrode. But the details are beyond the scope and are usually proprietary trade secrets. And we don't really need to look at that in this specialization. Now, graphite is used in probably every commercial lithium-ion cell on the market. Not every, almost every lithium-ion battery cell that's used in the market. But there are other materials that could be used as well. And one other material that has some interesting properties is lithium titanate oxide, or LTO. LTO has a very different crystal structure from graphite, and the figure on this slide shows this structure at an atomistic scale. In this figure, the titanium atoms are drawn as orange spheres and the oxygen atoms are drawn as red spheres. The titanium and oxygen atoms are very tightly bonded into this crystalline structure so that these bonds are not disturbed when lithium enters or leaves the particle. And the tight bonding is illustrated in the diagram by showing with green planes the faces of the crystal that these bonds construct overall. Again, lithium is shown as purple spheres, and the purple spheres are able to move through the openings in this crystal structure just like they were able to move between the graphene layers inside of graphite. But while the openings in graphite were simple, wide open layers, the openings in LTO are instead convoluted three-dimensional pathways. And you will learn that some materials used in positive electrodes also share these properties. The graph on the right side of this slide shows the open circuit potential of different negative electrode materials versus their electrode state of charge. Now, the electrode state of charge is related to but different from the cell state of charge. So to be a little bit more precise, I refer to the electrode state of charge as the stoichiometry of the electrode. If the electrode has no lithium stored in its openings, then the stoichiometry will be 0. If the electrode is full of lithium, in other words, it can't store any more lithium than it's already storing, then the stoichiometry will be 1. If the electrode is partially full, the stoichiometry will be a value between 0 and 1, and that's why it represents a kind of an electrode state of charge. Now, the voltage of a battery cell overall is equal to the voltage or potential of the positive electrode current collector minus the potential of the negative electrode current collector. To have a high voltage battery cell, we desire high potentials in the positive electrode materials and low potentials in the negative electrode materials. And looking at this graph, you can see why graphite is so attractive. The light blue or cyan colored line labeled MCMB is a form of graphite. MCMB happens to stand for mesocarbon microbeads, but all that we need to know here is that it's a type of graphite. These beads are nearly spherical, and if you look at them at the mesoscale or at the SEM kind of scale, which is why they're called these beads. We see that this graphite has a very low potential over its entire stoichiometry range, and that's really attractive when designing a high voltage lithium-ion cell. You can also see that the hard carbon and coke, which are other forms of carbon, have slightly different voltage characteristics. From a voltage perspective, they're not quite as attractive as graphite, but from a lifetime perspective, they can have some advantages. Lithium titanate oxide has the highest potential of all of those that we've seen as a candidate for a negative electrode. So from a voltage perspective, this material is not very attractive when we're designing negative electrodes. However, it turns out that battery cells that are constructed using lithium titanate oxide as their negative electrodes are nearly indestructible. These electrodes can be charged and discharged tens of thousands of times with very little noticeable capacity loss. So while the high voltage or high potential of the material means that the energy density of a cell using this material is quite low, the lifetime advantages can be very attractive, especially when we're not as concerned about the energy density. Another possible negative electrode material is silicon. The possible advantage of using silicon is that it can store more lithium than carbon can. If we use graphite as our electrode material, we can store up to 1 lithium atom per 6 carbon atoms. But if we use silicon as the electrode material instead, it turns out that we can in principle store up to 4 lithium atoms for every single silicon atom. And if you do the ratios, you find that this is a roughly 24-to-1 storage advantage using silicon instead of using carbon. In other words, the energy density if we use a silicon electrode can be a lot higher. There is a trade-off. If we use graphite as our electrode material, the volume change when we charge and discharge the electrode is about 10%, which is not very much. And that means that the stresses and strains caused by this volume change on the electrode is pretty small. But if we use silicon as our electrode material, the volume change is around 300 or even 400%. And that means that the stresses and strains are enormous. And because of that, silicon electrodes tend to fracture very quickly, and so they have short lives. So there's an enormous potential advantage of using silicon as the electrode material in terms of energy density, and that's led to a lot of research in developing ways to make silicon electrodes practical in a cell design. Some of the workarounds that researchers are looking at include mixing some graphite and some silicon together inside of the electrode so that the silicon does not need to form as large a volume fraction of the electrode, and therefore the electrode has some of the benefits of graphite and some of the benefits of the silicon materials. Another workaround might be to use silicon nanowires that leave spaces in between these nanowires for expansion. And the photograph that you see on this slide shows an SEM image of silicon nanowires. You can see they're like hairs on an animal or maybe carpet fibers. And the spaces in between these nanowires allow room for expansion and contraction and minimize the amount of fracture that happens in the electrode. At present, I'm not aware of any commercially successful lithium-ion battery cell that has a silicon electrode, but I believe this is very likely to change in the future. So to summarize what you've learned in this lesson, you now know that lithium-ion battery cells are manufactured in pouch, prismatic, and cylindrical form factors. In each of these cases, the current collector metal foils are generally coated on both sides with active materials. In the negative electrodes, the most common active materials at this point in history are some form of carbon. This might be natural or synthetic graphite, or hard carbon, or even some mixture of these materials. In a minority of lithium-ion battery cells at present, we can find lithium titanate oxide, or LTO, used as the negative electrode material. This material greatly increases the cell longevity, but it's costly because of the relative rarity of titanium, and it also lowers the energy density of this cell. In the future, I believe it's very likely that we will see lithium-ion battery cells that have some form of silicon in their negative electrodes. This will improve the energy density, but at present, you've learned that the big problem is that the cycle life, or the number of times the cell can be charged and discharged, is low when we use silicon electrodes. When this problem is overcome, then we're going to see a lot of silicon-containing electrodes in the future. That brings us to the end of this lesson, and in the next lesson we're going to look at the materials that can make up a positive electrode in a lithium-ion battery cell instead. In the last lesson, you learned that different materials can be used in the negative electrodes in lithium-ion battery cells. If you remember, we looked at graphite and at lithium titanate and also at silicon. In this lesson, we are going to look at materials that can be used for positive electrodes instead, and it turns out that there are many more options from which we can choose. The first intercalation material that was discovered for positive electrodes in lithium-ion battery cells was lithium cobalt oxide. And this material was discovered in 1980 by Professor Goodenough and his research team. The atomic crystalline structure of lithium cobalt oxide is drawn on this slide. Cobalt is shown as dark blue spheres, and oxygen is shown as red spheres. In the structure on this slide, cobalt and oxygen form very tight electrochemical bonds with each other, and these are not affected by lithium moving into and out of the material. And so because these bonds are constant, they're shown with these planes, the blue planes that show the surfaces formed by the crystalline structure of these bonds. When lithium enters into the electrode and when lithium leaves the electrode, the structure of the lithium cobalt oxide is not actually changed. It does not disturb these these cobalt oxygen bonds. As you see in the figure, the overall structure has layers of this cobalt oxide material, a lot like graphite has layers of graphene. And because cobalt oxide has this layered structure, it's often called a layered cathode material. The lithium atoms are free to enter and exit and to move around the space between the cobalt oxide layers. You'll notice in the chemical formula in the third bullet point on this slide that the subscript for lithium is X. This might not seem common to you. It might seem unusual if you're more familiar with chemical formula like H2O, where the subscripts are all integer numbers. The X in this formula is there to show that there is a variable amount of lithium in this structure. If there's no lithium at all in the structure, then X is 0. If the structure has as much lithium as it can possibly hold, then X is equal to 1. And if the structure has some amount of lithiation but not full lithiation, then X is going to be a number between 0 and 1. And so we see that X is not describing what's happening right at one point in an atomistic scale. It's actually an average over the whole electrode, or at least over a local region, of how much lithium is present, which is why it can be a fractional number. So as we charge a battery cell and discharge a battery cell, this value for X is going to change. The value indicates an electrode state of charge, and it's what we called a stoichiometry in the last lesson. Lithium cobalt oxide actually makes quite a good positive electrode material, and it's in very common use. You find it in a lot of portable electronics and laptops and mobile phones. But there are some challenges when we try to scale up the lithium cobalt oxide for very large battery cells for very large applications. For example, thinking about vehicle use or utility grid use. One of the problems is that cobalt is very rare, and so it's expensive. It's also a toxic element, and so we don't want to have too much of that getting thrown out by accident and entering in landfills. Another challenge with lithium cobalt oxide that may not be readily apparent is that we can only use about half of its theoretic capacity. If we think about the value of X in the subscript for lithium on the previous slide, the value of X can really only go between about 0.5 and 1. If it goes below 0.5, we have some capacity degradation issues that happen. So in order to make this material more practical for large-scale application, researchers have substituted different elements for some of the cobalt in the structure. If we substitute all of the cobalt with nickel, we end up with lithium nickel oxide, and that actually has a higher energy density for the same amount of material, so we can store more energy. Lithium nickel oxide, however, it has the higher energy density because it has higher voltage, which is nice, but it also suffers from being less stable thermally, meaning that if you overcharge the battery cell, it's more likely to combust, and that's, of course, very undesirable. It's also possible to substitute other metals. For cobalt, we can substitute aluminum or chromium or manganese, and these all give slightly different properties when we do so. Maybe the most popular substitution presently is to replace some of the cobalt with nickel and some with manganese, and so we end up with a nickel cobalt manganese, or NCM, material. And this material has exactly the same atomic crystalline structure as you see on this slide. It's just that some of the cobalt is replaced with other elements. The nickel in the structure tends to increase the voltage, and the manganese tends to make the material more thermally stable, which is a desirable property. At this point in history, many automotive battery packs are made with this NCM or NMC type of battery cell. Another alternative is to replace some of the cobalt with nickel and some with aluminum, and this is an NCA battery cell, and this is the type of battery cell that's used in Tesla automobiles at this point in time. We can investigate a completely different structure for positive electrodes, which is lithium manganese oxide, and this material was also discovered by Professor Goodenough and his research team. The image on the right of the slide shows the atomic scale crystalline structure of this material, and the blue spheres are manganese in this case, and the red spheres are oxygen. This structure might look familiar to you if you have a good memory. It's what we saw in the previous lesson for lithium titanate oxide, which is a possible negative electrode material. The name of this crystal structure is cubic spinel. And as you can see, there's many internal vacancies that could hold lithium, but these vacancies are organized, if you will, in convoluted, twisted, three-dimensional pathways. That allows the diffusion of lithium in three directions. And it's difficult to see this in a static picture on a slide, but it happens that lithium can enter in from both sides, it can enter in from top and bottom, and it can enter in from front and back as well. So from all three directions, and because of that we call this a three-dimensional structure. If you contrast it with the layered structure of lithium cobalt oxide, in that structure lithium could enter front and back and left and right, but it could not enter top and bottom. So lithium could move only in two directions, and we called that a two-dimensional structure. And on the next slide we're going to see a candidate positive electrode material where lithium can enter only through one direction in tunnels, and we call that a one-dimensional structure because of that. In the chemical equation for lithium manganese oxide, notice again there's an X in the subscript for lithium, and in this material X can go from 0 all the way up to 2, which is different from what we saw in lithium cobalt oxide. However, if X is larger than 1, the material tends to dissolve in the electrolytes commonly used in lithium-ion battery cells, and for that reason we use X from 0 to 1 almost always in practice. A huge advantage of the lithium manganese oxide versus lithium cobalt oxide, or even NMC or NCA, is that it is less expensive because manganese is very common, and it's also safer. But the drawback, as I've kind of hinted at already, is that it can have short life. It turns out that the manganese in the structure is very susceptible to acidic electrolyte conditions. Now, we don't make acidic electrolytes on purpose, but if there's any moisture in the air when we are building this cell, this moisture gets absorbed in the electrolyte, and it can combine with some common electrolyte salts, and the hydrogen from the water and the moisture and some fluorine from the salts can combine into hydrofluoric acid, HF. This hydrofluoric acid is really terrible stuff, and it's a very powerful acid, and it can eat away at the manganese in the lithium manganese oxide. And so the manganese can dissolve, and so the positive electrode structure basically dissolves, and there are less vacancies that are able to hold lithium, and so we have capacity loss. So when we build the cell, we try to eliminate moisture, but it's not possible to eliminate it completely. We build this cell in an environment where the electrolyte is injected in what's called a dry room, where we've evacuated as much moisture as we reasonably can, but there will always be some moisture in the electrolyte. So much of the research that you see in the literature, you're going to find people talking about lithium manganese oxide battery cells, and a lot of that is because it's quite inexpensive to obtain the material for a research lab, and it's quite inexpensive and easy to obtain. And because of that, because a lot of research is done with the material, you will also see a lot of papers where people investigate ways to prolong life. Sometimes they do that by adding different chemicals to the electrolyte that preferentially scavenges the acid so that the acid attacks these added materials instead of attacking the electrode itself. And sometimes you see people coating the electrode particles with something that protects the particles from the acid. Any battery cell that uses lithium manganese oxide is going to have something as part of its design in order to extend its life, but it's usually not disclosed to you exactly what that is. It's a trade secret almost always. A third variety of positive electrode active material was once again discovered by Professor Goodenough's research team, and these are the olivine-style phosphates. The most commonly found member of this family is called lithium iron phosphate. This material is very inexpensive and it's very non-toxic, and that's all fantastic. But unfortunately, it also has low energy density because of the low open circuit potential of the material, as we'll see later on. And it also has low specific energy because iron is a very heavy element. Its structure also makes it difficult to get a lot of power out of the material, so it's often a low specific power material. The image on the right of the slide shows the structure, and in this image, iron is represented by the brown spheres, and phosphorus by gray spheres, and oxygen by red spheres, and the lithium, again, as purple spheres. And in this overall structure, the iron oxide, the FeO6, forms the brown octahedral crystal shapes, and the phosphate, the PO4, forms the gray tetrahedral shapes. And in the image, you can see that the lithium atoms can go only one direction into these tunnel-like vacancies in the structure. It's not free to flow in 2 dimensions like it is in a layered cathode, or in 3 dimensions like it is in a cubic spinel cathode. And so that tends to reduce the power that's available. The most common way to solve this problem is to use extremely small particles in our positive electrode, which means that the diffusion distance is very short, and therefore the diffusion overall can happen more quickly and we can get a lot of power out. But we require very small particles to do this. Another challenge using the material is that it has very low electronic conductivity. It's difficult for the electrons to move around in the active material. And the way to get around this problem is by coating the material with conductive additives like carbon black, so that the electrons can flow on the surface of the particle through the carbon black from the electrode to the current collector and out of this cell. There are different candidates for positive electrode materials, but I've shown you the most common ones. Most of what you see that's different from this are simply mixtures of these, where some optimization has taken place to attempt to get the most desirable properties from 2 or 3 different materials at the same time by combining them in what we call a blend electrode. So in summary, in this lesson, you've learned about the materials that are most commonly used in positive electrodes in commercial lithium-ion battery cells at this point in time. Since essentially every lithium-ion battery cell on the market has a graphite negative electrode, the distinguishing factor between the chemistries of different cells is therefore what is going on in the positive electrode. And so it's quite common to refer to a cell by the chemistry of its positive electrode only. We might talk about a lithium cobalt oxide cell, or we might talk about an NMC cell, or a LMO cell, or a lithium iron phosphate cell, or something like that. And you've already seen that you can predict a little bit about the different power capabilities of this material depending on whether it's a one-dimensional or a two-dimensional or a three-dimensional structure. It also turns out that these different materials have different voltage properties that lead to different energy densities. Remember that the voltage of a battery cell is equal to the potential of the positive electrode current collector minus the potential of the negative electrode current collector. Therefore, for a high voltage battery cell, we would like to have a positive electrode that has a high potential. The figure on the right of this slide shows the open circuit potential of these different electrode materials as a function of how much lithium is in them, their stoichiometry, or the electrode state of charge. You can see that lithium iron phosphate has the lowest potential of all of those that we've considered. This means that lithium iron phosphate cells tend to have low energy density because of this. You can see that other types of positive electrode materials have slightly different voltage characteristics, but all of them turn out to be higher than lithium iron phosphate. When we come to the third course in the specialization that talks about estimating state of charge of a battery cell, we're going to find that the different voltage characteristics of these materials is also important at that point. You're going to learn that the accuracy of a state of charge estimate depends quite heavily on the information that is conveyed in the voltage signal that we measure. And simply by looking at the graph on this slide, you can already begin to predict some qualities of estimating state of charge using different materials. In particular, notice that the iron phosphate curve has essentially no change in voltage over about 80% of its state of charge range. This means that the voltage I measure at 20% electrode state of charge and the voltage I measure at 80% state of charge are almost exactly the same, and so by voltage only it's going to be very difficult to distinguish what state of charge is for battery cells using this material. Looking at the other materials, we see that lithium manganese oxide also has some flat spots in its overall profile, but it is a little bit less flat overall than iron phosphate, and so it's a little easier to estimate state of charge for an LMO cell. And looking at the NCA and NMC cells, you might imagine that it would be easier to estimate state of charge, well, because there's a fairly consistent slope or a fairly consistent change in voltage across the state of charge range, and that actually is true, that these tend to be the easiest cells to write good state of charge estimation algorithms for. So when you choose a cell chemistry in the design of the battery pack, there's going to be implications beyond simply energy density or power density. There will also be implications on the ability of the battery management system to regulate the activity of the battery pack. So to wrap up, remember that layered positive electrodes can use only about half of their theoretic capacity. I didn't explain why, but it turns out that if you take too much lithium out of those layers that separate the cobalt oxide layers, the layers will tend to collapse and it will not be possible to insert lithium between the layers anymore. So we need to keep about 50% electrode state of charge or higher to make sure that the layers don't collapse on each other. We learned that the olivine positive electrode materials have low voltage and give very little state information in that voltage as well, and that the spinel positive electrodes are inexpensive and non-toxic, which is great, but that they also tend to degrade rapidly. So there are advantages and disadvantages of all of these materials. Doesn't matter which one you choose. It turns out to be an engineering effort, as always, to balance the trade-offs to find the best one for your particular application. So that brings us to the end of this particular topic, and from here we're going to move on and look at the electrolyte, the solvent and the salts chosen for lithium-ion battery cells, and also the separator. In the last two lessons, you've seen that the most common materials used in negative and positive electrodes in lithium-ion battery cells are graphite in the negative electrode and some other common materials in the positive electrode. In this lesson, you will learn about the electrolytes and the separators for these cells, and we start by looking at the electrolyte. You might remember that the electrolyte is the media that conducts ions between the electrodes internal to this cell, and that in a general electrochemical cell, the electrolyte consists of a solvent into which we dissolve either a salt or an acid or a base. Some battery cells use an electrolyte whose solvent is water, and we call those aqueous cells. But if you look at the electrochemical series, you will notice that water dissociates into hydrogen gas and oxygen gas at a potential of around 2 volts. So any battery cell having voltage higher than 2 volts cannot use water as its solvent. The slight exception to this is the lead-acid battery cell that has voltage that's often a little bit over 2 volts per cell. And the reason that this is possible is that when sulfuric acid is dissolved in the water, that slightly changes the voltage at which water breaks down into hydrogen and oxygen. It slightly elevates that voltage and makes a 2-volt battery cell possible. But it's not possible to get it much above 2 volts. And so an aqueous solution in a lead-acid battery cell actually works, but an aqueous solution would not work for a lithium-ion battery cell because these typically have overall voltages much higher than 2 volts and usually higher than 3 volts as well. So instead, the lithium-ion battery cells are made using electrolytes that are non-aqueous, and they are built using organic solvents plus a lithium-based salt that dissolves into that solvent. The electrolyte in a lithium-ion battery cell acts purely as an ion conductor. It does not take part of the normal chemical reactions for charging and discharging the battery cell. The table on this slide shows some of the most common solvents that are used in electrolytes in lithium-ion battery cells. These include ethylene carbonate, propylene carbonate, dimethyl carbonate, ethyl methyl carbonate, and diethyl carbonate. The table also shows the common abbreviations that you will see in the literature. Ethylene carbonate is abbreviated EC, propylene carbonate is PC, dimethyl carbonate is DMC, ethyl methyl carbonate is EMC, and finally diethyl carbonate is abbreviated DEC. Each of these solvents has slightly different properties. Some of them become essentially solid at temperatures below around 0 degrees Celsius, so these solvents are not appropriate for battery cells that must operate at low temperatures. Others cause the cell to degrade more or less rapidly. Even though the solvent does not participate in the normal reaction of charging and discharging a battery cell, it can participate in undesired side reactions that slowly cause the cell to deteriorate over time. And so to get the most desirable properties in a design so that it works well at cold temperatures and warm temperatures and that it doesn't degrade quickly, often these solvents are mixed together in the electrolyte in different ratios. And it's beyond the scope of this specialization to look at the reasons behind all these different properties, but I would like to share out a common feature to all of these. If you look at the chemical bond structure of each of the solvents that's drawn in the table, you will notice that they are different in many ways but similar in one way. At the top of each one of these molecules there's an oxygen that is double bonded with a carbon atom. This double bond causes the oxygen atom to develop a slight negative charge and the other parts of the molecule to develop a slight positive charge. So the overall molecule is slightly polarized. And it's this polarization that allows these solvents to dissolve salts. So when we add a salt, which if you remember is an ionic compound that has one component that's positively charged and one component that's negatively charged, this salt will easily break down into a cation and an anion inside of the solvent, and it will make a good electrolyte for the lithium-ion battery cell. The most commonly used salt in a lithium-ion battery cell is lithium hexafluorophosphate, which I find quite difficult to say. And in this specialization, I will not need to refer to the salt very frequently, but when I do, I will probably simply call it LiPF6 instead. There are some other candidate salts that are used, and these include lithium tetrafluoroborate and lithium perchlorate. These are used for some reasons, but they are certainly not as common as LiPF6. As we talked about on the previous slides, the solvent does not participate in the normal chemical reactions in the lithium-ion battery cell, but different solvents have different properties with respect to aging and low temperature performance and so forth. And in the same way, different salts have different properties with respect to aging and so forth. But they don't usually have much impact on how a battery management system conducts its day-to-day life, and so we don't have much opportunity to discuss the design choice of building a salt. So because the solvent does not participate in the chemical reaction, but the salt does, because the salt is a charge carrier through the solvent, it's common to refer to the electrolyte simply by naming it salt and by kind of omitting what the solvent is, even though the electrolyte we know includes the solvent and the salt. So we might refer to an LiPF6 electrolyte, and it's simply understood that there's also a solvent mixed in that we're not mentioning. Lithium-ion battery cells must also have a separator. The separator is a permeable membrane that has tiny holes in it, and these holes are large enough that ions can pass through them, but they're also small enough that the positive and negative electrode can't touch each other. If they were to touch each other, you would have a short circuit, which would lead to heat buildup and thermal runaway, possibly a fire or an explosion. For this reason, the separator also must be an electronic insulator. We can't allow electrons to flow across the separator, but we want ions to flow very easily through the pores in the separator. The image on the left shows a separator material that's used in some lithium-ion battery cells, and to the unaided eye, it looks just like a thin sheet of white plastic, and you can even see my fingers through the material. It's that thin. But if you look at it under magnification, as I show in the center image on this slide, it's possible to see these tiny pores between the fibers of the material. The pores are large enough for the ions to go through, but they're small enough that the electrode materials cannot contact each other. And that's really illustrated in the photograph on the right side of this slide, which shows a scanning electron microscope picture of a single particle of lithium manganese oxide material on top of a separator to give you an idea of the relative scale. And you can see that the pores in the separated material are much, much, much smaller than a particle size, so that particles on either side of the separator will not contact each other, but that the ions can still flow through the pore openings. Lithium-ion battery cells, of course, also have current collectors, and these are made from metal foils onto which the electrode materials are deposited. The purpose of the current collector is to conduct electrons from the electrode materials to the tabs of the terminals of the cell to the outside circuit. And these foils are subjected to very harsh environments inside the cells. The lithium ions in the electrolyte and also the fluorine-based ions in the electrolyte tend to be very reactive chemically, and they want to undergo chemical reactions with just about everything. So we choose current collector materials very carefully so that they will not be degraded by the interior chemical environment of the battery cell. In every lithium-ion battery cell of which I'm aware, the positive electrode current collector is aluminum foil. And this is chosen, if you remember back when we looked at the electrochemical series, because aluminum tends not to react to anything as long as its potential is about 3 volts or higher. And the positive electrode active materials, of course, are chosen to have higher potentials. And in the normal operating region of the lithium-ion battery cell, then they will not react with this aluminum and cause any damage to it. In the negative electrode, the current collector is almost always a copper foil. And that's again chosen because if you go back to the electrochemical series, you will see that any potentials lower than about 2 volts, the copper is stable electrochemically and will not react. The image on the right side of this slide shows a simple roll of aluminum foil that you might use in your kitchen for food products. And the foils that we're talking about for lithium-ion battery cells are actually very, very similar to these. So the positive electrode current collector is made out of a similar aluminum foil. The primary difference between the battery cell current collector and what you would have in your kitchen is thickness. The battery cell aluminum foil is usually on the order of 20 microns in thickness, which is quite a bit thinner than what you would use in your kitchen. So to summarize this lesson, you are reminded that the electrolyte in a lithium-ion battery cell comprises both a solvent and a salt. The solvent is usually made out of some combination of ethylene carbonate, propylene carbonate, dimethyl carbonate, ethyl methyl carbonate, and diethyl carbonate. The salt is usually lithium hexafluorophosphate or LiPF6, but there are some other options that are occasionally used, and these include lithium tetrafluoroborate or lithium perchlorate. The most common salt, LiPF6, dissociates into a lithium cation in the solvent and a PF6 anion as well. The PF6 anion turns out to be inert towards strong reducing agents such as lithium metal, and that makes it very attractive inside the cell because it will not react with them. You might remember in the previous lesson I mentioned that trace amounts of water in the electrolyte can lead to forming hydrofluoric acid or HF. This comes from the water or H2O dissociating into hydrogen and oxygen, and the PF6 dissociating into PF5 2- and F-. And the hydrogen from the water and the F- from the PF6 combine to make hydrofluoric acid or HF. And this hydrofluoric acid will slowly dissolve the inside of the battery cell, and in particular some of the positive electrode active materials are very sensitive to it. So for this reason, it's very important to fill the battery cell with electrolyte in a dry environment where as much moisture has been removed from the air as practically possible, so that we have very little of this moisture in the electrolyte and therefore very little of this hydrofluoric acid. You have learned that the separator in a lithium-ion battery cell is a non-conductive porous membrane that simply separates mechanically and physically both electrodes to prevent short circuits. But we've also seen that it must have small pores or holes in it that allows the electrolyte to permeate through the separator and allows the cations and the anions in the electrolyte to move back and forth so that the normal operation of the battery cell can happen. And finally, you've learned that the current collectors are made from very thin copper and aluminum foils. So that brings us to the end of this lesson, and so far this week you've learned about the materials that make up negative electrodes and positive electrodes and electrolytes and separators and current collectors. The next topic we look at, I think, is a very interesting one, and it asks the question, is lithium a very rare element that's likely to run out if we insist on making electric vehicles, for example? Are we exchanging some kind of oil shortage with a lithium shortage? And so next topic, we'll have some fun looking at that. We conclude this week's learning material with a lesson that I think is very practical and important, but it's also kind of a fun thought experiment. As you know, there's a lot of reason to be concerned at the rate at which we're using fossil fuels. Even if our planet were completely full of oil in its center, and of course it isn't, At some point, if we use the oil and never replenish it, then we will run out. And I'm not going to argue about when that might be. That's not my concern. My concern is, are we replacing a potential oil crisis with a lithium crisis? If we adopt lithium-ion battery cells for large-scale applications like electric vehicles and grid storage and so forth, are we going to consume lithium at such a high a rate that we're likely to run out of lithium very soon? So people are concerned about this, and it's an important question, and it's one that we're going to ask and see what answer we come up with. The chart on this slide shows the relative abundance of every element in the periodic table in the Earth's crust. These elements are organized by their atomic number on the bottom axis and their relative abundance on the vertical axis. And you can also see on the vertical axis that it's a logarithmic scale, which means that one axis unit above the other indicates a factor of 10 greater abundance. We're curious to see where lithium ends up on this chart, and if you look at the chart and study it for a little while, you'll see that lithium is between 20 and 100 times more abundant than either lead or nickel, which are used in present-day battery cells quite a lot. So from that perspective, we would think that there might be plenty of lithium for batteries, at least compared to lead acid and nickel-based chemistries. Now, it's also true that it's difficult to find lithium deposits in nature, since lithium is one of the most reactive elements, and lithium is not usually found isolated in its elemental form all by itself. It's usually found in some lithium-based compound instead. So we need to find these lithium-based compounds and do some processing on them in order to extract the lithium for use in our battery cells. So we'll consider that a little bit also. While we're on the slide, you might notice that the relative abundance of cadmium and mercury, whose usage is deprecated because of their toxicity, are about 1,000 times less common than lithium, but they're still used commercially, including in battery cells. So the previous slide says that lithium is relatively abundant on this planet, but how much lithium would we actually need in an electric vehicle? So for purpose of example, let's consider a lithium cobalt oxide battery cell. If we go to the periodic table and look up the atomic mass of lithium and of cobalt and of oxygen, and we compute the mean atomic weight of lithium cobalt oxide and compare it with the mean atomic weight of lithium itself, we find that lithium cobalt oxide is approximately 7% lithium by weight. The positive electrode particles comprise only a portion of the overall cell construction as it's made. If we think about the entire cell, we find that lithium cobalt oxide comprises less than about 1/3 of cell weight, and so the lithium content of the electrode turns out to be only about 1/3 of 7%, or about 2% of cell weight. And maybe you're wondering about lithium in the negative electrode. When the cell is manufactured, there is no lithium in the negative electrode. The first time you charge this cell is when lithium enters the negative electrode, and that's why we're considering only how much lithium is in a fresh lithium cobalt oxide electrode. Now, there is some lithium in the salt used in the electrolyte, such as LiPF6. The electrolyte in total comprises about 10% of the cell weight, and if we use the lithium hexafluorophosphate, or LiPF6, as our salt, the amount of lithium in the electrolyte is about 10% of the 10%. So overall, lithium in the electrolyte constitutes about 1% of cell weight. So combining the amount of lithium in lithium cobalt oxide and in the electrolyte, we find that a high-energy lithium-ion battery cell has about 3% of its weight that's made up from the lithium itself. So we're going to do some more analysis with that number to see what that means practically, but before we do that, I want to point out the photograph on this slide. This is a picture of piles of lithium salt from one of the most common ways of obtaining it in nature. Enormous salt flats, primarily in South America, but we find them in other places as well, contain high quantities of these lithium-based salt compounds. So lithium is obtained by mining these salt flats, by taking these salts and processing them, and then extracting the lithium from them. So let's continue with our example. Remember that we said that lithium content in a high energy battery cell is less than about 3% of that cell's weight. Batteries used in hybrid and electric vehicles weigh roughly 7 kilograms per kilowatt hour. And so we can say that the lithium content is about 3% of that, or about 0.2 kilograms per kilowatt hour. How many kilowatt hours do we need? So we need to think about how large this battery pack must be for different types of vehicles. So let's consider an electric vehicle with a 200-mile electric range. It turns out that this vehicle needs about 60 kilowatt hours in its battery in order to obtain that range. And you'll find out how to compute that number, simulate that number in the second course in the specialization. But for now, I just state that number for you. So if we consider that we require a 60 kilowatt hour battery pack and there's going to be 0.2 kilograms per kilowatt hour, that ends up being a total of about 12 kilograms of lithium per electric vehicle. Now, an electric vehicle is the extreme case for the purpose of transportation. A plug-in electric vehicle uses much less all-electric range. So for a plug-in hybrid electric vehicle, we would maybe require about 10% of an electric vehicle battery capacity. And a hybrid electric vehicle requires even less capacity than that. So let's take the worst case. Let's consider 1 million electric vehicles. These would require 1 million electric vehicles multiplied by 12 kilograms per vehicle, or about 12,000 tons of lithium. 1 million plug-in hybrid electric vehicles would consume less than about 1,200 tons. To make the example simpler, we are assuming that there's no recycling, but of course all of these battery sacks will be recycled when they come to end of life. But even without recycling, and by doing some simple arithmetic, we want to know if there's enough lithium on the planet to support our desire for electric vehicles. So if we go back to the chart on the first slide, and if we convert that data to actual quantities of each element, it turns out that the known available supply of lithium is over 200 billion tons. So by simple math, every human being presently alive could own more than 2,000 electric vehicles. And that's even without recycling. And if we are recycling, of course we have an essentially endless supply if we assume our recycling efforts are ideal. So you may have seen news articles where writers try to make the public fearful about the lithium supply. And these authors cite different references as to the available supply of lithium in order to support their claims. But please note that the chart that was on the first slide of this lesson was generated by the United States Geological Survey, which is a very reputable source. But on the other hand, remember that this source includes the amount of lithium that's dissolved in seawater, and it turns out that the majority of lithium available on our planet is dissolved in seawater, and it's fairly difficult to extract that lithium from the seawater. So it means that the analysis I perform here, while being accurate, is also a little optimistic because of that. So you have to weigh how much lithium is easily available versus how much there is total. And every year, more and more easily available lithium deposits seem to be found. And so it's my opinion, you can form your own of course, that we really don't have a lithium crisis. So, does that mean everything's okay? Well, maybe. But there are other elements used in lithium-ion battery cells that turn out to be far more rare than lithium even. We've seen already this week that lithium-ion battery cells use electrodes that are made from different materials. Now carbon, which is used in the negative electrode, is very common, so there's no real concern about that. And as long as we use graphite as our negative electrode material, we're not going to run out of that. But the positive electrode materials are a little bit less certain. Most positive electrode materials in commercial lithium-ion battery cells use at least some cobalt, and cobalt is quite rare. And most of our cobalt supply comes from the Congo, which also has some political instability. So it may be reasonable to have some worry about battery technologies for electric vehicles, but in my opinion, not because lithium might run out, but because some of these other elements are quite rare. But there are solutions for that as well. even if it turns out that our cobalt supply becomes very constrained, we already know that there are other candidate materials that can be used as the positive electrode of lithium-ion battery cells that can replace cobalt. And we've seen that LCO can be replaced by NMC, which greatly reduces the amount of cobalt, or by NCA, which reduces the amount of cobalt, or even by iron phosphate or LMO. So, in summary, I'm quite optimistic about the future battery supply for electrified vehicles and other applications. So to summarize this lesson, it turns out that lithium is one of the most abundant elements on the planet. We've done some very simple back-of-the-napkin approximate analysis, but even if it's a little bit wrong, it shows that the total supply of lithium is more than sufficient to meet demand for consumer electronics, for electrified drivetrains and other applications, even if we don't recycle. And of course, we're going to recycle, and recycling can only improve this picture. On the other hand, there are other elements such as cobalt or other elements used in lithium-ion battery cells that are more scarce than is lithium. But if for some reason this doesn't get very much attention in the press, and even so, as we've discussed, there are alternative compounds that could be used that don't rely on these rare elements and are therefore much more abundant. So, to conclude, I'm quite optimistic about the supply of materials for lithium-ion battery cells in the future. To summarize our progress this last week, notice that we extended beyond an initial understanding of how electrochemical cells work and focused our attention instead on learning how lithium-ion battery cells work and how they differ from standard electrochemical battery cells. We looked first at why someone might be interested in exploring using lithium-ion battery cells instead of standard electrochemical battery cells. We saw that some of the advantages happen to include high energy density and high power density, and the fact that a single package develops a higher voltage, so we don't need to stack a lot of cells in series for a high voltage battery pack. We looked at how the mechanism that causes a lithium-ion battery cell to operate differs from that of a standard electrochemical battery cell. It's a little bit similar to how the negative electrode works in a nickel metal hydride cell. But in a lithium-ion battery cell, the intercalation mechanism happens in both the negative and the positive electrodes, whereas in the nickel metal hydride it's confined only to that negative electrode. We discussed that the intercalation mechanism is much more gentle than a standard chemical reaction, and for that reason, lithium-ion battery cells tend to last much, much longer than electrochemical battery cells do. For example, a recent news article I saw indicates that the battery pack in a Tesla vehicle will probably exceed 500,000 miles of range before it reaches end of life. We then spent some time exploring materials that are used for current collectors and for electrodes and for the separator and for the electrolyte in different types of lithium-ion battery cells. We saw that the properties, especially of the different electrode materials, causes slight differences in how the different varieties of lithium-ion battery cells perform. For example, we've seen that some have higher voltage than others, and some might have longer life than others, and some might be less expensive than others. And finally, we conducted this really interesting back-of-the-napkin thought experiment regarding whether the global supply of lithium is sufficient to meet the possible future demand. And, at least in my summary, I think that the outlook looks very positive for the future. So where do we go from here? Remember that our focus in this specialization is leading to being able to develop algorithms to manage lithium-ion battery packs. We've spent some time now learning about how battery cells work, and now it's time to begin changing our focus to look at how battery management systems work. And so the remainder of this course focuses on the required functionality of a battery management system. As we move on from this course into later courses in the specialization, those later courses are going to build on that knowledge, and you will learn how to develop the algorithms that go inside of a battery management system. but at the present time we're still really looking at a higher level functionality of the battery management system itself. In particular, we will ask the questions, what does a battery management system need to do? What are some design considerations for the battery management system and for the architecture of the overall battery pack and how those are connected with each other? What are the sensing requirements of a battery management system, and how do we actually find the sensors and build the sensors to meet those requirements? How does a battery management system safely connect to its load and disconnect from its load, and some other safety considerations related to that? And finally, what does a battery management system need to know about the thermal management of a battery pack? So you will learn about all of these and even more in the remaining 2 weeks of the course. So far in this course, we've spent almost all of our time looking at how battery cells operate. And during the first week, you learned how standard electrochemical battery cells work. And during the second week, you learned more about how lithium-ion battery cells work and how they work a little differently. Now we're beginning to turn our attention to the battery management system that controls and manages battery packs built from many lithium-ion battery cells. And during the next 2 weeks, you're going to learn the principal requirements of a battery management system and some ideas of how those requirements can be satisfied. We will not discuss algorithms themselves in any depth. We will leave that for later courses in the specialization to do so. Again, at this point, our primary objective is to get a fundamental understanding of what a battery management system is and what it must do. Remember that a battery management system, or a BMS, is something that we called an embedded system in the first week of the course. An embedded system is made from purpose-built electronics combined with purpose-built software or processing in order to enable a specific application. The photograph on this slide shows the battery management system electronics from a Ford C-Max Energy plug-in hybrid electric vehicle. My research team happened to purchase a battery pack from a totaled vehicle from a salvage yard because we wanted to do some research using the battery cells. But when we disassembled the battery pack, we also disassembled the battery management system casing to see what was there, and this is what we found. You can see that this battery management system has a large number of electronic components on a circuit board. And around the edges of the board you can see connectors in a variety of different colors. Most of these connectors are wired directly to the terminals of the cells that enable measuring the individual cell voltages. Others of the connectors are wired to different other computing elements in the vehicle, such as the master vehicle controller and so forth, in order to enable the battery management system to communicate with the host application what are the available limits of the battery pack. All of these connectors turn out to be slightly different mechanically from one another, so it's physically impossible to plug in the wrong connector in the wrong connection. And when we look at the circuit board itself, you can also notice that the color of the circuit board is different on one side from the other. The left side of the circuit board houses most of the analog sensing elements that measure voltages and perform balancing that we will discuss in the coming weeks. And the right side of the circuit board contains most of the digital elements to do the computations required by the battery management system. When we're operating the battery pack and the battery management system, the cells in the battery pack are going to generate some heat because of their some resistance in them, and that heat must be dissipated by the thermal management system of the vehicle. But it also turns out that the electronics of the battery management system generates heat that must also be managed by the thermal management system of the vehicle. So this circuit board that you see on this slide is housed in a metal case using thermally conductive paste so that there's good thermal conductivity but bad electronic conductivity between the components on the circuit board and the metal casing so that heat can be removed from the metal case. And in this picture, I scraped off that paste so you could see the main circuit elements more clearly. The majority of the paste was over the elements in the top and left part of the battery management system. It looks almost like a grid. And also over some of the computing elements to the right, where the computing elements may generate more heat. But on the left side, the grid-like elements are a lot of individual resistors that are used when balancing the battery pack using a passive balancing scheme, where excess energy in some cells is dissipated as heat through these resistors, and that heat must be removed through the thermal paste, through the casing of the battery management system, using the thermal management system of the vehicle. The example battery management system on the previous slide was from a vehicle application, but regardless of what the application happens to be, the battery management system has a few different priorities. The first priority is, of course, safety. A battery management system first and foremost is designed to protect the safety of the human operator of the host application. So the battery management system must detect unsafe operating conditions and respond to those in some way. In some applications, the battery management system is not given the authority to take action on its own, so in that case it must recommend certain actions to the host application that it can take instead to perhaps turn off the battery system and shut it down. The second priority of a battery management system is to protect the battery pack itself. This is especially important if the host application fails in some way and is beginning to cause abuse to the battery pack. In many cases, the battery pack has some authority to detect these conditions and to disconnect from the load if it is sensing some abuse that would cause damage to the battery pack, and especially if it's sensing some abuse that would cause a safety hazard instead. A third priority of a battery management system is to prolong the life of the battery as long as possible under normal operating conditions. And this is in a non-abuse situation when the host application is correctly following all the directives that the battery management system gives. We want to make sure that we give those directives in such a way that we maximize performance in some sense, but we also maximize the life. And we do this generally by informing the host application what is the maximum power that can be drawn from the battery pack or that can be sunk by the battery pack at any point in time over some horizon, some time horizon. Another priority is to maintain the battery pack in a state in which the battery pack is able to fulfill all of its functional design requirements. What do I mean? In some applications, like an automotive application, it may be a requirement that under every circumstance I retain enough reserve in my battery pack that I can always accomplish some acceleration event for a short period of time, or some braking event for a short period of time. So in other words, I can give some amount of power or sink some amount of power for a safety reason. In that case, I must make sure that the state of charge of each of the cells does not get too high so that I can always accept some charge, or it doesn't get too low so that I can always deliver some charge to the load. So in those cases, the battery management system will not give permission to the host application to discharge the battery pack beyond some point or charge beyond some point. And the final design priority is performance. For the battery management system to inform the host application how to make the best use of the battery pack right now. And I might not be near any of the major limits of the battery pack where it might be close to overcharge or over discharge, but I might still want to know what is the best way to use the battery pack so that I prolong the life and get the most performance possible. And we do this usually again by informing the host application what the power limits are right now, and sometimes also how to charge the battery pack, what is the best profile of charging power versus time to charge this battery pack in a way that extends life but charges quickly. In order to achieve these priorities, the battery management system must be connected to all of the internal battery pack components to be able to sense and understand what is happening inside of the battery pack. And it must also be connected to the host application to be able to communicate with that application to give its recommendations on how the battery pack should be used. And the diagram on the right of this slide shows this in a block diagram kind of sense. The cells of the battery pack are shown as blue, and they're drawn as being connected in series with one another using thick lines to represent the high power primary high current connecting path of the battery. And these high power lines are connected to the host application load through devices called contactors, which we will study in more detail later on. But you can think of the contactor as being a switch, an on-off switch that either connects the high voltage, high power battery pack to the load or disconnects it from the load under software control. The same unit that controls the contactors often does all of the high current and high voltage monitoring of the battery pack. And we can also see that the battery management system must be connected to the individual cells in the sense that it must be able to measure all of the cell voltages and perhaps even all of the cell temperatures. The battery management system is further connected to the thermal management system, the cooling system usually inside the battery pack. And so everything that you see inside of the yellow rectangle in the diagram is typically contained inside the enclosure, the physical enclosure of the battery pack. Outside of this enclosure, you can see the host application with which the battery management system must constantly be in communication in order to understand the requirements of the host application and in order to convey the limits of the battery pack at this point in time. So when we think about how to achieve these priorities, we can divide the functionality of the battery management system into a number of major categories, and I will outline 5 major categories. And for the remainder of this lesson, I will simply identify what those 5 categories happen to be, and then we will spend the remaining part of this week and all of next week looking at these 5 functional categories in more detail. The first requirement that we look at has to do with sensing and high voltage control. The battery management system must be able to measure all of the voltages of every cell in the battery pack, and it must be able to measure the overall battery pack current and different temperatures inside the battery pack as well. In terms of control, I must be able to control the contactors that connect the battery pack to the load and disconnect it from the load. In order to do that, we have to be able to perform an operation called pre-charging that you will learn about as well. We must be able to detect when there's a ground fault or an isolation fault between the battery pack and some point that should not be electrically connected but might be under some extreme conditions. And the battery management system must also be able to control the thermal management system. The second aspect of functionality that we will look at has to do with protection. In this case, we're thinking primarily of how do we protect the battery pack itself, how do we protect the battery pack against over-discharge, and how do we protect it against overcharge, and how do we protect against excessive electrical current, and how about a short circuit or extreme temperatures. The third area of functionality has to do with interface, and under this category we think about some of the requirements of the host application and how those rely on information that are known inside the battery pack. So these might have to do with computing remaining range in an electric vehicle. And we certainly need to be able to communicate with the host application itself, and in many applications it's also important to create within the battery pack some kind of a permanent record or permanent log of different conditions and have maybe a separate interface for diagnostics purposes as well. The fourth basic area of functionality has to do with performance management of the battery pack. And this is where we will spend almost all of our time in this specialization, learning how to accomplish the requirements of performance management. This has to do with being able to estimate the state of charge of the battery cells, and estimating power limits and how much energy is available, and how to do the balancing or the equalization of the cells in the battery pack. The fifth and final area of BMS functionality has to do with diagnostics. This has to do with detecting abuse of the battery pack by the host application. It has to do with determining the state of health of the battery cells under either normal or abuse conditions. And in some cases, it also has to do with estimating the present state of life and predicting from that perhaps how much future life we expect the battery pack to deliver before the battery pack must be replaced and recycled. As we think of these 5 major aspects of functionality that are required really in any battery management system, it turns out that some applications find these requirements more important than other applications. In some applications, maybe we don't even implement all of these features because we determine that they are not critical. In most cases, the question regarding when to implement a feature or not, and how much effort we put in to implementing that feature very, very well or not, has to do with how expensive it is to do so. If there were no cost associated with implementing all of these features using the best technology available, then of course we would do that. But there is a cost associated with each one of these features, and so we must make a decision. Is this cost really necessary in this application? So I have a rule of thumb to propose to you. If you are not familiar with the term, a rule of thumb is a broadly applicable principle that is developed by experience. This is not something that we can derive with math. This is more experiential and a little bit more ad hoc. It's not always true, but it's true often enough that it can be a guiding principle unless we have some more detailed analysis that contradicts the rule of thumb. So the rule of thumb I propose in this case is the following. Your battery is cheap enough, it is inexpensive enough if you cannot remember the last time that you replaced it. So for example, for my television remote control, it's operated using disposable batteries. And a few times a year these batteries wear out and I must recycle the old ones and replace the battery cells with new ones. And if these batteries were very, very expensive, then I would remember with perfect precision the date and time when I went to the store and purchased a new battery pack, because it would be just nagging at the back of my brain at how much I spent to replace the battery and how I could have used that money for something that was more important to me, and how upset I am that I had to replace the battery. But it turns out I don't remember the last time I replaced the batteries in my TV remote control. And so by this rule of thumb, then that must mean that the financial investment in these batteries was low enough that any kind of more advanced circuitry in my television remote control that would have cost more money would not really have been worth it. So the battery must have been cheap enough. But think about the battery in an electric vehicle. The battery in this electric vehicle will cost thousands of dollars or thousands of euros to replace. So you know that if I had to replace the battery pack in my electric vehicle, I would remember for a very long time the exact date that I replaced the battery and the exact amount that I paid to do so. And it may turn out that I would never purchase that vehicle again or anything like that vehicle because I was just so upset by it. What do we learn from this rule of thumb? We learn that inexpensive batteries don't need to last very long, but that large battery packs or expensive batteries need to last as long as physically possible. So large battery packs represent a greater investment by the consumer, and they motivate better battery management, even if it costs more to implement that better battery management. This specialization is really focused on large applications with large battery packs. for example, vehicle applications or maybe grid applications. And the methods that we discuss are very general, and they also apply to consumer electronics, but you have to make the decision of when does the cost of implementing a sophisticated battery management system with sophisticated algorithms, when is that cost okay? When is the battery pack so expensive that I can justify this additional cost? And honestly, the cost isn't that much more than you would using a simpler approach, but there is some cost. And even for the consumer electronics, many mobile phones nowadays have non-user replaceable batteries in them. So that means that in order to replace the battery, you have to make an appointment with some store, and you must take your mobile phone to the store physically, and you must wait while they replace it and so forth. So there's a big opportunity cost in terms of time and even in terms of money to do so. So even for a fairly small battery pack, you might want to implement the best battery management that you can in order to extend that battery pack's life as long as possible, to have the greatest consumer acceptance possible, because that's what's going to drive future sales and reviews and so forth. So in this specialization, we will spend the majority of our time investigating fairly sophisticated methods that work well in any scenario. The sophisticated methods may require maybe some more expensive sensors and maybe some more expensive processors than some less sophisticated methods. So you may not be able to justify the methods economically in every case. We will spend a little bit of time looking at less sophisticated methods, and that will allow you to perhaps implement both of them in simulation or even in a prototype to see which one works best for you, which is the best trade-off. And in the end, only you can make the design decision for your particular application as to which is the best method to use. But you're going to see that in most cases, inexpensive electronics and inexpensive processors only allow for very poor battery management. And if you were to spend just a little bit more on electronics and a little bit more for a better processor, you can build a much better battery management system that can extend battery pack life and can enhance safety. So that brings us to the end of this lesson, where you've learned that a battery management system is an embedded system that protects the safety of the host application operator. It protects the battery from abuse. It prolongs the battery's life. It maintains the battery in a functional state, and it informs the host application regarding how to make best use of the battery pack at this present point in time. In order to achieve these priorities, we can come up with a list of battery management system functional requirements and place these lists into different categories. And the categories that we will look at this week and next are the following 5. The first that we will look at for the remainder of this week has to do with battery management system sensing and high voltage control. Next week we begin by looking at protection. Then we look at interface, then at performance management, and finally at diagnostics. We noted that there are different levels of sophistication in how a battery management system works, and not every battery management system will implement all of the features that we talk about, but our focus is going to be on advanced methods that might have a higher cost but give better results in most cases. And based on what you learn, you will be able to make informed design decisions in your own application as to which features you implement and how to do so. So that brings us to the end of this lesson. As we continue this week again, we're going to be looking primarily at high voltage sensing and control. But before we do that, there will be one additional lesson where we talk about the design of the battery pack itself and how the cells are organized into a battery pack, and what we can infer from that design into how to design a battery management system as well. In the previous lecture topic, you learned the 5 major requirements of a battery management system. And before we continue by looking at how a battery management system will meet these 5 requirements, I'd like to spend a little bit of time talking about the principle of modular design for a battery pack and how that modular battery pack design also informs and suggests a modular design for the battery management system itself. Since we're looking primarily at battery packs and battery management systems for large applications, these will usually involve batteries from which there will be a high power demand. And we know that power is equal to voltage multiplied by current, so a high power battery must deliver either high voltage or high current, or both. When we think about how to meet a high power demand, the first thing we could think about is by maximizing the voltage of the battery pack. But we find out that chemistry of individual battery cells is going to limit the maximum voltage of one cell. For example, most lithium-ion battery cells operate in a voltage range between about 3 and 4 volts, give or take. So if we require a battery pack of higher voltage, then we can accomplish that only by connecting many cells in series. And when we do so, the pack voltage is equal to the sum of the voltages of the cells connected in series. An approximate analysis would be to take the nominal voltage of one of the cells and multiply by the number of cells in series to get a nominal battery pack voltage by that. We might also consider trying to maximize the amount of current that we get from a battery pack. When we do, we find that how a particular cell is constructed places some limits on the amount of current that we can extract from that cell or put into that cell. But we also know that if we put cells in parallel, the battery pack current is divided between those parallel cells, and so that the overall pack current can be much higher even for a limited amount of cell current. And we can approximate the amount of current that we can get from a battery pack as the number of cells in parallel multiplied by the amount of current that we could extract from any particular cell. We might also be interested in thinking about the capacity of a battery pack in ampere hours. If all of the cells have equal capacity, then the capacity of the battery pack is equal to the number of cells connected in parallel multiplied by the capacity of any individual cell. And so from this, we can compute a rough but a pretty good estimate, pretty good approximation of the total pack energy and total pack power. The pack energy is equal to the cell energy multiplied by the number of cells. The cell energy is approximately equal to the cell capacity multiplied by the cell nominal voltage. So if we have NS cells connected in series and NP cells connected in parallel, the overall energy is NS multiplied by NP multiplied by cell capacity multiplied by cell nominal voltage. The individual cell power is equal to the maximum cell current multiplied by the nominal cell voltage. So the pack power is equal then to the number of cells multiplying that cell power, or NS multiplied by NP multiplied by the maximum cell current multiplied by the cell nominal voltage, at least to a first order approximation, and we'll learn more exact methods throughout this specialization. But from this approximate analysis, we can conclude that in order to meet certain energy or power requirements in a battery pack, the product of the number of cells in series and the number of cells in parallel must meet some criteria, but actually that the individual values of NS and NP are quite flexible. For example, we might find that the product for some application must be 12. In that case, NS might be 12 and NP might be 1. Or NS might be 1 and NP might be 12. Or one of them might be 3 and the other 4. Or one of them might be 2 and the other 6. So from an energy and power perspective, we have a lot of flexibility in how we choose the number of cells in series and how we choose the number of cells in parallel in order to meet these requirements. So how do we choose them? Well, the choice is usually made by economic factors and by safety factors. For safety, we usually want the overall battery pack voltage to be less than about 100 volts DC. And this factor turns out to be a little bit arbitrary. It's possible to have a safety hazard at lower voltages, or still even to be relatively safe at higher voltage, depending on the environmental conditions. So there are different professional and standards associations that come up with slightly different answers as to what is a safe DC voltage. For example, the National Fire Protection Association, the NFPA, historically had a maximum voltage limit of 50 volts DC before considering the battery to be a safety hazard, and more recently they have raised that value to 100 volts DC. Automotive manufacturers tend to be very conservative, and so they prefer to have voltages of less than 50 volts in any part of the battery pack that might be exposed. Furthermore, at this point in history, the power electronics required for operating at voltages larger than about 600 volts turn out to become quite expensive quite quickly. And for that reason, most applications require a voltage of less than 600 volts, at least at this point in time. So using both of these considerations, we tend to have limits on the number of cells that we would like to stack in series in a battery pack. So let's think about it the other way. Maybe we want low voltage, but we want high current. But there are some difficulties with this approach as well. The problem is that power losses through wiring and other components, but primarily wiring, are proportional to the square of current. That is, if the electrical current passes through wiring that has some resistance R, and the current is I, then the power loss through that wiring is I squared times R. So the bigger current is, the much faster I lose power, I waste power. So for efficiency, we would either need to reduce the resistance of the wiring, or we need to minimize the electrical current. In order to reduce resistance, we need to have far thicker wire, and we have more strands in the wiring. And the thicker it is, the more copper is required, and copper is a relatively expensive element. So we really would prefer to use thin wire, having somewhat higher resistance, in order to save on cost. So this fact tends to put design limits on the number of cells that we wire in parallel. So, as we often find in engineering, there's a design trade-off. We need to make a compromise between the number of cells in series and the number of cells in parallel. A very common solution is to build battery packs from smaller modules of cells. Each one of these modules has a DC voltage that's less than approximately 100 volts in order to maintain safety of a particular module if a technician is opening the module to do some diagnostics or repair. And then you take these modules with individual voltages less than 100 volts and you wire the modules in series to make a higher voltage battery pack. And this approach overall makes the number of cells in series relatively large and the number of cells in parallel relatively small. So there still remains a high voltage hazard when we consider the overall battery pack and not just the module, but this hazard can be managed by proper care when servicing the battery pack and by putting mechanical service disconnects into the design such that when the battery pack housing is opened, it automatically disconnects the modules from each other, and so that there is no voltage inside the battery pack larger than about 100 volts when the case is open. In my experience, this is the most common approach to building a battery pack for vehicle applications. Cells tend to be wired in series more than they're wired in parallel, but there are some reasons why we might consider wiring modules in parallel as well, and we'll talk about that shortly. When we're discussing either modules that are or battery packs that are made from cells where some are in series and some are in parallel, there's a common way of talking about this. Consider the battery pack in the photograph on the right side of this slide. We see that this battery pack is made from 6 individual cells, and that these cells are wired such that pairs of cells make a module, and 3 modules are then connected in series. So overall, the number of cells in parallel is 2, and the number of cells in series, or number of modules in series, is 3. And this particular battery pack would be called a 2P3S pack, 2 cells in parallel and 3 cells in series. As a actual example, I show some photographs of components of a battery pack from a Nissan Leaf electric vehicle. On the left photograph, and on the left side of that photograph, you can see an individual battery cell, and you can see that it's a pouch format cell. And to the right side of that same photograph, you can see a module that is built from that cell. And if you open up that module, you find that it contains 4 cells internally, 2 in series and 2 in parallel. So we would call this a 2S, 2P module. In the right photograph, you see a cutaway of the Nissan Leaf chassis overall. And you can see that the battery pack is mounted underneath the passenger compartment of the vehicle. And the overall battery pack is built from 48 of these modules that we saw in the left photograph. And in this design, some of the modules are stacked vertically and some of them horizontally in this battery area. In addition to safety reasons, there are some other reasons why building a battery pack from smaller modules can make sense. One is that the smaller modules are easier to handle by humans or by robots who are assembling the battery. The individual modules can be tested before integrating them into the pack, and if one module turns out to have a failed component, then it's much less expensive to service that module than it would be to service an entire battery pack. Ideally, the overall battery pack design would be made from multiple instances of the same module design, and ideally the same module could be used in different battery packs for completely different applications. And the reason for this is then that your non-recurring engineering costs, your NRE, to design the battery module would be amortized over many products. The engineers need to design one module one time only and then can reuse that design for many different applications. And it's less expensive than needing to design new modules for every single new application. As we proceed through the specialization, we will consider how modular design of battery management systems is done to support a modular design of a battery pack. In particular, we will tend to focus on design extremes, but the methods that you will learn are general and apply to designs even in between these extremes. So suppose that I determine that I need 3 cells in parallel in a battery pack and 96 cells in series overall. I might consider then the design shown in this drawing that you see on the slide. In this drawing, we take 3 individual cells and we join them together in parallel to make a module. And that module we call a parallel cell module, or PCM, because its cells are connected in parallel. And then we take 96 of these PCMs and we connect them in series to make the overall battery pack. One advantage of this approach to a modular design is that we know that battery cells connected in parallel must maintain the same voltage just electrically, physically, because of Kirchhoff's voltage law. So we need to measure only 1 voltage per every 3 cells, which reduces the cost of my voltage sensing and some of the battery management algorithms as well. And for the same reason, the individual cells inside of one of these PCMs will self-equalize or self-balance because they must maintain the same voltage overall. And so for these reasons, it's very common to find battery packs that comprise cells connected physically in parallel before they are connected in series. But we could also consider the opposite design extreme as shown in the second illustration. It has the same number of cells and the same overall general configuration, but they are wired differently. In this case, we take 96 cells and we connect them in series to make one module called a series cell module, or SCM. And then we take 3 of the SCMs and connect them in parallel, but only at the high voltage terminals and not at the individual cell voltage terminals. There turn out to be some additional complexities to this second approach. We are required to measure the voltages of all cells, which is true in any case for lithium-ion battery management systems. But in this case, I need to measure all 3 times 96 or 288 cell voltages because they could potentially all be different, whereas in the PCM approach, we were guaranteed that each module of 3 cells had the same voltage by Kirchhoff's voltage law. Here in the second approach, they could all be different, and so we must measure them all. Also, in the SEM approach, the individual cells will tend not to balance each other automatically, and so there are some additional requirements for balancing circuitry. So those are two disadvantages of the SEM approach. But there is one very large advantage of the SEM approach in some applications. Suppose we want to make a very large electric vehicle, maybe an electric transit bus, or maybe a large piece of heavy equipment like a bulldozer or something like that. If this vehicle must have very long range in some use cases, but relatively short range in other use cases, if I put a very large battery pack to satisfy the most difficult use case, then I've really over-designed for the simpler, lighter use case. And it would be nice to have battery packs of different sizes that I could put in a vehicle for the different use cases. But using the PCM approach, that's really not a feasible thing to do. But if I build a modular battery pack out of SCMs, then that allows me to have the same overall battery bus voltage with different capacities depending on how many SCMs I install in the application. For relatively low range, I might use one SCM and have a certain voltage. For much higher demand applications, I might insert 2 or 3 or more SCMs, and I have exactly the same overall bus voltage. I just am able to draw more current from it so I can drive bigger motors or bigger loads. And that means that the design of everything outside the battery pack is common, and I just plug in a certain number of SCMs, however many I need. So there's no additional design for a low capacity application versus a high capacity application. It's simply a matter of how many of these modules the consumer decides to purchase and install, and that can be a huge advantage. From our perspective in this specialization, it's possible to design battery packs and battery management systems for either one of these design extremes. And in fact, most battery packs are some combination, some compromise between these extremes. For example, we might build a battery pack from 18-cell 3P6S modules. The module and power energy are then approximately 18 times that of a single cell. Turns out to be not exactly that in practice, and we'll talk more about that later on. But if I do one of these modules with 3 cells in parallel and 6 cells in series, and then connect 16 modules in series, I come up with the overall design requirements of the application. And I meet safety limits of the overall module voltage and so forth. Well, just as I can build battery packs out of modules, I can also build battery management system electronics using a modular approach. So a modular battery pack suggests using a hierarchical master-slave battery management system design as well, and we'll talk about that on this slide and in the following slides. For example, we might have some of the electronics that are dedicated most directly to managing individual cells that are located inside of the module of cells that they manage. This design approach minimizes the wiring and the connections and the wiring losses in the overall battery pack. We would call the electronics connected directly to the cells a slave BMS. And the slave BMS has all of the electronics for measuring voltages, for measuring temperatures, and for balancing the individual cells. There's commonly a single master unit for every battery pack, and the master unit does the supervisory control of everything overall. It's directly connected to the circuitry that manages and measures the overall battery pack current and opens and closes the contactors. The master unit communicates with all of the slaves, and it can do this using a daisy chain architecture like the one drawn in the illustration on this slide. And in that case, the master talks to the first slave, and the first slave talks to the second slave, and the second slave talks to the third slave, and any response goes from one slave to the other, and finally back to the master. So there's one single bus on which everything is connected in a daisy chain kind of way. Or the master can communicate with all the slave units using a star architecture where the master is connected in kind of directly to every single slave. And there's different approaches as well. In order to reduce wiring, some kind of a bus architecture or a daisy chain architecture tends to be the most popular in my experience. In a master-slave design, the slave has certain responsibilities, and the photograph on the slide shows an example that is a demonstration board that linear technology has made in the past to allow designers to experiment with voltage measurement using their 6804 part, and now it's marketed under Analog Devices now that analog and linear have merged. This is a good example of a slave design, and you can look this up on the internet by going to the website for the 6804 part and looking up this demonstration board. It also has schematics and sample code and things like that that you can work with. Even though it's a good example, it actually implements some functionality that not every slave needs to implement in practice, and so the features of this demo board could be made smaller in a physical design. One of the principal requirements of the slave board is to be able to measure the voltage of every cell in the module, and the connector on the top of the board in the photograph connects to the wiring harness that connects to each of the individual cells in the module for this purpose. Another requirement is for the slave to be able to measure temperatures, and again there are capabilities on this example demonstration board to connect to off-board thermistors to be able to do that. From an algorithm point of view, we would love to measure the temperature of every single cell independently, but that requires an enormous amount of temperature sensors and wiring and expense. So instead, most battery packs use only 1 or 2 temperature sensors per module and some kind of an interpolation and extrapolation method to estimate the temperatures of the other cells in the module. The third function of a battery management system slave is to balance the amount of energy stored in every cell in the module. I've already mentioned balancing or equalizing a number of times, but we don't really get to study it in depth until Course 5 in this specialization. But as a preview, each individual battery cell will have slightly different efficiency from one another and slightly different self-discharge rates and so forth. And because of that, it's a requirement that we somehow be able to equalize the level of charge in individual cells, either by draining charge out of cells that have more energy than others, or by moving charge from cells having more energy to other cells that have less energy. This particular slave BMS design performs balancing by connecting a resistor in parallel to a cell that happens to have too much charge. And this extra charge drains through that resistor, and the level of charge then is depleted. And these resistors are on the top portion of this circuit board, all of the parallel components that you see there. A final important design requirement for a BMS slave is to be able to communicate all of the information that it measures and collects back to the master so that the algorithms can process this information in the master unit. And the particular solution shown here uses a serial bus where the master can communicate over a daisy chain bus to the individual addressable components or to all of the components at the same time using a broadcast message. The connectors that allow this are shown at the bottom to the left and to the right of the board, where one side has the connection from the neighboring board into this one, and then the other side connects out to the next neighbor, and finally one of them connects to the master unit. A BMS master has certain responsibilities as well. The master must control the contactors or the high current switches that connect the battery cells, the battery pack, to the load, and also disconnect the battery pack from the load. The photograph on this slide shows a prototype BMS master that we've developed in our research lab, and a production master would be much smaller and much neater than this. You must understand this is for research purposes and has different requirements. But I include this photograph to enable me to point out a few components without too much difficulty. For example, the contactors are these high current switches I've mentioned a few times. In this photo, they are in the top right portion where you see 3 white cylindrical elements. and each one of these is a contactor, and we'll discuss why we need 3 later this week. The master unit must also monitor the battery pack current, and in this particular design there are 2 approaches to do so that our research team can investigate the advantages and disadvantages of the 2 approaches. One is called a current shunt method and the other is an inductive method, and you will learn about those later this week. And both of those are connected to the thick black wiring on the bottom right side of the battery pack. The master is also responsible for measuring isolation between the high voltage battery pack and the chassis of the load, and this is also accomplished in this prototype system, although the electronics to do so are less easy to point out. They're not really obvious from this photograph. The master must communicate with the slaves, and this is done in our solution using a serial communication bus. The master must communicate with the host application, and these are done by, again, some communication buses that are connected with some of the ribbon cables that you see in the photograph toward the left. And finally, the master must control the thermal management system, which in our case is external to this box and must be done using external communication. One important benefit of a master-slave design is that many aspects of the design can be reused from one application to another. We don't have to redesign the electronics starting from nothing every time we build a new battery management system for a new application. So we ask in this slide, is it possible to reuse a slave design? And often the answer is yes, assuming that the electronics used in the slave design are flexible in terms of the number of cells that they monitor, and assuming that the physical size of the slave design is something that can fit into different packages required by different applications. Maybe surprisingly, often the packaging size, the form factor of the slave turns out to be surprisingly important. So even if the overall electronic design can be reused without any changes in different applications, it can be necessary to redesign the circuit board footprint to fit in different applications. If we anticipate that our product will have very high volume production, in that case it might be to our advantage to optimize the slave design for that particular application in order to save some cost in every slave unit that we sell. Also, you know that different lithium-ion cell chemistries have different voltages and different temperature ranges. And for example, a lithium iron phosphate battery cell often has a maximum voltage of around 3.6 volts, whereas others like NMC have maximum voltages around 4.2 volts. So if our electronics are capable of measuring voltages between 0 and say 5 volts, we can accommodate different chemistries by simple software changes that anticipate these different voltage ranges. But if our electronics can only handle a limited range, then we would need to redesign for every different chemistry. It turns out that a 5-volt voltage range is pretty common, and so it's quite easy to design the slave electronics to be able to handle any lithium-ion chemistry presently on the market. So it's often possible to reuse the electronic design for a slave board. So we ask, is it possible to reuse the electronic design for a master board as well for different applications? And it turns out this is often more difficult. The master design needs to be more flexible. Different applications require different numbers of contactors and different types of contactors. And so if we want a universal design, it has to be very flexible as to how many contactors it controls and the ability to produce the different signals required to control those contactors. The current sensing solution that we use in the battery pack also requires some flexibility because we can use fundamentally different approaches to measure the electrical current. So if we require a universal design, then our electronics must be able to control these different types of current sensor. There may be different ways to connect the battery pack charger depending on the application, and there may be different types of thermal management system as well. And so it's possible to reuse the design of a master and a battery management system, but this can be accomplished only by incorporating quite a lot of flexibility using additional analog and inputs and outputs and digital inputs and outputs that might be required in a special purpose design. So we might consider a fairly generic design that we never actually implement, But when we implement a specific design, we take features from that generic design and keep those, the ones that we require, and then we omit the features that we do not require in a particular application. This brings us to the end of this lesson, and to summarize what you've seen, you've learned that high energy and high power battery packs require cells configured both in parallel and in series. Safety and cost limit the number of cells in series, and losses versus cost give us a trade-off for the number of cells in parallel. So the overall design is some kind of an optimization between the factors of safety and cost for the number of cells in series and the losses for the number of cells in parallel. You've learned that battery packs are often built from smaller modules of cells, and this gives advantages with regard to how the modules are handled and how they're tested, and it tends to reduce the non-recurring or NRE engineering costs of building different battery management systems and packs for different applications. The fact that battery packs are often built with a modular design motivates building battery management systems with a modular design also, and it's very common to see some kind of a master-slave topology in a battery management system. The slaves handle the voltage measurement and the temperature measurement and balancing, and the master handles the battery pack current sensing, the isolation sensing, the contactor control, and thermal management. This modular design tends to make it easier to reuse the slave solution in many different applications, but there are greater challenges in reusing the electronic design of the master unless a lot of redundant components are built in to add quite a lot of flexibility that isn't usually needed in any particular application. So in relatively high volume production, it usually makes sense to have a specialized master board for every application, and in some cases it even makes sense to optimize the design of the slave board as well. But we also mentioned that the specialized electronics of a master implementation could be based off of some generic design where you keep only the components from the design that are necessary, and by eliminating the components that are not necessary in that application. So that brings us to the end of this lesson, and we continue by looking at, for the rest of the week, the requirements of a battery management system to be able to measure and control components inside of the overall battery pack. We now begin to look at the 5 requirement areas of a battery management system in more detail. For the remainder of this week, our focus is going to be on requirement number 1, which is sensing and high voltage control. In this lesson, we're going to consider how to measure cell voltage. In a lithium-ion battery pack, it's absolutely critical to measure every single cell's voltage. The difference in voltage between cells is an indicator of their relative balance and an indicator of how much they require equalization, and you will learn more about that in the 5th course in the specialization. Measurements of voltage are also required inputs to most state of charge and state of health estimation algorithms. And further, for safety purposes, it's critical that we know the voltage of every cell. Even if the voltage of a battery pack is within acceptable limits, it's possible for the voltage of individual cells to be outside of acceptable limits. And if I were to overcharge a lithium-ion battery cell by mistake, that can lead to thermal runaway, as shown in the picture to the right. Thermal runaway happens when heat builds up in a cell, which causes the separator to melt, which further causes an internal short circuit that leads to further heat buildup, and this reaction becomes self-sustaining. So in order to guarantee or ensure that we're not overcharging individual cells, we must know the voltage of every cell, and we cannot skip measuring any voltages in a lithium-ion battery pack. So how do we actually measure these voltages? At the most basic level, voltage is measured using a circuit that's known as an analog to digital converter. This technology has a number of commonly seen abbreviations such as ADC or A/D or A2D or A-2-D spelled out. An analog to digital converter samples the voltage level at its input, and it converts that voltage level into a binary pattern of ones and zeros inside of a special purpose integrated circuit or inside of a microcontroller having a built-in ADC. The binary pattern is a digital representation of the voltage that it's measuring. There are several common analog to digital conversion architectures. One is known as a direct conversion or a flash technology. Electronically, this converter uses a bank of comparator circuits that detect whether the input voltage is above or below some internally regulated fixed voltage. So overall, this collection of comparators is used to determine and output the code corresponding to the voltage that's closest to any one of these comparator circuits. This technology is the fastest of all the ADC methods, and it's essentially instantaneous, but it's also the most expensive to implement because of the number of comparators and the number of fixed reference voltages that must be built inside of the converter. The second method for analog to digital conversion relies internally on really the opposite technology, a digital to analog converter. It turns out that it's relatively simple to build a digital to analog converter using some common components, some resistors, and an operational amplifier. There may be better approaches than that, but the main point is that it's simple to build a digital to analog controller, whereas it's more complicated to build an analog to digital converter. So the second analog to digital conversion approach guesses at what the voltage might be, and then outputs a voltage corresponding to that guess using its digital to analog converter. It then uses a single comparator to see whether the voltage produced by the guess is above or below the voltage at the input that it's trying to measure. And by successive approximation, it keeps on this higher-lower guessing until it gets close enough to an estimate of the voltage it's trying to measure. This is a somewhat slow approach because of the need to repeatedly make these guesses, but it's also a very inexpensive approach to implement. The third approach is relatively modern and is adopted in many applications. It's known as a sigma delta or sometimes as a delta sigma approach. The method is somewhat similar to the successive approximation approach in that it guesses what the voltage is and produces a voltage at its output corresponding to that guess. And then it uses a 1-bit flash analog to digital converter, which requires only a single comparator to encode that difference between the approximation and the input it's trying to measure. Usually the delta sigma approach uses very fast sampling in order to come up with sums and differences of the 1-bit ADC in order to very quickly approximate the input signal. So it successively approximates using a flash ADC at a very fast sampler rate, and it's a very popular approach. Regardless of the method used for the ADC, each of these is usually implemented in a specialized integrated circuit, or IC, because of the need to precisely match all of the resistances and capacitances and all of the components involved in making the circuit. And it's easier to match these components on side of an integrated circuit than it is using discrete components in an externally built circuit. It's also common practice to include analog to digital converters built into many microcontrollers, so battery management systems for small battery packs may not need any external circuitry outside of the microcontroller itself for voltage measurement. When you're designing a battery management system and you must select an analog to digital converter for your design, there are several criteria that you must be aware of. The first that we will talk about is the resolution of the converter. The resolution of an analog to digital converter is the smallest change in the input signal that can be measured. It's the step size between consecutive converter output codes in voltage. So consider an analog to digital converter that has m bits at its output. That means it has 2 to the power m output codes. If these codes happen to be distributed evenly over the entire input range, as is most common, then the range of input from the lowest voltage you can measure to the highest voltage you can measure we will call EFSR, where FSR means full scale range. If all of these are evenly distributed, then the resolution is the full scale voltage difference divided by 2 to the power m. For example, let's consider a converter that has input range from 0 volts to 5 volts. Suppose this converter also has 16 bits of precision such that m equals 16. Then the resolution of the converter, which we will call Q, is computed as Q equals 5 volts minus 0 volts, all divided by 2 to the power 16. The answer to this computation is 76 microvolts. The values I use in this example are typical of the better analog to digital converters presently available for battery management systems. So a resolution of 76 microvolts is a common value. The plot on the right illustrates this input-output relationship of an analog to digital converter. On the horizontal axis, you see the actual input voltage that's been normalized by subtracting the minimum voltage of the converter and by dividing by the full scale range of the converter. So that maps the minimum voltage to 0 and the maximum voltage to 1 on this axis. In this example, we're considering a converter that has 3 output bits, or m equals 3, so there are 2 to the m, or 8 possible distinct output codes ranging from 000 all the way up to 111 in binary, and these are shown on the vertical axis. The blue line on the graph shows how the input voltage is converted into an output code. The input range is generally divided into 8 regions, and the converter rounds the input voltage to the closest voltage that is represented by an output code. So slightly negative inputs all the way up to slightly positive inputs get rounded to an output code of 000, and inputs that are a little larger than that get rounded to the code 001 and so forth, and this continues all the way up to the maximum measured voltage. And voltage inputs slightly smaller than the maximum value up to slightly larger to the maximum value are rounded to the output code 111. The input voltage distance between any one of these output codes is the resolution of the converter. So the output code changes anytime the input changes by this resolution voltage. So we could say that the smallest change in output corresponds to a single bit change in the least significant bit position of the output. So the resolution of an analog to digital converter is often called the LSB voltage, which stands for the least significant bit voltage of the converter. Another important consideration when choosing an ADC is its accuracy. Its accuracy has to do with the absolute difference between the reported value of voltage and the true value of voltage. And differences might arise due to several causes. One is due to the inaccuracy of quantization that we saw on the previous slide, the rounding to the nearest output code. This means that there is an unmeasurable part of the true voltage, and that unmeasurable part has magnitude that is less than 1/2 of this resolution. The figure on the right illustrates this quantization error. There's a signal plotted versus time, so the horizontal axis is time, the vertical axis is value in the top plot. In the top plot, the blue line is the input voltage signal, and the red stair-step line corresponds to the voltage codes that are reported by the analog to digital converter. And you can see that the blue line has been rounded in every case to the closest voltage code that is available to the converter. But this rounding does not produce a perfectly accurate result. There's some difference between the quantized signal and the actual input signal. And this difference is called quantization error, and it is drawn in the plot on the bottom. So again, the horizontal axis is time, and the vertical axis now is the quantization error voltage. In this example, the analog to digital converter resolution Q is equal to 1 volt, and so the quantization error is limited to values between plus and minus 1/2 of a volt. A second source of inaccuracy in a converter is known as offset error. Offset is a constant difference, a constant bias between the ideal measured value and the reported measured value that spans the entire measurement range of the converter. Offset errors can be caused by biases in the electronics, either internal or external to the converter. A third source of inaccuracy of the converter is gain error. In the previous slide, we saw the input-output relationship of an ideal conversion process. If the actual conversion process has different slope from what we've seen in this ideal case, that means that there is a gain error in the conversion, and this gain error is usually expressed as a %. Finally, the converter might have a nonlinear error. This is any departure from the actual and the ideal step widths in the conversion, and is often expressed in the number of analog to digital converter counts that are the worst case differences. There are several other considerations that we must take into account when we select an analog to digital converter. One is the effect of temperature. The offset and gain and nonlinear errors that we talked about on the previous slide are all functions of temperature, and we must ensure that our solution provides acceptable performance within the entire range of temperature expected in the application. A second consideration is called timing jitter. Timing jitter is when the absolute time difference between samples made by the converter is not exactly constant. In the second course of the specialization, when we look at more detail on how we make models of lithium-ion battery cells, you will learn that we assume that there's a constant and exactly constant timing between samples we make. These models will degrade in accuracy whenever the timing is not in fact constant, and so we will have some specification on the maximum timing jitter that we will permit in our converter. A third consideration when we're designing using an analog to digital converter is related to something called aliasing. This is not so much a function of the converter itself as it is a function of the fact that we're looking at a continuous time signal at only snapshots at discrete points in time and not at every single possible point in time. In control theory and signal processing theory, there is something known as the Nyquist sampling theorem that states that the sample rate of your conversion process must be at least twice the highest frequency found in the input signal. If we do not meet this criteria, then high-frequency inputs actually turn out to look like low-frequency inputs after they're sampled. The drawing on the slide illustrates this. I draw a blue sinusoidal signal versus time. This sinusoidal signal has a frequency of 5 Hertz. If we sample the signal very quickly, then we will be able to reproduce this 5 Hertz signal with very high fidelity. The Nyquist sampling theory says that the minimum rate at which we can sample the signal if we want to reconstruct it perfectly is 10 Hertz. If we sample more slowly than 10 Hertz, then we have a problem. The yellow boxes on this diagram show what happens if we sample the signal at 7 Hertz instead. And you can see that these yellow boxes correspond exactly to points on that blue signal sampled at a 7 Hertz rate. We don't get enough samples per period if we sample this slowly, though, to be able to state with assurance that the input signal is 5 Hertz. In fact, it looks to us as if the input signal might be 2 Hertz instead. You see the red dotted line on this graph is a 2 Hertz sinusoid, and it passes exactly through the same yellow markers that were created by sampling the 5 Hertz signal. So therefore, the actual 5 Hertz signal is masquerading in our samples as a 2 Hertz signal. It's aliasing as a 2 Hertz signal, and that's why we call this phenomenon aliasing. One factor we have to our advantage when we're designing a sample rate is that battery cells have long time constants and they're quite slow devices. And that means that we usually don't need to sample the input voltages at a very high rate due to the dynamics of the battery cells themselves. However, it might be more important to sample the input voltage quickly if the external load has some very fast time constants. In an automotive application, for example, the battery pack is connected to a device called an inverter that drives the motor, and the inverter has power electronics inside of it that often have switching frequencies in the tens of kilohertz, and this switching can cause noise at those frequencies on this measured battery voltage. So by sampling more quickly than the battery dynamics themselves might dictate we need to, our algorithms for battery management may be able to help mitigate the effects of noise from the inverter and still provide good estimates of state of charge and state of health and so forth. Because high-power battery packs usually comprise many battery cells in series, it's not efficient to use discrete analog to digital components to measure all of the voltages in all of the cells. Instead, different manufacturers have created integrated circuits or chipsets for the specific purpose of aiding high-voltage battery management system design. These relatively low-cost measurement chips are used in modules or slave units close to the battery cells, and these measurement chips do not have any significant processing on board. Instead, they make the voltage measurements and they transmit those voltage measurements to a master unit, and the master unit does all of the processing for state of charge and state of health estimation and so forth. An advantage to delegating this analog to digital conversion task to specialized chipsets is that the integrated circuits can then be designed to implement the very difficult task of highly accurate voltage sensing with high common mode rejection, with fast response in environments that often have high electromagnetic interference or EMI, perhaps even high heat and high vibration. These chips are also often designed so that they can be placed in parallel for redundant and fault-tolerant designs. If different chips that are expected to provide exactly the same voltage measurement in fact produce quite different voltage measurements, then we can conclude that at least one of these chips is faulty. The master unit can then inform the application that there is a fault in the battery management electronics that must be investigated and repaired. There are a number of vendors that make chipsets to perform these voltage measurements, and some examples are Analog Devices and Maxim and Texas Instruments. In order to illustrate some common functionality of these chipsets, I've chosen to talk about the LTC 6811 part. This part was originally designed by Linear Technology Corporation and hence the LTC. But Linear Technology was acquired by Analog Devices, and so this part is now being marketed through Analog Devices. Each of the integrated circuits, each of the 6811 parts is capable of monitoring up to 12 cells in series in a module, and then multiples of this chipset can be placed in series in a daisy chain slave architecture so that overall hundreds of cells in series in a battery pack can be monitored. In order to facilitate the connection of measurements from one slave to another, this chip has built-in isolated electronics for communication between the parts that's also very highly noise immune, that allows for very robust communication in noisy environments. This chip also supports both internal and external cell equalization circuitry, either using passive balancing or connected to an active balancing solution that is also marketed through Analog Devices. The chipset can be powered by the battery module itself, meaning that we don't require an external power source in order to make it function, and that can be a huge advantage. And finally, this chipset is able to measure up to 5 temperatures directly. It can also be configured with some external circuitry to measure more temperatures than that if that's what's required. The illustration on this slide shows a block diagram of the components internal to the 6811 chip. Everything in the orange box corresponds to electronics inside of the chip, and external to the component on the left we see the individual battery cells in series. The resistors and transistors drawn external to the 6811 are for balancing. The transistors inside the 6811 that connect to these external circuits control the balancers. The external cell voltages are connected internally to 2 different multiplexers, analog multiplexers, and each one of these multiplexers is connected to a single sigma delta analog to digital converter. The 12 cells in the battery module then have their voltages measured 2 at a time in parallel, 1 voltage per multiplexer per converter. Therefore, after 6 conversion cycles, all of the cell voltages are measured. The other circuitry that's drawn on this diagram to the top of the 6811 has to do with communication across the isolated daisy chain mechanism between one component and another. Circuitry drawn on the bottom is used for interfacing with some general purpose analog to digital inputs and outputs that can be controlled by the master BMS to measure temperatures or communicate with memories or any other number of functions. The example I presented on the previous slide considers a component available through Analog Devices, but there are other components available on the market. And so how should you choose which component to use in your application? On this slide, I present a few ideas for you to think about when you're making that decision. First, you need to consider how many cells are wired in series in your battery pack. And then you need to compare that against how many cells each integrated circuit from each silicon vendor is able to monitor. If your pack has a lot of cells in series, there can be advantages to choosing a chip that can monitor a lot of cell voltages at the same time. Another consideration is how many cells in total can be monitored using however many number of chips. The example I showed you is for the 6811 part that allows daisy chaining of individual monitoring chips in series so that you can monitor in total hundreds of battery cell voltages. But not every solution from every vendor allows for this. So you need to select a solution that's able to monitor all of the voltages that you require for your battery pack design. A third consideration is whether the chipset supports balancing. It's extremely helpful if you're able to control balancing for individual cells using this chipset instead of having to create additional electronics of your own to do so. Of course, the chipset must have the measurement accuracy that meets the needs of the algorithms you plan to implement in your battery management system. It must also be able to measure a sufficient number of temperatures for inputs to the battery management system algorithms. In order to minimize overall system cost, you may need to minimize the number of wires that are needed to communicate from one integrated circuit to another in between different slave units in the master BMS. And this might seem silly to you if you haven't performed this design before, but wires turn out to be quite expensive, and connectors between different parts in a battery management system further turn out to be quite expensive. And so minimizing the number of wires is a pretty significant concern. Finally, it's important to confirm that this chipset that you've selected is actually available, and what is the cost of the solution per cell in your design. And this might also seem like a silly consideration to you, but in my experience in the past at least, there have been a number of silicon vendors that have announced products, and these products never actually made it to market and were never actually available. So it's important that you talk with a vendor to ensure that the quantity of components that you need will be available to you in a reasonable time. So in summary, in this lesson, you've learned that all battery cell voltages in a lithium-ion battery pack must be monitored continuously during operation. This is done using an analog to digital converter, which is generally built into a special purpose integrated circuit that performs this function. When selecting an analog to digital converter, you must consider the resolution and the accuracy to ensure that both of these meet your design requirements. In order to monitor large battery packs, silicon vendors have produced specialized chipsets to perform all of the functions required. I showed you an example of one of these chipsets, the LTC6811, and you learned some general criteria to consider when selecting a chipset for your own design. And that concludes this particular topic on voltage measurement. The next thing that we're going to look at is how do we measure other quantities in a battery pack for our battery management algorithms. In this lesson, you will learn how a battery management system measures temperature. It turns out that the operational characteristics of battery cells depend very strongly on temperature. For example, the electrical resistance of a battery cell is often quite low at warm temperatures and quite high at cold temperatures. And this means in part that we can get more power out of the battery cell at warm temperatures because of the lower resistance than we can at cold temperatures. And so the BMS needs to know what are the temperatures of its cells in order to be able to compute power limits and also to be able to accurately compute estimates of state of charge and state of health and so forth. It also turns out that the rate of degradation is a strong function of temperature. Battery cells tend to degrade much more rapidly at warm temperatures than they do at cold temperatures. And when the battery management system is controlling the thermal management system, it needs to know the temperatures of the battery cells in order to do so properly. There are exceptions to the general rule that degradation happens most quickly at warm temperatures. For example, at very cold temperatures, we can have extremely rapid degradation if we attempt to charge a battery cell. You will learn more about this in the fourth course in the specialization when you learn about state of health estimation. But you will learn that a phenomenon known as lithium plating can happen, which very quickly degrades the cell and can even result in a safety situation. So it's common not to charge lithium-ion battery cells when the temperature is colder than about 0 degrees Celsius. We also measure temperature because some unexpected change in temperature can indicate a cell failure or some kind of impending safety concern. In an ideal situation, we would measure temperatures internal to every single cell in the battery pack, but that would require a temperature sensor somehow inserted into the packaging, and that's not really feasible. So we have to instead depend on temperature sensors that are somehow mounted external to some of the cells. And also because temperature sensing is relatively expensive, and because temperature differences across a well-designed battery module are relatively small, we often use only a few temperature sensors placed at strategic locations in a battery module or a battery pack, and we use a thermal model we have developed of our battery pack in order to interpolate and extrapolate among these measurements to come up with estimates of the temperatures at every cell location. In the previous lesson, you learned how a battery management system can measure voltage using an analog to digital voltage converter circuit. It turns out that there's no circuit that can directly measure temperature. Instead, somehow we must come up with a means to convert temperature into a voltage that's related to that temperature, and then we measure the voltage using an analog to digital converter. And in this lesson you will learn about two different technologies for measuring temperature. The first is to use a thermocouple. A thermocouple is made from placing two different metals in contact with each other, and these different metals actually form a kind of a miniature battery. A chemical reaction is happening at the surface of this bimetal barrier that produces a small voltage. The voltage that's produced by this thermocouple turns out to vary with temperature in proportion to the temperature difference between the thermocouple and some other reference temperature at a different point in the circuit. Now, this voltage difference is usually very small, in the order of microvolts, but it can be amplified and measured in order to form a voltage that I can convert into a temperature reading. A design challenge when using thermocouples is that we must have a calibrated reference temperature against which we're comparing the measured temperature. And some integrated circuits can generate this reference temperature internally, but otherwise we need to have an externally calibrated temperature source, which is not feasible in a battery management system. So overall, in my opinion, thermocouples are best suited for laboratory testing when we can have all of the necessary temperature references and equipment on hand, but they're not especially well suited for production battery management system designs. But while we're here, I show you a photograph that illustrates a thermocouple-based temperature sensor. The wand on the right of this instrument houses the two different metals inside this long pole, and this is connected through some standard wiring to the packaging on the left, and inside that packaging there are electronics necessary to produce the reference temperature and to amplify the signal and to produce a display of the temperature for the user to observe. An alternate approach to measuring temperature uses a component known as a thermistor. A thermistor is a special kind of resistor. All resistors turn out to have value that changes somewhat with respect to temperature, but most resistor designs are done such that this temperature variation is minimized. A thermistor, on the other hand, is a resistor that has been designed to maximize the change in resistance as a function of temperature. There are two varieties. One is called a negative temperature coefficient, or NTC thermistor, and it has resistance that varies inversely with temperature. The other kind is called a positive temperature coefficient, or PTC thermistor, which has a value that varies proportionally with temperature. So if we were able to measure thermistor resistance, then we could infer from that measured resistance what the temperature must be. But we can't measure resistance directly with an electric circuit. Remember that we can measure only voltage directly using an analog to digital converter. So somehow we must convert that resistance into a voltage that's measurable. And by the way, the photograph on this slide is simply showing a collection of thermistors so that you have some idea what they look like. So I need a way of converting resistance into a measurable voltage, and the most common way of doing this is to use a circuit that's known as a voltage divider circuit. I've drawn a schematic diagram of a voltage divider circuit on this slide, and in this circuit the top resistor labeled R1 has a resistance that is not changing very much with temperature, but the lower resistance labeled R-therm has a value that is designed to change significantly with temperature, and this is the thermistor. The circuit is supplied with a constant known voltage V at the top of the circuit, and the analog to digital converter measures the voltage drop across the thermistor, which is labeled V-therm. When we begin to analyze the circuit, the first thing we do is to compute the current that passes from the voltage source to ground. And our assumption is that the analog to digital converter draws essentially no current, and so we say that the current into that A to D device is 0. So then we can use Ohm's law to say that the current through the two resistors connected in series is equal to the voltage drop across the resistors divided by the overall resistance, or I equals V divided by the sum of the two resistances. Again, by Ohm's law, we know that the voltage drop across the thermistor is equal to the current through that thermistor multiplied by its resistance. So we can combine these two equations to find that the voltage drop across the thermistor is equal to the overall voltage V multiplied by a scale factor. And the scale factor is the thermistor resistance divided by the sum of the two resistances. Now in the circuit, it turns out that there's always going to be current flowing from the voltage source V to ground. And power is being dissipated through this circuit as I squared times R, where I has been computed already and R is the sum of the resistances. And we don't want to, this power is parasitic. We don't want to waste all this power, and so we would like to minimize then the amount of current that flows. So we design the value of R1 to be relatively high in order to minimize the current. But we also have to balance that requirement with the requirement of providing a measurable voltage at the thermistor. So usually the value of R1 is similar to the thermistor resistance at some reference temperature like 25 degrees Celsius. And that's done in order to minimize the overall power loss, but still to provide a measurable voltage in the voltage divider. So our desire is to measure the voltage across the thermistor and to use that voltage to be able to calculate the resistance of the thermistor. So we take the expression on the previous slide and we rearrange it to solve for the resistance of the thermistor. When we do so, we find that the thermistor resistance is equal to R1 multiplied by a scale factor, and the scale factor is the voltage drop across the thermistor divided by the difference between the source voltage and the thermistor voltage. The data sheet that documents the specifications of the thermistor that you purchase will give you an equation that relates the resistance of the component to temperature. And this turns out often to be an exponential relationship like the one shown on this slide. In this equation, we see that the thermistor resistance is equal to some reference resistance R0, which is measured at some reference temperature like 25 degrees Celsius. And this reference resistance R0 multiplies an exponential term, and the exponential term has an argument that is related to the differences in reciprocals between the measured temperature and this reference temperature, where this difference is scaled by a device parameter beta. This equation is really fundamentally designed to work with temperatures in Kelvin, and so the 273.15 factors converts Celsius temperatures into Kelvin temperatures for this equation to work properly. Let's look at an example of how this might work out in practice. In this example, I'm using a negative temperature coefficient, or NTC device, that has a value of R0 equal to 100 kiloohms measured at the reference temperature of 25 degrees Celsius, and it has a beta parameter equal to 4,282. The plot that you see on the slide shows resistance of the thermistor itself as a function of temperature. And you see that there's a very wide range from over 2 megaohms at its highest point to essentially no resistance as the temperature varies. In the second plot, I show what the measured voltage would be at the analog to digital converter if we use the thermistor in a voltage divider circuit where the R1 value is equal to 100 kiloohms and the supplied voltage is equal to 5 volts. At extremely low temperatures, the thermistor resistance is very high, and essentially all of the voltage from the 5 volt source is dropped across the thermistor and none across R1, and so we measure a voltage that's close to 5 volts. On the other extreme, at very warm temperatures, the thermistor resistance is essentially zero, and so the voltage drop across the thermistor is essentially zero, and so most of the voltage will be dropped across R1, and so the measured voltage across the thermistor is essentially 0 volts. At the reference temperature of 25 degrees Celsius, the value of R1 and the thermistor resistance are equal, so half of the voltage is dropped across each of the components, and so the measured voltage is half of 5 volts, or 2.5 volts. And overall, the profile of measured voltage versus temperature has a sigmoidal shape. And when we plot it, we see that there's a fairly linear region between about 0 degrees and 50 degrees, and outside of that linear region it does tend to curve more. So some very simplified designs rely on this linear shape if they don't require a very accurate temperature sensor, and they just fit a straight line to the central region. But if I want a more accurate calibration, I simply do a table lookup of the actual design values, which is also quite easy to do. So for this more accurate temperature measurement, we can invert the relationship in the second plot to compute the relationship shown in the plot on the right, the third plot. All I've done is to interchange the temperature and the measured voltage axes and replot the data that way. And this again gives me a lookup table, so I can store a vector of measured voltages and a corresponding vector of temperatures, and anytime I read a voltage, I can look in that voltage vector and find the closest value and then look up the corresponding temperature. So for example, if we measured 4.0 volts, we can go to the lookup table and find 4.0 volts in the temperature, in the voltage axis rather, and then we draw this vertical line and notice where it encounters the blue line, and then the value of the blue line by drawing a horizontal line there is the point in temperature that we're measuring. So lookup tables are extremely efficient in terms of computation, even though they do require some memory to store all of these values. So to summarize this lesson, you've learned that we must measure and control cell temperature to preserve battery health and to provide critical information to our algorithms that compute power and state of charge and state of health and so forth. It's generally too expensive to measure the temperature of every individual cell in a battery pack, so instead we measure several temperatures inside of a module or inside of a pack using sensors placed at strategic locations, and then we use some kind of interpolation and or extrapolation scheme to estimate what the temperatures must be for every cell in the battery pack. There is no mechanism that allows us to measure temperature directly, so instead we must somehow convert temperature into a voltage, and then we must measure that voltage using an analog to digital converter. And you learned about two different approaches. We can use a thermocouple with an amplifier, but there are some drawbacks to doing that involves complexity and expense. The other method would be to use a thermistor with a voltage divider circuit instead, and that's what's most commonly done. So that brings us to the end of this lesson on how to measure temperature. And as we continue on in this week, the next thing that we're going to look at then is how do we measure electrical current? And that's the topic of the next lesson. In the previous lessons, you've learned how a battery management system can measure voltage and temperature, and now in this lesson, you're going to learn how a battery management system can measure electrical current. Battery pack electrical current measurements are required in order to monitor battery pack safety, in order to ensure that excessive amounts of current are not flowing. They're required in order to log abuse conditions. And in addition, they're required by most state of charge and state of health algorithms, including those that you will learn about in the upcoming courses in this specialization. But remember that we cannot measure any physical quantity directly except for voltage. So we cannot measure electrical current directly. Somehow instead we must convert the current into a voltage signal and then measure that voltage signal using an analog to digital converter, and then from that reading infer what the current must have been. There are two basic approaches to doing this. The first approach is to use a resistive shunt, and the second approach uses a Hall effect sensor, and you will learn about both of those approaches in this lesson. First, we look at the current shunt sensor. A shunt is a low-valued but very high-precision calibrated resistance that's placed in series with the battery cells and the load that they power. So usually at the negative terminal of the battery pack, between the negative of the battery and the negative of the load. The photograph on the slide shows a current sensing shunt. The large screw terminals on the top are connected, one to the battery pack negative terminal and the other one to the load negative terminal. And all of the current passing through the battery pack passes through this shunt current sensor. The parallel plates between the two large screw terminals are what form the calibrated resistance. And when current flows through the resistance, Ohm's law tells us that there will be a voltage drop such that the current is equal to the voltage divided by the known shunt resistance. If we were to use a large resistance, then we would also, however, waste a lot of power with this device as heat, and that's not our desire. So we want to use a very small resistance. But when we use a very small resistance, the voltage drop across the shunt ends up being very small also. And so the voltage difference across the shunt sensor must be amplified before we sense it, and the calculation for current must be adjusted accordingly by dividing the measured voltage by the amplification factor before computing what the current must be. If we look at the shunt device in more detail, we notice that there are in fact 4 different connection terminals. As we talked about on the last slide, the 2 terminals on the top are connected, one to the battery pack and the other to the load, and that the overall battery pack current flows through those 2 large terminals and through the shunt device itself. All of this battery pack current passing through these parallel plates produces the voltage drop that we want to measure, and the resistance that's actually calibrated on this device is the value between the 2 small screw terminals, not between the 2 large screw terminals. And the sensing leads that we use to measure the shunt voltage are therefore connected to the small terminals and not to the large terminals. And so the large terminals don't have a calibrated resistance themselves, and the connection resistance of whatever connecting devices we put on them to connect to the battery pack and the load also don't have calibrated resistance. And that could be quite significant. It can quite significantly bias our calculations if we were to measure across the large terminals. So we measure across the small terminals instead. And it's very important to connect a shunt this way. This connection style is called a Kelvin connection, and it enables what is known as 4-wire voltage measurement. We assume that essentially no current is drawn by the analog to digital converter that's connected to the small screw terminals, and therefore the wiring between the A to D and the small screw terminals has no voltage drop over it, and so we are truly measuring the voltage drop across only that calibrated resistance. If we were instead to connect the voltage sensing wires to the large terminals, we would be measuring the voltage drop across the calibrated resistance plus the voltage drop across the screw terminals in that connection. And a large current flows through those, and so there would be a significant I times R voltage change across the large terminals that would really interfere with us being able to get good measurements of what current is. We would make serious miscalculations. So to summarize the current sensor using shunt sensing mechanism before we look at the Hall effect sensor, I'll make a few comments here. So you've seen that in order to use a shunt sensor, we absolutely must use this 4-wire connection, otherwise our measurements will all be wrong. When we compare this method of sensing to the Hall effect method that we're going to talk about very soon, we'll find that an advantage to using the shunt sensor is that there is no built-in offset at zero current using a shunt. In other words, the voltage drop at zero current is I times R, or 0 volts. And so a shunt sensor is good to avoid drift in certain kinds of state of charge estimation algorithms. In particular, in the third course in the specialization, you'll see that there's a simple method to estimate state of charge that's called Coulomb counting. And what it does is to integrate the current sensor measurements. But if there's a constant offset in the current sensor measurement, I'll be integrating that offset over time, and I will get ever-increasing estimation error. And that's, of course, really bad. So we desire a current sensor that has no offset, if at all possible, and the current shunt, in fact, does not have offset, so that's really good. But we do still have to be careful, because even though the shunt has no built-in offset, the amplifying circuitry and the analog to digital conversion circuitry may have some offset, so we still may need to calibrate some offset out. There's just going to be relatively little of it to calibrate out. When we compare this type of current sensor to a Hall effect, it also has a disadvantage in that the shunt is not isolated electrically from the battery pack. And in many times this is a requirement that the battery management system electronics be electrically isolated from the battery that they're managing. And if that's the case in your particular application, you will require extra circuitry to isolate this current shunt from your BMS electronics. So an example is an automotive application where traditionally the BMS is powered by the 12-volt lead-acid battery in the vehicle, and the other electronics, the motors and so forth, are powered by the high-voltage battery pack. And so if there was a loss of electrical isolation between the BMS and the high-voltage battery pack, that means that there is a loss of isolation between the 12-volt system and the high-voltage battery pack. And if you know how standard automobiles are constructed, the 12-volt system is actually physically connected to the chassis of the vehicle. And so if I don't have isolation between the high voltage and the 12-volt, I also don't have isolation between the high voltage and the chassis. And so that's a safety consideration, because someone touching the chassis could shock themselves, and we don't want that. And so this isolation is a requirement that's not built in, that we would have to add. And a design consideration when using a shunt is that we desire to have a very low shunt resistance in order to minimize power losses. But regardless of whatever resistance we end up choosing, there will be some power loss. And this power loss will result in heat buildup, and the heat buildup must somehow be removed by our thermal management system. So it places additional load on that system. Finally, you've seen that we need to amplify the shunt signal in order to get a measurable voltage. And anytime there's amplification, that introduces the possibility of amplifying random electrical noise in the circuit. And therefore, it can be important to shield the wiring between the shunt sensor and the amplifier from this electromagnetic interference. Now we look at the Hall effect current sensing method instead. This is based on a principle from electromagnetics, where we find that if a coil of insulated wire is wrapped around a primary current carrying wire, that this primary current carrying wire induces an electrical current in this coil. Even though there's no electrical connection whatsoever, it's done through the electromagnetic fields that are built up when current is flowing through a wire. Hall effect sensors measure this induced current in the secondary coil and use that to infer what the amount of current passing through the primary wire must have been. So in the photograph on the right-hand side of this slide, I show an example of a Hall effect current sensor, and I hope you can see there's a large oval opening in this sensor toward the upper right-hand side. And the large current carrying conductor would be inserted through this opening, and there's no electrical connection whatsoever. We just pass the wire through the opening. And inside of this packaging for the Hall effect sensor, there's actually a coil that wraps around that opening. And there's further electronics inside of the package that measure the current going through this coil and produce an output voltage that's somehow proportional to that current to be measured by the battery management system. And that's illustrated schematically on the right. At the bottom you can see the current carrying wire going through the center of the coil, but it's not electrically connected, and the coil wrapped around that secondary. The voltage across that coil, or the current through that coil rather, is measured and is conditioned and makes a voltage proportional to that current for the battery management system to measure as well. We can summarize some of the design considerations for a Hall effect current sensor that we need to think about. One advantage when we use a Hall effect sensor is that it's automatically isolated electrically from the battery pack current because there's no electrical connection whatsoever between the primary current carrying wire and the sensor. So we don't require any isolation circuitry when we're measuring battery pack current. However, anytime we use electromagnetics, there is a physical phenomenon that we can encounter known as hysteresis. And magnetic hysteresis causes the present measured voltage to be a function not only of the present instantaneous current going through the primary, but also somehow a function of past current that went through this primary current carrying wire. So there's a history somehow embedded in the present measurement. And in some cases it's possible to purchase Hall effect sensors that have feedback circuitry that tries to eliminate this history as much as possible to give you as clean a present instantaneous measurement as possible. But no matter how good a job you do with this conditioning circuitry, there will always be some amount of hysteresis in your measurement that you have to deal with. So this hysteresis means that a current reading after charging your battery pack for a while will be different from a current reading after discharging a battery pack for a while, even though the current might be exactly the same at this moment in time. And in particular, if the battery pack is resting and we should be measuring zero current, I will be actually measuring some value above zero or less than zero, depending on whether I've recently been charging or discharging. And that's a problem. If I'm integrating the current sensor in order to provide a state of charge estimate, then I will have this offset that will cause increasing error over time, and that's not desirable. So one possible solution is to measure current from the Hall effect sensor when the battery pack is disconnected from the load and we know that current is zero, and then to use that as our default zero measurement and subtract that value from all future measurements. But unfortunately, this bias is not a static thing. It actually changes with time, and it drifts with time, and it changes with temperature also in often unpredictable ways. So even if we come up with a clever scheme somehow to zero out this offset by subtracting an estimate of the offset, there's always going to be some error in the reported current, some bias in the reported current that changes with time and with temperature. And this causes all kinds of problems with a number of battery management system algorithms, especially state of charge estimation. So if we are to use a Hall effect current sensor, some kind of compensation is necessary. And it's often also necessary to try to estimate the DC bias and to subtract that out from measurements in our algorithms. Because of this additional complexity to the algorithms and the uncertainty that this adds to our estimates, I personally don't prefer Hall effect current sensors, but you will still find them in many commercial products, mostly because their built-in electrical isolation makes them very attractive to electronics designers. So in summary, we must be able to measure battery pack electrical current in order to monitor battery pack safety, in order to log abuse conditions, and in order to inform state of charge and state of health algorithms. You learned about two different methods that might be used. We may either use a current shunt or a Hall effect sensor. Both of these methods have their advantages and disadvantages, and both are actually in common use. And when you're designing your own battery management system, you'll need to evaluate the advantages and disadvantages of both to come up with the correct decision for your own particular design. That brings us to the end of this particular lecture, this lesson topic, and it brings us to the end of our three main sensing requirements of sensing voltage and current and temperature. And from now on, for the rest of the week, we look at some other high voltage measurement and control aspects of measuring isolation and contactor control and thermal management system control as well. And that's what we start to do next. In recent lecture topics, you've learned how a battery management system can sense the physical quantities of voltage and temperature and current that it must know in order to safely operate the battery pack and to execute the algorithms that you'll be learning about later in the specialization. In this lesson, you will learn for the first time about how a battery management system must control something instead of simply measure or sense something. Specifically, you will learn how a battery management system controls its contactors. When a battery pack is not in use, its internal high voltage bus must be completely disconnected from the load at both the positive and the negative terminals, and it does this to prevent a high voltage shock hazard. Now, to be able to disconnect both terminals from the load, we require some kind of an electronically controlled on-off switch that's capable of conducting large levels of current when it's turned on. One of these switches is used to connect the positive terminal of the battery pack to the load, and the other to connect the negative terminal of the battery pack to the load. These switches must be electronically controllable, of course, and a device that can perform this operation is known as a relay, or more often as a contactor when we're using this device to control large amounts of current. And there are some internal differences to how a relay and how a contactor work, but both of them are high current capable devices. They're on-off controlled switches. The photograph on this slide shows an example contactor, and the physical size of the device, to give you some reference, is maybe about the size of your fist, maybe a little smaller than that. The red and the black wires that you see in the photograph are the low voltage, low current wires that control the contactor. The screw terminals on the top are where we connect the high current carrying wires. When we apply a voltage to the red and black wires, that closes the contactor and it makes a connection electrically between those two screw terminals and allows current to flow. When we remove the voltage from the red and black wires, that opens the contactor and it opens up or removes the connection between the screw terminals, and that causes current to stop flowing. When we connect the battery pack to the load, it's not simply a matter of closing both contactors and then operating. We actually have to be quite careful when we connect a battery pack to most loads that we might encounter. And the reason is that many loads have a high capacitance to them. For example, in the vehicle application, the load of the battery pack is the motor controller, otherwise known as an inverter. And this inverter operates semiconductor devices and switches them on and off at very high frequencies, which would tend to put very high transients on this voltage bus, and that can cause damage to the battery pack that we don't desire. And so the inverter also has large capacitors inside of it to smooth out these transients so that when the motor is operating, the battery pack does not experience this high level of noise caused by the load that it's connected to. So that's a good thing, but on the other hand, if I started with a motor controller whose capacitors were initially at 0 volts charge, and I wanted to connect a high voltage battery pack, and I connected both the positive and the negative terminals at the same time. What would happen would instantly an enormous amount of current would flow out of the battery pack to try to charge the capacitors in this load. This enormous amount of electrical current has the potential to cause arcing inside the contactors and to weld them closed, and after that point they would never be able to physically be opened again. They'd be physically damaged, and it could even blow a fuse in our battery management system. So any practical battery management system for a high power application uses not 2 contactors but 3, where the third contactor is known as a pre-charge contactor. And in this lesson, you will learn how the contactors are controlled when the battery pack needs to connect to the load, and how they are controlled when the battery pack disconnects from its load. The drawing on this slide shows how a battery pack is connected to the external bus and the location of the 3 contactors in this overall schematic. To the far left, you can see the series connected battery stack. And I've drawn a fuse in the center of this battery stack so that if the fuse were to blow, the pack would be divided into 2 parts, and the overall pack voltage then would be divided essentially in half. So if a technician were to open up the battery pack, the maximum voltage that could be encountered would be half of the battery pack voltage. So the fuse is placed where it is to minimize the maximum voltage that would be encountered by the technician. The fuse is put there for safety reasons. The red shaded boxes are symbols that depict the contactors, and at the top of each symbol you can see 2 terminals with a thick line drawn above it. In this diagram, none of these thick lines or bars are connected to the terminals, and so all of the contactors are in an open state. When the contactor is in an open state, that means that the left side of the contactor is electrically disconnected from the right side. In each of these contactor symbols, you can also see that there's a coil drawn at the bottom, and this is the control mechanism for the contactor. When the coil is activated, the contactor closes and a connection is made between the high current terminals. When the coil is deactivated, the contactor opens and the high current terminals are then disconnected. The thick lines in the diagram shows the parts of the circuit that are presently activated. And the diagram shows a battery pack at rest. So all of the connectors are open, all of the contactors rather are open, and the only activated connections are to the left of the contactors. The load is completely disconnected from the battery pack at this point. Now, notice that I have activated the left branch of all the contactor coils, but the right branch of only the negative contactor. This connects the negative terminal of the battery pack to the negative terminal of the load. But at this point, the positive terminal of the battery pack is still disconnected from the load. The next step is to close the pre-charge contactor. So far, I have not changed this diagram. To close the pre-charge contactor, I need to activate the right branch of its coil circuit. And when I do that, the contactor closes and a pathway is formed between the positive terminal of the battery and through the pre-charge contactor, through the pre-charge resistor to the positive terminal of the load. So let's do that. At this point, current flows from the battery pack through the pre-charge resistor to the load. The capacitance of this load is able to charge because of this current flowing, but the resistance of the pre-charge resistor limits how quickly we charge that capacitor. And that ensures that the contactors don't fuse, that there's no damage caused to them. The battery pack current is limited by this pre-charge resistor. If all goes according to plan, the capacitive load is quickly charged up and we can move on to the next step. But for fault tolerance, it's important to check to see whether things are going according to plan. So one thing we can do is to monitor the temperature of this pre-charge resistor. And if the temperature becomes too high, then the load may have some short circuit inside of it and may be drawing too much current. So if that's the case, we can deactivate the pre-charge contactor and deactivate the negative contactor and disconnect the battery pack from the load. We can also monitor the bus voltage and the pack voltage. If these voltages do not converge quickly enough to the same value, then again the load may have some kind of a short circuit fault and the pack will disconnect. Or instead of monitoring the load voltage in addition to the battery pack voltage, we can monitor one of the voltages, usually the battery pack voltage, and the load current, which we have to do anyway. So we would then we would consider that the capacitive load was fully charged when the current going to the load was essentially zero. And this might be a better approach since we already have a battery pack current sensor and we're already measuring the battery cell voltages, so we don't need to add an additional sensor to do this. If the pre-charge current does not approach zero quickly enough, the load may have a short circuit and the pack should disconnect. The third step, assuming everything has gone well, is to close the positive contactor. So again, I'm going to redraw the circuit here, and in this case you can see that the positive contactor is closed and that the load is connected directly to the bus at both terminals. The third step is to close the positive contactor. Again, I've redrawn exactly the same picture from the previous slide as a starting point. If we determine that the bus voltage and the pack voltage have become close enough, quickly enough, then we can close the high current pathway. Alternately, if the pre-charge current has approached zero quickly enough, we can close this pathway. We do so by activating the right branch of the coil of the positive contactor. At this point, all three contactors are closed, so the negative terminal of the battery pack is connected directly to the load. The positive terminal of the battery pack is connected through the pre-charge resistor to the load, but it's also connected directly through the positive contactor to the load. And because the positive contactor has essentially no resistance, this pre-charge path, even though it's still active, carries essentially no current. The load is now connected directly to the battery pack through two low resistance contactors for a single low resistance pathway. The final step after the positive contactor is closed is to open the pre-charge contactor. We do this by deactivating the right branch of the coil for the pre-charge contactor. Notice in the diagram the pre-charge pathway is now deactivated, but there's still a low resistance pathway for current to flow from the battery pack to the load. And at this point, the normal pack operation starts. It's interesting to consider what we should do when we're shutting the pack down. How should we disconnect the battery pack from the load? And the answer is not as clear. If the load is actively drawing power from the battery pack and I abruptly disconnect, then arcing might still occur across the contactor as I'm trying to open it up, and that might still weld the terminals together internal to the contactor and cause the contactor to be permanently closed even though I'm trying to open it. So one possibility when shutting the battery pack down is to activate the pre-charge path once again to shut the pack down in the reverse order from which I started it. But again, if current is being actively drawn from the battery pack and I were to disconnect the battery pack in an emergency situation, then there might be more current through the pre-charge resistor than that resistor is rated for. And consequently, this resistor might turn into a fuse and might be destroyed. But remember that the entire reason for requiring the pre-charge circuit in the first place is because the load is often capacitive. That means that the load has some amount of energy stored inside of it. So if all the contactors were simultaneously opened in some kind of an emergency setting, the capacitor in the load stores enough energy that it's likely to supply the load for a period long enough for the contactors to open completely to prevent arcing from happening and to prevent damage. So most likely the battery pack can be disconnected from a capacitive load simply by opening all of the contactors without an elaborate shutdown procedure. To summarize what you've learned in this lesson, you've seen that there is a need to be careful when connecting a battery pack to a load when we're powering the battery pack on. It's very common for the load to be capacitive in nature, and for that kind of scenario, a pre-charge path is needed in order to charge the load somewhat slowly before the main contactor is closed. This imposes a need to be able to measure both the battery pack voltage and the battery bus voltage, or to measure the battery pack voltage and current through the battery pack. And that saves need for additional sensors. And finally, we also discussed a procedure to follow when powering down the load, and that this procedure was maybe not quite as clear as the one to follow when powering up the load, but nonetheless you could experiment with both and see which works best for your application. So that brings us to the end of this lesson on how to turn on your battery pack. With this lesson, we continue to investigate requirement 1 of battery management systems, which have to do with sensing and control. The particular aspect that we are going to look at now has to do with sensing the presence of a ground fault, otherwise known as an isolation fault. The primary concern that we have has to do with safety. We ask the question, is it safe to touch one terminal, external terminal of the battery pack, and the vehicle chassis at the same time? And one possible application has to do with when a vehicle is being serviced. If I open up the hood of the vehicle, as shown in this picture, and if I were to touch one terminal of the battery with one hand and to touch the chassis of the vehicle at the same time with the other hand, would I be safe? Another application would have to do with if I were in an accident and somehow the electronics and the battery pack structure were compromised, would it be safe for an emergency responder to touch the chassis of the vehicle, or you as an occupant, would it be safe for you to touch the chassis as you're trying to exit the vehicle? The high voltage battery should be completely isolated from the chassis, so there should be no problem. And notice that this is quite different from how the 12-volt system is wired in a standard vehicle. In a standard vehicle, the positive terminal from the 12-volt battery is wired independently to everything in the vehicle that requires power. But the ground of the 12-volt battery is wired directly to the chassis. And this is done to eliminate the need for running ground wires to every component in the car. It saves wiring. And it's safe to do so because 12 volts from the 12-volt battery does not have sufficient potential to cause significant injury or harm. It's not safe to do the same thing with a high voltage battery, so neither terminal of the high voltage battery should ever be connected to the chassis of the vehicle. There is a safety standard that dictates the requirement for isolation. The Federal Motor Vehicle Safety Standard, or FMVSS, says that isolation is considered sufficient if less than 2 milliamps of current can flow when I connect the chassis to either the positive terminal directly or to the negative terminal directly using a direct short circuit. This is because it's believed that 2 milliamps of current is less than but close to a lethal threshold. So for worst case analysis, we consider that the resistance of a person might be 0, and if a person were to connect using their body these 2 points, we would want less than 2 milliamps of current to flow. So how to measure isolation? We set up the problem by drawing the schematic diagram shown on the right of this slide. And at the top of the schematic, you can see the high voltage battery and its positive and negative terminals that could be connected to a load. And at the bottom of the schematic, we see the chassis of the vehicle. And ideally, these are completely isolated electrically from each other, no connection whatsoever. I modify the diagram now a little bit to show between the high voltage battery and the chassis I've added 2 voltmeters and 2 resistors. The resistors model the resistance between the negative terminal in the chassis and between the positive terminal in the chassis. These are not physically present. We don't physically add resistors because that would break isolation. These resistors are shown in the circuit to model whatever resistance is actually present, and ideally that resistance is infinite. I also draw these voltmeters, V1 and V2, and we will actually measure these voltages at some point in our algorithm for checking for isolation. Since we wish for both resistances to be infinite, the worst case resistance is going to be the smaller of the two resistors. So we define something called an isolation resistance, Ri, to be the minimum of R1 and R2. And since we require that less than 2 milliamps of current can flow if there's a direct short from one side of the battery to the chassis ground, that means that the remaining resistance must limit this current flow. So by Ohm's law, the isolation resistance must then be greater than the battery voltage divided by 2 milliamps. In other words, it must be greater in magnitude than 500 times VB, of VB is the battery voltage. So our objective is going to be to somehow measure this isolation resistance, the smaller of these two resistances. We don't care about the larger one, we just care about the worst case, smaller one. And to do so, we begin by measuring the two voltages shown in the diagram using a high impedance analog to digital converter that has an internal resistance that's specified usually to be greater than 10 mega ohms. You see, when we're placing these voltmeters in the circuit, technically speaking, we're breaking the isolation that we're looking for. We're making a pathway between one terminal of the battery pack and the chassis of the chassis of the vehicle. But because we specify that the resistance of the voltmeter must be greater than 10 mega ohms, we ensure that less than 2 milliamps of current will flow for most batteries unless the battery voltage is extremely high. And so this is not breaking isolation according to our specification by placing this voltmeter in the circuit. Also notice the polarity indicated on the voltmeters. Both voltages are defined to be positive values, and so when we look at the equations on the upcoming slides, keep that in mind. To continue with the analysis of the circuit, I've first copied the circuit diagram from the previous slide on the top, but I've also redrawn the circuit in a slightly different but equivalent way on the bottom. And if you spend a minute and examine both of these diagrams, you will see that all of the connections are exactly the same, but the diagram on the bottom makes it a little bit more clear that the two resistances form a voltage divider across the battery voltage. Similarly, we see that the sum of V1 plus V2 must be equal to the overall battery voltage. Our objective is to find the smaller of the two resistances, and in a voltage divider, the lesser of the two measured voltages corresponds to the smaller resistor. So if V1 is less than V2, then we must find R1. Otherwise, we must find R2. In the next few slides, we're going to talk about a method that we can follow in order to do this, but before we do so, I first note that we can write that the quotient of V1 divided by R1 is equal to the quotient of V2 over R2. We find this to be true by using Ohm's law and recognizing that I1 must be equal to I2, since that's the only pathway through which current is flowing. And we're going to use these identities in the mathematics we use to solve this problem. We're going to consider two independent cases. In one case, we have determined that V1 is less than V2, and so we must find R1. In the opposite case, we've determined that V2 is less than V1, and therefore we want to find R2. But let's start with the first case. Our next step is to insert a known resistance R0 between the battery and chassis using a transistor switch to close the circuit, as shown in the diagram. So once again, this is going to break strict isolation because we have intentionally made a pathway between the positive terminal and the chassis of the vehicle. However, if we choose this resistor R0 to have a large enough resistance, then we don't actually violate the requirement of less than 2 milliamps of current flowing. So this requires that the resistance R0 be much greater than 500 times the battery voltage. After we've inserted this resistance, we measure the new voltage V2 prime. By Kirchhoff's current law, we know that the current flowing through R1 between the negative terminal of the battery and the chassis must equal the sum of the currents flowing through R2 and through R0 that we've now added to this circuit. So by Ohm's law, the current through R1 is the voltage drop across R1 divided by its resistance. the voltage across R1 is equal to the battery voltage minus this new measured voltage V2 prime. So the current passing through R1 is equal to the battery voltage minus V2 prime, all divided by R1. The current through R2 is equal to its voltage drop divided by its resistance, which is V2 prime divided by R2. The current through R0 is its voltage drop divided by its resistance, or V2 prime divided by R0. Therefore, we have this equation that I've shown that basically says that the current through R1 is equal to the sum of the currents through R0 and R2, or VB minus minus V2 prime all divided by R1 is equal to V2 prime divided by R2 plus V2 prime divided by R0. We continue the analysis of this equation by substituting the fact that the battery voltage is equal to the previously measured V1 plus V2, and the fact that R2 is equal to R1 times the quotient of V2 divided by V1. We find that V1 plus V2 minus V2 prime divided by R1 is equal to the V2 prime divided by R2 plus V2 prime divided by R0. We can rearrange this by making the substitution for R2 that we have in the last bullet point on this slide. And we find that this is equal to V2 prime multiplied the quotient of V1 divided by R2, V2 all divided by R1, plus V2 prime divided by R0. So we're going to start with that equation and continue on the next slide. So in the last slide we concluded with this relationship, and to proceed we combine all the terms that include resistance R1, which is the term on the left-hand side of the equation, and the first term on the right-hand side of the equation. We bring them all to the left side of the equation by subtracting the term on the right-hand side. And when we do so, we find this result, that V1 plus V2 minus V2 prime times the quotient of V1 over V2 all divided by R1 is V2 prime over R0. We rearrange this equation. The first thing we do is we take the reciprocal of both sides, and then we solve for R1 by multiplying both sides by what's the numerator of the left-hand side as written, but what would be the denominator after taking the reciprocal. We do some rearranging, and we have a final answer that you can see here, that R1 is equal to R0 times the scale factor, and the scale factor is 1 plus V1 over V2 times quantity V2 minus V2 prime all divided by V2 prime. We make this calculation, we find R1, and our final conclusion is that the battery pack is sufficiently isolated if this isolation resistance R1 is larger than 500 times the battery voltage, and that the battery pack therefore is not sufficiently isolated if this condition is not met. So what we've seen in the last few slides is a method for determining the isolation resistance if the initial measurement of V1 was less than the measurement of V2. And the procedure for determining the isolation resistance turns out to be essentially the same if the opposite condition is true, except now we must find R2 in the circuit instead of finding R1 in the circuit, because that will be the limiting value. To do so, we insert a large known resistance R0 between the battery's negative terminal and the chassis using a transistor switch as shown in this diagram. We now measure the voltage difference between the negative terminal and the chassis, which is labeled here as V1 prime. By Kirchhoff's current law, we again say that current through resistance R2 is equal to the sum of the currents through resistor R1 and the current through R0. And using Ohm's law, we convert these equations into voltages divided by resistances, and we achieve this equation that you see here, that the battery voltage minus V1 prime all divided by R2 is equal to V1 prime over R1 plus V1 prime over R0. Our next step, once again, is to substitute the identity that the battery voltage is equal to the sum of the originally measured voltages V1 plus V2, and we also substitute that R1 equals R2 times the quotient of the two voltages from the earlier identity as well, and we achieve this equation here, which is very similar to what we saw in the opposite case. Here we see that V1 plus V2 minus V1 prime all divided by R2 is equal to V1 prime multiplying V2 divided by V1 all divided by R2 plus V1 prime over R0. To continue, we start with this equation on the next slide, copied exactly. And we combine all of the terms that include resistance R2 and we bring them to the left side of the equation, as you can see here. And again, we take the reciprocal of both sides of this equation and we solve for R2. And the final result you can see is that the isolation resistance R2 is equal to R0 multiplying a scale factor, where the scale factor is 1 plus V2 over V1 times V1 minus V1 prime, all divided by V1 prime. Once again, we conclude that isolation is sufficient if the isolation resistance R2 is bigger than 500 times the battery voltage, and that isolation is not sufficient if that condition is not met. So in summary, in a vehicle application, you have learned that we must maintain isolation between the high voltage battery pack and the chassis of the vehicle. Isolation is considered sufficient if less than 2 milliamps of current can flow if a direct short circuit were to be introduced between either of the battery terminals and the chassis. You learned how to conduct the Federal Motor Vehicle Safety Standard, or FMVSS, procedure for determining the isolation resistance Ri for the battery pack. And the bottom line, you learned that if we follow this procedure, we consider that isolation is sufficient if this resistance is bigger than 500 times the battery pack voltage. That brings us to the end of this topic, and there's one more topic remaining when we look at the measurement and control aspects of requirement 1 of a battery management system, and that's what we're going to look at in the next lesson. The final topic that we look at that relates to requirement 1 of the battery management system is that of thermal control. And this is not a major focus of the specialization, so I'm not going to go into a lot of detail, but there are some important and relevant points to mention, and that's what this lesson is all about. The temperature of a battery pack has some fairly significant impacts on safety as well as on the lifetime of the battery pack. Generally, lithium-ion battery cells last longest if they're maintained in the temperature band from about 10 degrees Celsius to about 40 degrees Celsius during use. A good rule of thumb is that if you as a human being are comfortable at a particular temperature, then the battery pack is also comfortable at that temperature. In other words, if you feel too cold, then it's probably too cold for the battery pack to perform well. If you feel too hot, then it's probably too hot for the battery pack as well. The battery pack can certainly survive colder and warmer temperatures, but you get the maximum performance and the maximum life out of the battery pack if you maintain it in that kind of a temperature band. The figure on the left of the slide illustrates the safe operating window of lithium-ion battery cells as a function of cell voltage and of temperature. On the horizontal axis you see cell voltage. The safe operating range is going to be different for lithium-ion cells of different chemistries, but this is generally between about maybe a little over 2 volts up to maybe a little over 4 volts. The vertical axis is temperature in degrees Celsius, and the safe operating window extends maybe from about negative 30 degrees Celsius up to about 60 degrees Celsius on this axis. Again, there are some variations depending on how the cell is manufactured and what additives are placed in the electrolyte and some different things like that. But roughly speaking, this is the safe operating window of lithium-ion cells in general. If the cell voltage becomes too low, then the current collector on the negative electrode begins dissolving into the electrolyte. And remember that this is a copper foil, and so copper from this current collector dissolves into positively charged copper ions in the electrolyte, and these try to compete with the positively charged lithium ions in the electrolyte to cycle back and forth through the battery cell, just as the lithium does. Now, these copper ions are usually too large to intercalate into the active materials of either electrode, and so instead they plate metallic copper onto the surface of the electrodes. And this causes a metallic annealing site to form, and once one of these sites has formed, it's easier for other copper or lithium, any other trace metals that are in the electrolyte to form on this annealing site and to make long, thin metallic dendrites that can grow across the separator and cause a short circuit between the two electrodes of this cell. So worst case, under voltage can lead to short circuits and to thermal runaway. On the other hand, if I overcharge a battery cell, that can cause positive electrode breakdown. Remember that when we charge a cell, lithium moves out of the positive electrode, and remember that in some electrodes there's this layered crystal structure that can collapse if too much lithium is removed. So overcharging causes material breakdown in this electrode and quite severe capacity loss. If I overcharge a battery cell at cold temperatures, lithium comes out of the electrolyte in ionic form and will actually plate solid metallic lithium onto the surface of the negative electrode. It's called lithium plating. This removes lithium from circulation, so causes capacity loss, and it also causes dendrites to form and can lead to short circuits as well. Those are some of the primary causes. They can also lead to secondary effects. For example, if I overcharge a battery, it can lead to temperature rise, and that itself can cause the solid electrolyte interface layer, a film layer that grows on the negative electrode particles to passivate them, to break down and expose fresh graphite to the solvent in the electrolyte, which causes more solid electrolyte interface layer to grow. And this reduces the amount of cyclable lithium and decreases the capacity of the battery cell. And just the very act of this formation and growth of SEI, the solid electrolyte interface, can cause temperature rise. And so temperature rise causes SEI growth, which causes temperature rise, and you see that we're having a problem. At some point, the separator can melt, and this could lead to short circuits between the negative and the positive electrode particles, and that short circuit causes large amounts of current to flow, which causes additional temperature rise. This can cause the electrolyte to begin to break down and to form gases and to build up pressure inside the cell. Some of these gases are flammable, and if they're released to the environment, if the cell packaging fails, that can lead to external fires also. As temperature increases, this possibility of venting increases, and the problem is getting worse and worse. You can tell it's accelerating. The cathode materials, the positive electrode materials, often contain enough oxygen. They're generally oxides, and there's enough oxygen in the material itself that once a fire has started, that the fire is self-sustaining. And even in a vacuum, the cell will continue to burn because of the oxygen that is in the positive electrode. And this is a condition called thermal runaway and must be avoided at all costs. So it's also worth noting that it's not only the maximum or minimum temperature of the battery pack that matters, it's also important to keep a relatively uniform temperature across all of the cells of the battery pack. The rate of aging depends on the temperature locally, and so if I want the battery pack to age in a uniform way, all of the cells should have very similar temperatures. If some cells turn out to age more quickly than others, then some will become weaker than the others. And it's usually the weakest cell in the battery pack that limits performance rather than, for example, the average cell in the battery pack. So even if all of your cells are in fantastic health except for one, that one weak cell will limit what your battery pack is able to do. Keeping cells at uniform temperatures also helps to maintain consistency, and so this battery pack will not be limited by only one weak cell. Two different methods are commonly used to cool a battery pack. One is forced air cooling, where fans can direct air across the battery cells in order to cool them. And the other is liquid cooling, where some thermally conductive liquid is run through pipes or plates right up next to the cells to remove heat from them. If the battery pack is used at relatively low rates, then air cooling may be sufficient. But if the battery pack routinely sees high power demand, then it will need a more aggressive cooling strategy to remove this heat because the heat is generated at a faster rate. It might not seem intuitive, but electric vehicles generally need less cooling per cell than hybrid electric vehicles. And this is because electric vehicles are designed for energy applications, for long-range applications, so each cell is discharged at a relatively low rate and therefore generates heat at a relatively low rate as well per cell. Hybrid electric vehicles have essentially zero electric range, and they're designed only to provide the peak power demand, and so power is drawn from cells at a relatively high rate per cell, generating heat at a faster rate as well. So again, that analysis is per cell, so you have to do the math to come up with the aggregate heat generation to see whether liquid cooling is required or whether air cooling is sufficient. The two photographs on this slide show cutaways of two vehicles. The vehicle on the top is the extended range electric vehicle, the Chevy Volt, and the vehicle on the bottom is the Tesla Model S. Both of these vehicles use liquid thermal management. In the Chevy Volt, the battery pack sits between the driver's seat and the passenger seat in the front of the vehicle, and it runs down the center of the vehicle between the passenger seats and the rear, and then splits off and makes a T shape and is behind the passenger seats in the rear. And in this design, there are plates inserted between cells in the battery pack, and these plates have thin, tiny channels in them through which the liquid is pumped to remove the heat generated by the cells. In the Tesla Model S, the battery pack is located in the floor underneath the entire passenger compartment, and liquid is passed in between the cells in this region to cool them. In some cases, it may actually turn out to be advantageous to implement heating in addition to cooling. If we have the ability to heat a battery pack, then we can charge the pack even if the ambient temperature is quite low, because we can cause the temperature of the battery pack itself can be warm enough to charge without risk of lithium plating and damage, even though the outside temperature is cold. Notice that the biggest reason we might want to heat a battery pack is to enable charging, and so heating will be done probably only when the battery pack, the vehicle, is plugged in to the utilities grid, and so we're not wasting battery pack energy to heat the battery pack. Instead, we're using the utilities energy in order to heat the battery pack. Also, because of the resistance of the battery cells, as I'm charging and discharging, even a cold battery pack tends to heat up fairly quickly, so this is why cooling is more important than heating usually. In some cases, we may also wish to cool the battery pack below ambient temperature. Air cooling and liquid cooling exchange heat with the environment and so are able to bring the battery pack temperature down no further than the ambient temperature. But instead, if we use some kind of a refrigerant in our cooling system, then it's possible to cool the battery pack below the temperature of the environment. This is going to require significant energy, and so it may not be a good idea when the vehicle is in operation because we're using the energy from the battery pack to do so. But if the vehicle is parked and the vehicle is plugged in to the utilities grid, then it can be a good idea because it can bring the temperature of the battery cells down into a more healthy range and extend the life of the battery pack. In the United States, one of the cities that's often used as a benchmark is Phoenix, Arizona. If you've been there in the summer, you understand why. Phoenix has very elevated temperatures in the summer, and a vehicle not operating, simply parked on the pavement, encounters really extreme temperatures, even up to 50 or 60 degrees Celsius just parked. And so I think you can see why the ability to refrigerate the battery pack when the vehicle is stationary might be a good thing to do in that situation. So to summarize this very short lesson, you've learned that it's important to keep the battery cells in a comfortable temperature range to ensure safety and to extend the battery pack's life. It's also important to keep the cells at a uniform temperature so that they will age at a consistent rate. And this has the side benefit of reducing the need for many temperature sensors, since we can quite safely assume that the temperatures of most cells are relatively the same. In present commercial automotive battery packs, we either have air cooling or liquid cooling. There are some reports that range and life are negatively impacted by air-cooled systems, since the air cooling is not as effective as liquid cooling. Liquid cooling systems are more expensive, but they're able to extract more heat at a faster rate than air-cooled systems are able to do. Active heating and active cooling while the vehicle is plugged into the utilities grid can extend life and can also shorten charge times, especially if the ambient temperature is cold, by bringing the temperature of the battery pack into a range that will enable faster charging. And finally, I remind you that the focus of this specialization really has to do with designing algorithms for battery management systems. The focus is not on the thermal management system of the vehicle. And in fact, the thermal management system is an enormous design challenge, and you could probably have an entire specialization simply on that topic, but I'll leave that up to someone else to develop who's an expert in that area. So that brings us to an end of this lesson and an end to the major topic areas of this week. The remaining lesson is a summary lesson that looks at what you've learned and looks ahead to the topics that we're going to look at next week. This past week, we devoted our attention to learning about major battery management system functions as part of the preparation to learn how to design battery management system algorithms. We looked at an overview of what a battery management system is required to do, and we looked at 5 basic categories of what a battery management system must do, including sensing and high voltage control and performance management and communications and so forth. We also looked at some design considerations for how the battery pack is designed in its own electronic architecture and what implications that has on the battery management system electronics as maybe a master-slave design. We looked in more detail at the first of the 5 BMS requirements, which has to do with sensing and high voltage control. We asked, what are the sensing requirements of a BMS, and how does the BMS meet those requirements? Specifically, we looked at the voltage sensing capability requirements and how that can be met using analog to digital converters. And you learned how to select an analog to digital converter by looking at resolution requirements and accuracy requirements and sample rate requirements. You learned how to measure temperature using either thermocouples or thermistors combined with the analog to digital converters, and you saw how to measure electrical current using either a current shunt or a Hall effect sensor. You learned how a battery management system safely connects and disconnects from a load, and how to determine whether the battery pack is properly isolated from the chassis of the vehicle. And finally, we looked very briefly at what a battery management system needs to know regarding thermal management. Next week, you will continue to learn about the major battery management system functions. We continue by looking at each requirement that has already been identified and studying these requirements in more detail in order. So we start by looking at the second requirement, which has to do with protection, and ask, what do we need to do to protect the battery pack and to protect the user? How do we actually do it? We look at the third requirement of interface and ask, what must the battery management system interface with and how does it do it? We look at the fourth requirement of performance management, and this includes an introduction to state of charge and total energy and available power estimation. And finally, we look at the diagnostics requirement, which includes an introduction to state of health estimation. So congratulations for making it to this point, and I look forward to talking with you again next week about these additional BMS requirements. Welcome to week 4 of the course. If you're planning to complete the honors section, then there's one more week left. Otherwise, this is the final week, so you're almost there. Last week, our focus was on studying requirement 1 of a battery management system, which had to do with sensing and high voltage control. This week, the plan is to examine the remaining 4 requirements of a battery management system. You may remember that these were protection and interface and performance management and diagnostics. In this lesson, we consider specifically requirement number 2, which has to do with protection. A battery management system must provide monitoring and control to protect in 2 different ways. The first one that we look at is the requirement to protect the battery pack cells from out-of-tolerance ambient conditions. The second is to protect the user from the consequences of battery pack failures. And as you've already learned, high energy storage batteries can be very dangerous. If energy is released in some uncontrolled way, this can have catastrophic consequences. One example is if there's a short circuit inside one or more of the battery cells that will cause large levels of electrical current to flow, which will cause a lot of heat to be generated, which will cause thermal runaway and fire in the battery pack. A second example is if there's physical damage to the battery pack, such as if a vehicle is involved in an accident, and this can lead to very unpredictable energy release due to crushing or penetration of the cells and so forth. If a battery cell develops an internal or an external short circuit, hundreds or even thousands of amperes can develop in microseconds. So if we want to have any hope of protecting against a short circuit, the protection circuitry must act extremely quickly. This is very difficult, and in many instances the best we can really hope to do is to isolate the damage caused by short circuit in one cell so that it does not propagate to other cells in the battery pack. Different applications and different cell chemistries require different degrees of protection. A failure in a lithium-ion cell can be very dangerous, and it can lead to a fire and even lead to an explosion. In many applications, including in the automotive environment, protection is indispensable. When we're designing protection for a battery pack, we must address the following undesirable events or conditions. We must address excessive current during charging or discharging. We must address the possibility of and a response to a short circuit. We must consider overvoltage and undervoltage. We must think about high ambient temperatures and overheating of the battery pack. And we need to look at what happens if isolation is lost. In other words, if there's a ground fault. And we also need to think about what to do if there's abuse to the battery pack. When we're designing protections, we should also consider what happens if our protection mechanism itself fails. Whenever possible, we should implement redundant protection paths so that if the primary protection mechanism fails, then the secondary protection mechanism will still be able to protect the user and the battery pack. The drawing on the right-hand side of the slide attempts to illustrate this. It shows in a graphical way the region of operation in which we would like to operate our battery pack and the region that we would really like to stay away from. In this case, the horizontal axis is temperature and the vertical axis is magnitude of electrical current. The region that is shaded in red indicates locations where it is unsafe to operate the battery pack in terms of temperature and current magnitude. Any point that is not colored red is technically an acceptable point at which we can operate the battery pack. However, we would like to leave a safety margin in our designs so that we not only stay out of the red zone, but we also don't even really get close to the red zone. So we define this green region that you see, which is what we call the safe operating zone, that is separated from the failure zone by a safety margin region which is shaded in white. We choose our safety devices to constrain operation to be inside of the green region. For example, our design might include a thermal fuse. Whenever the temperature increases beyond the fuse set point temperature, the fuse will trigger and operation will cease. The operation boundary of the thermal fuse is drawn as a vertical line on this diagram. To the left of this line, the fuse is not activated and operation continues as normal. To the right of this line, the fuse has activated and has shut down the battery pack. We might also consider using a resettable fuse. A resettable fuse is characterized by the diagonal line that's a function of both current and temperature. So whenever current goes above a certain level at the present temperature, or whenever temperature goes above a certain level at a certain magnitude of current, the resettable fuse will trip, and again operation will cease until the temperature goes down enough that the fuse resets. We can also consider some kind of an electronic protection that is continuously monitoring the magnitude of the electrical current and will again discontinue operation when the circuit determines that electrical current has gone above some magnitude. What's important in this diagram is that you notice that in order to go from the safe operating zone shaded in green to the unsafe failure zone shaded in red, a minimum of 2 of these protection mechanisms must be breached to do so. This means that to enter the failure zone, at least 2 of the protection systems will have failed completely, or to put it another way, we're almost certain that we will never enter a failure zone because we have at least 2 protection mechanisms that will always keep us from doing so. Again, if one of our safety mechanisms fails, we will enter the white region, which is a safety margin, and it's still safe to operate in that region. It's only if 2 of our safety mechanisms fail that we will enter the failure zone. We can draw a similar diagram when we consider protecting against overvoltage and overtemperature together. The diagram on the right illustrates this with temperature once again on the horizontal axis, but this time with voltage on the vertical axis. The thermal fuse can protect against overtemperature. Different kinds of electronic protection can protect against overvoltage and undervoltage. For example, when we consider overvoltage, our battery management system might have dedicated electronics that monitor the voltage of individual battery cells and shuts down. Or the software in our battery management system might additionally monitor these voltages and shut down when they become too high. Additionally, when we think about overvoltage, the most likely cause leading to overvoltage is when we're charging the battery pack, when we're plugged into a charger. So the charging system might have its own overvoltage circuitry or software detection mechanism that can notice if there's a problem and respond to it. On the undervoltage side, our battery management system can once again have either electronic or software-based undervoltage detection, and the load connected to the battery pack can also implement undervoltage protection mechanisms. We do need to be a little bit careful when adding these protection mechanisms, however, especially if they are electronic mechanisms, because each of the devices that we add into the main current carrying path will add some kind of resistance to that path, and that will reduce the power that's delivered to the load and also increase the amount of heat that's generated in the battery pack. It will also increase the cost of the battery pack because of the additional components that we're adding. So we don't want to add an enormous number of these protection devices, but we do want to be careful in our design to add a sufficient number to meet safety standards. Some examples to consider when designing safety mechanisms include a thermal fuse that operates when the present temperature is above some limiting temperature, a conventional fuse which is designed to prevent overcurrent but also operates based on an internal temperature. A note, however, on the conventional fuse is that it operates when it heats up internally and an internal element vaporizes basically, and this may not act quickly enough to protect against some very rapidly accelerating events such as the result of a short circuit. So we might need to consider more active fault detection, by which I mean an electronic device coupled with software instead of some passive device. In addition to protecting the battery pack from environmental conditions that comprise safety hazards, we also need to be able to build into our design the ability to detect operational faults and to be able to tolerate and, whenever possible, rectify these faults. For example, current state-of-the-art battery management systems use processors that have dual processing cores. These cores execute the same instructions at slightly different time offsets and then compare the results of the instructions against each other. When the results don't match, this can trigger execution of additional code that tries to recover from that fault, or at least to inform the user that something went wrong. In a master-slave battery management system, the slave systems can also often detect cell faults without any additional input processing by the master. For example, many of the battery management integrated circuits that we looked at previously can detect automatically overvoltage or undervoltage at a cell level based on thresholds that have been programmed into that slave by the master BMS. They can also often monitor for overtemperature and undertemperature, since they are also measuring those quantities. And in some cases, again, the slave integrated circuits themselves can be redundantly implemented so that you have two slave chips measuring the same physical quantities and comparing results against each other. And if those results do not agree, then at least one of the results is wrong, and that can be reported to the master BMS, which will take appropriate action to respond to that. If a slave determines that there has been a very serious fault, it may in some cases be given authority to shut down the battery pack without involving the master microprocessor. This is an extreme condition and not one to be undertaken very frequently, but it can help to save a battery pack and to ensure safety when communications with the master microprocessor has been lost or when the master microprocessor has failed entirely. Monitoring voltage faults and temperature faults is fairly simple, but there are some other types of faults that are much more complicated and must be detected using software. One example is the method that you learned for detecting isolation faults last week. All of this discussion also brings up the realization that the communications link between the master and the slaves must have very high electrical noise immunity, or very high EMI, electromagnetic interference immunity. We really desire that the communication be robust and reliable and fault-free in order to have an overall robust battery management system that's able to detect the safety of the battery pack and to perform all of its normal required operations. Whenever we're designing a battery management system for specific applications, it's also important to be aware that there are different international safety standards that must be complied with. For example, when designing a battery management system for a passenger vehicle that has a maximum vehicle weight up to 3,500 kilograms, we must comply with the ISO 26262 safety standards. If we're designing a battery management system for an electric motorcycle, we must comply with ISO 19695. And this is similar to, but somewhat different from, the ISO 262. Or if we're designing a battery management system for trucks larger than 3,500 kilograms, which includes even commonly seen vehicles like the Ford F-250 or the Chevy Silverado and others, then we must comply with the IEC 61508. Now, it's not the goal of this specialization to talk about safety standards. They're quite complicated and they would require courses of their own really to understand them and how to implement them. At this point, I simply want you to be aware that these standards exist, and it's important when designing a BMS such that our software and hardware designs comply with these standards. The fact that there are different standards for different applications tends to make it difficult to have one universal BMS that can apply to any application at all. The safety standards I've listed all have the same general goals, but they are somewhat different in how they describe these goals and in how they apply them. For example, they define things called safety integration levels, or SILs, and evaluate them, though, in different ways. So it's challenging to design to all of these standards simultaneously. And as I've mentioned, these standards are complicated and require courses or specializations of their own to understand them completely. When implementing BMS software, the amount of time and code required to satisfy the standards should also not be underestimated. Some of the colleagues that I have in the field tell me that 40% or more of the BMS code is written specifically to address safety standards. So to summarize this lesson, you've learned that it's critical to protect the battery pack operator and the battery pack itself. It's good design practice to require multiple protections to fail before the battery pack itself is able to fail. Along the same lines, it's important to have redundant sensing and processing to make a robust design to enable fault detection. And finally, there exist international standards that inform as to the best practice designs that lead to robust and fault-tolerant implementations, but these are beyond the scope of this specialization. So that concludes this lesson on safety and protection, and from here we move on to look at the remaining BMS requirements. Last week and so far this week, you've learned about requirements 1 and 2 of a battery management system, which have to do with sensing and high voltage control and protection. In this lesson, we're going to consider requirement 3, which has to do with interface between the battery management system and the host application. This includes the communications itself. It also possibly includes controlling a charger, data recording for diagnostics purposes, and it can include auxiliary tasks such as range estimation. Let's first think about how the BMS communicates with the host application. There are many ways of doing this, but a very common approach that's used in a lot of applications is the Control Area Network, or CAN bus, which is an industry standard way of communicating. In the automotive application, it's the universal way of communicating between electronic components in the vehicle. The CAN bus specification is designed to provide robust communications between two processors in a very demanding and harsh automotive environment where there are high levels of electrical noise. It's already used in conventional vehicles where these noises come from spark plugs firing, for example, and so it's a natural choice when moving to electric drivetrains where there's also a significant amount of electrical noise generated by the electronics that drive the power for the electrical motors. The CAN bus uses two wires and communicates in a serial fashion, one bit at a time between the two processors. It's designed to network intelligent sensors and actuators and processors together, and it's able to operate at two rates simultaneously. One of these rates we would consider a high-speed rate. It might be around 1 million bits per second, or roughly 1 million baud. The high-speed operation is used for critical things such as engine management and vehicle stability and motion control, and things that are performance critical and safety critical. The low-speed operation might work at 100,000 bits per second, or roughly 100,000 baud, for example. The low-speed CAN bus might be used for simple switching, control of lighting, operation of power windows and mirror adjustments, and instrument displays and other functions where the safety and performance are not as time critical. The CAN bus protocol defines how to transmit information between two different entities connected on the bus in the following way. It gives a method to address the messages to a specific destination device connected to the bus. It defines the data format to be used in the message. It defines the transmission speed of the high-speed and the low-speed aspects of the protocol. It also defines priority settings for a message being transmitted on the bus, and it defines sequencing of messages and responses. It also talks about how to detect errors and how to handle those in order to get retransmissions so that we are able to communicate everything that we desire to communicate. And it defines some control signals. I've illustrated the format of one frame of a CAN bus message on this slide. The frame begins with a single bit that's a start of frame or SOF marker. Then there's a 29-bit identifier for the address of the recipient of the message. Then there's 1 bit ready to receive or RTR field, and this is followed by a 6-bit control field that describes what this message is all about. The main part of the message is a data field with the information that is to be transmitted across the wire across the bus from the transmitter to the intended recipient, and this data field can have a length of anywhere between 0 and 8 bytes. This is followed by a checksum that's used to detect whether there have been any transmission errors in the message, and this checksum is often called a cyclic redundancy check or a CRC check. The next field is a 2-bit acknowledgement field that's used to acknowledge correct receipt of a message, and finally the message concludes with a 7-bit end of frame or EOF, which is combined with the when combined with the 1-bit start of frame puts bookends on the message so that the recipient knows that the entire message has been received correctly. These data frames are transmitted sequentially over a bus that's shared between many devices, and when data frames are successfully received, an acknowledgement is sent back. If a data frame is not received at all, there will be no acknowledgement, and so after some timeout period it's retransmitted. If the data frame has been received correctly, then the acknowledgement will be sent back to the original sender, and so the sender knows there's no need to retransmit. One application that requires the battery pack to communicate with the outside world is when the battery pack is being charged. Battery packs are charged generally in two different ways. One way is what I will call random charging. This is when charge is delivered in unpredictable patterns to the battery pack from the host application. In a vehicle, this happens when the driver presses the brake pedal, and instead of using the friction brakes, it's possible to use the motor, put the braking energy through the motor back into the battery pack to add charge to the battery pack. And this recovers some of the energy that would otherwise be lost and improves the efficiency of the vehicle. Now, of course, in a vehicle you still need the redundant friction brakes, and so regenerative braking is used for only a portion of the overall braking need, but it does help to increase efficiency. Control of random charging is done by providing the host application with charge power limits that must be obeyed at all points in time. And these power limits are dynamic in the sense that they change as the state and the environment of the battery pack changes, and so the battery management system must continually calculate how much recharge the power the pack can safely accept and then transmit these limits to the host application. The second type of charging is what I'll call plug-in charging, and this is used in an electric vehicle that could be connected to the electric power grid. So this includes pure electric vehicles, of course, and plug-in hybrid electric vehicles and extended range electric vehicles. In these applications, it's possible to communicate directly from the battery pack through the host application to the charger to control the charger's output current or power more directly. So the battery management system can then ensure that the voltage of the charger meets certain requirements, and it can conduct balancing of the different battery cells and of the battery pack while charging is happening. The mode of plug-in charging often follows what we call a constant power, constant voltage mode, which we saw a number of weeks ago in this course. There are more exotic methods that are possible, and it's my belief that future electric vehicle charging will be optimized in order to charge the battery pack quickly and safely, and that this optimization process will turn out to be somewhat different from standard constant power, constant voltage charging. Lithium-ion cells can safely accept much faster charging when they are warm than when they are cold, and so some battery management systems implement heating that activates when the vehicle is being charged when it's plugged in. The heating system is powered directly from the grid, and so battery energy is not wasted in order to activate these heaters. And so the heating system makes the battery pack last longer in the sense that it can charge more quickly without causing damage, which is a huge advantage, of course. While we're talking about charging, I would like to perform a really fun thought experiment with you. One of the things that's limiting consumer acceptance of electric vehicles is the rate at which they can be recharged. So we might want to consider what limits that rate. Let's think about this. First, we need to think about how much energy is required when we're charging the battery pack. And it turns out that most passenger vehicles of moderate size require between 200 to 300 watt-hours per mile traveled. And this is a value that we can verify at the end of the second course in the specialization. So if we desire a 300-mile range, the battery pack must have between 60 to 90 kilowatt-hours of capacity. If we're to charge the entire battery pack in 3 minutes, which is roughly the time it takes to fill a gasoline tank of a standard automobile, then it would require power transfer at the rate of about 1.8 megawatts, and that's an enormous amount of power. So instead of thinking about what's required to charge in 3 minutes, let's think from the other point of view of how much power is commonly available. In the United States, in a household standard circuit, electrical power is provided at 110 volts AC and 15 amperes. And this is roughly 1.5 kilowatts, and charging at this rate is termed level 1 charging. A level 1 circuit then is able to recharge the battery pack in about 40 to 60 hours. And clearly that's far too long, so we must consider other levels of power that might be available. Again, in the United States, it's also quite common for households to have specialty circuits for the electric stove and for electric clothes dryers that operate at 220 volts AC and between 30 and 40 amperes. This corresponds to about 6.6 kilowatts, and this type of charging is called level 2 charging. Level 2 charging is able to recharge a battery pack of this size in between 10 to 15 hours. So that's still very long, but clearly it's far better than level 1 charging. And in fact, since most people don't drive 300 miles every day, level 2 charging is generally considered sufficient for most vehicle applications unless you happen to be driving very long distances between two destinations. And so there's something called level 3 charging, which presently exists in multiple forms. One uses direct current and operates up to a limit of around 500 volts and about 125 amperes. This can charge up to a battery pack up to about 80% state of charge in about 30 minutes. Tesla has implemented their own proprietary level 3 fast charging system for their Model S, and that can provide about 50% state of charge in about 20 minutes. So you see that in most cases the limit to how quickly we charge a battery pack is not truly the battery chemistry. Instead, it's the electrical service to which the battery pack is connected. But it's also true that the battery can limit charge rates, especially at low temperatures and at high states of charge. So present research on fast charging is concentrating on how can we accelerate that final 20% of charge, and how can we safely charge a battery pack at low temperatures. A third function that I associate with the communication requirement of the battery management system is that of maintaining a logbook. For warranty and for diagnostic purposes, the battery management system should store a permanent record of unusual or abuse events. This record should include a description of what the abuse was, such as whether it was a measurement that was out of tolerance, or whether there was some overvoltage or undervoltage, or whether too much current was measured, or something like that. It should also measure the duration of the abuse event and the magnitude of the abuse event. Since an overvoltage event of 1 microsecond is probably not a major concern, but an overvoltage of 1 minute could quite easily be a significant concern. This logbook can also store diagnostic information that is not directly related to any unusual event, but it could be useful in determining how this battery pack has been used over time. It can store the number of charge and discharge cycles completed. It can store the state of health estimates at the beginning or ending of every drive cycle. And it could store just about anything you can think of that should be maintained between one point in time and another point in time, such as when the battery pack is removed from the load and when it's reconnected to the load. This record is stored in non-volatile memory. For example, flash memory, such as used in solid-state drives in your laptop or on a USB thumb drive. These data can be transmitted to the host application when required, but many battery management systems have secondary diagnostic interfaces so that a technician is able to access the data directly without requiring a path through the host application to do so. This way, the technician can determine directly from the battery management system the information that's required to diagnose a problem, and which can lead to some ability to correct the problem. There are other tasks a battery management system might do in cooperation with a host application. These would tend to be more application specific, and the one that I talk about here briefly applies to electric vehicles. In that case, the host application might require the battery management system to compute an estimate of the present remaining range of the vehicle based on the amount of energy remaining in the battery pack. This, however, turns out to be a quantity that's heavily influenced by environmental factors, such as what are the vehicle characteristics, and how is the vehicle being driven, and what is the surrounding terrain, such as are there many hills, will I be going up or down a lot? What is the weather like? Is there a lot of snow on the ground that's causing friction, or is there a lot of wind that's either impeding or helping progress? It even matters whether the ambient temperature is warm or cold and how the vehicle will operate. So range estimation is very difficult. It depends not only on how much energy is available in the battery, but also on the characteristics that are truly known only by the host application. And so at this point in history, it appears to me at least that every automotive manufacturer will have their own range estimation algorithms. But again, in the next specialization towards the end, we will see how to simulate an electric vehicle as an example battery load, and you'll be able to see perhaps how range estimation might be done. At this point in the specialization, it's sufficient to know that the battery management system must at least produce the inputs to these algorithms, and especially for the range estimation algorithm, how much energy is presently available in the battery pack. And so, to summarize this lesson, you've learned that a battery management system must communicate critical information about the present operating condition of the battery pack to the host application. This is very often done using a CAN bus protocol, and since CAN bus electronics are implemented in hardware already on many microcontrollers that are available off the shelf, this is not a difficult thing to do. The communication needs and requirements tend to be application specific, but there are some common features. The battery management system must often give information about how to control the battery pack charging system in order to avoid safety hazards. The battery management system must often maintain a logbook of unusual or abusive events. The battery management system may also be required to perform application-specific tasks that might include computing an estimate of how much available range is left or distance to empty estimate for an electric vehicle. And of course, the battery management system must communicate to the host application estimates of available energy and available power and states of charge and states of health and so forth. And so we will begin to consider the estimates that a battery management system must provide to the host application in the next lesson. Last week, you learned that there are 5 major requirement areas that must be satisfied by a battery management system. So far, you've learned about requirements 1 through 3 in more detail. In this lesson, we consider requirement 4, which has to do with performance management, and this includes computing estimates of state of charge and available power, and having an ability to balance or equalize cells in a battery pack. Fundamentally, applications using battery packs need to know 2 basic quantities that describe the present state of the battery. The first is how much energy is available in the battery pack. The second is how much power is available in the immediate future, and this I try to illustrate by drawing a glass of soda and a straw, and I'll explain what I mean by this as I continue. Knowledge about how much energy is available in a battery is most important for applications like electric vehicles. Energy tells me how much work I can do. In an electric vehicle, the energy estimate informs me as to how far I am able to drive before I must recharge the battery pack. In this illustration, we can compare the amount of energy in a battery to the amount of soda in a glass as an analogy. When a battery is fully charged, there's a lot of available energy, and when the battery is fully discharged, there's no available energy. It's the same with the glass. When the glass is full, there's a lot of soda in it. When the glass is empty, there's no soda in it. Energy is a total quantity, talking about a total amount of work that we can do. We can contrast that with the concept of power. Power is the rate of energy usage. Knowledge of how much power is available in the immediate future is most important for applications like hybrid electric vehicles. This information tells me whether I can accept recharge energy quickly or whether I can provide energy quickly to accelerate. In the example, power is illustrated by the straw. If the straw has a wide diameter, then we can extract soda quickly from the glass. If the straw has a narrow diameter, we can extract soda only slowly. So energy and power are like soda and a straw. Both power and energy estimates are important for applications like extended range electric vehicles and plug-in hybrid electric vehicles, because they need to know how far they can drive, but they also need to know how quickly they can accelerate and decelerate. It turns out that no sensor exists that's able to measure the available energy or the available power. Instead, we must create methods to estimate the amount of energy and power. And in order to estimate energy, we must know at least all of the cell states of charge and all of the total capacities of the cells in the battery pack. To estimate power, we must know at least all the cell states of charge and all of the resistances of the cells in the battery pack. But it turns out that we cannot measure these properties directly either. No sensor exists that can measure state of charge or capacity or resistance directly. So we must find ways to estimate these values, and the diagram on this slide shows the overall process. To the right of the diagram, we see the desired outputs of how much energy and how much power might be available from the battery pack. In order to come up with these estimates, we need to know all of the capacities of the cells, denoted as Q, and we must know all of the states of charge of all of the cells, and we must know all of the resistances of all the cells, denoted by R. Once we have these values, we can perform deterministic calculations to arrive at how much energy and how much power are available. But we can't measure state of charge or capacity or resistance directly, so we must somehow come up with values for these quantities using things that we can measure. The available inputs include cell voltages and battery pack current and either cell or module temperatures. So we use those basic measurements with computer methods called algorithms to come up with estimates of capacity and state of charge and resistance. And those estimates then feed the power calculations, and in the end we're able to compute the estimates of energy and power that we require. It turns out that there are both good methods and poor methods to produce estimates. There's not only one way to do it. The simplest methods are usually, unfortunately, the least effective methods also. And there are some impacts to implementing a poor estimator. One of these could be an abrupt correction when a voltage or a current limit is exceeded. For example, if a battery management system in a vehicle tells the vehicle control computer that 50 kilowatts of power is available, and then that vehicle draws that power to start accelerating, but then the battery management system says, "Oh, sorry, I was wrong, that's too much power, my cell voltages are now too low," what's going to happen? One thing could be that the battery management system or the vehicle control computer decides to simply cut off power to the vehicle in order to protect the battery pack. But that would be an enormous safety concern. And the customer furthermore would develop some perception that the vehicle exhibits poor drivability and would be very unlikely to purchase your product again in the future or to recommend it to someone else. Another alternative, when a bad estimate has been made and the battery management system says, "Oh no, the voltages are too low," is to just accept that condition and keep on operating. Even though it's causing some damage to the cells, we're still allowing the vehicle to use energy from the battery pack in order to accelerate, because I promised the vehicle that it was able to do so. This might be less of an immediate safety concern, but it does cause damage to the cells, which is an undesirable consequence. So the most common approach to compensate for uncertainty introduced by poor battery management system estimation algorithms is to over-design the battery pack by putting in too much capacity for the application, and then by derating the estimates of energy and power that we tell the host application in order to ensure that we never overcharge or over-discharge the battery cells. So as an example, if I calculate that there is 50 kilowatts of power available, but I don't trust my estimate, I might multiply that value by a factor like 0.8 and then tell the vehicle that, oh, there's only 40 kilowatts of power available. So clearly, we're not using the entire capacity of the battery pack if I do that very often. So all of these responses to using a poor estimation algorithm have costs in dollars or euros or whatever currency, and costs also in weight and volume if I need to add more battery cells than are really required by the application. So we'd really prefer to do a better job of creating estimates. And you might wonder why there's a picture of this gentleman on the slide. His name is Rudy Kalman, K-A-L-M-A-N, and he was the inventor of a technology known as the Kalman filter. Kalman filters turn out to be the optimal way of estimating the internal state of some dynamic system when we have the ability to measure only the inputs and outputs of that system. And in the third course in the specialization, we're going to spend a lot of time investigating this method called Kalman filtering, and you're going to learn all about it. And you're going to learn how to implement the Kalman filter and some of its variations that work for nonlinear systems such as battery cells. And you'll learn how to apply the extended Kalman filter and the sigma point Kalman filter or the unscented Kalman filter to estimate battery cell state of charge. And when we get to course 3, it will take a few weeks to learn how to do this, but the outcome will be that you will know how to perform state estimations so much better than can be done using some of these ad hoc poor methods. And you'll learn how to find the near optimal solution for estimating state of charge of battery cells. So to summarize this lesson, you've been reminded that applications need to know at least 2 principal quantities about the battery pack: how much energy is available and how much power is available in the near future. Unfortunately, we are not able to measure these quantities directly, and so we must estimate them based on knowledge of states of charge and capacities and resistances of cells in the battery pack. Again, these quantities also are not things that we can measure directly, and so we must estimate their values using measured quantities like cell voltage and battery pack current and temperatures. The major premise of this entire specialization on algorithms for battery management systems is that investing some time learning about good battery management system algorithms, and by investing some money on good battery management system electronics and algorithms, can ultimately lead to a reduced battery pack size and result in considerable cost savings when building a battery management system and selling many quantities of it. In the second course in the specialization, you will learn how to create mathematical descriptions or models of battery cells that are needed by these algorithms. In the third course, you will learn about advanced methods for state of charge estimation, including Kalman filtering. In the fourth course, you will learn about state of health estimation, which will allow you to compute estimates of battery cell capacity and resistance. And finally, in the fifth course of the specialization, you will learn about how to balance a battery pack and how to estimate power limits. Over the remainder of this week, we'll talk about a preview of some of these. We can't go into depth until we do it in this sequence, but you will at least see ideas of the concepts involved that you will learn over the rest of the specialization. In this lesson, we continue to explore Requirement 3 of the Battery Management System, which has to do with performance management. We're thinking specifically about the requirement for state of charge estimation, and it's worthwhile to think a little bit about what truly does state of charge mean. You probably already have a good intuitive feeling for state of charge based simply on using electronic devices that have state of charge meters. This might include the state of charge indicator on your notebook computer or on your mobile phone or on some other electronic device. So you already understand when the meter reads 100% that the battery is fully charged, and when the meter reads 0% the battery is empty. But is this display something that is empirical and not truly physical, or does it correspond to something that is truly physical even though it may not be measurable directly? The diagram below shows a schematic of a lithium-ion battery cell where we're thinking about how lithium moves inside the cell as the cell is operated. When we discharge the cell, lithium moves from the negative electrode across to the positive electrode. And when we charge the cell, the opposite happens. Lithium moves from the positive electrode over to the negative electrode. So if you think about it, when the cell is fully charged, there will be a lot of lithium in the negative electrode. And when the cell is discharged, there will be much less lithium in the negative electrode. So thinking about it that way, we can connect our intuitive idea of state of charge directly to the physical quantity of how much lithium is present in the negative electrode particles, or equivalently, what is the concentration of lithium in the negative electrode particles of the battery cell. In this specialization, we do not spend very much time talking about modeling or understanding lithium-ion battery cells at the electrochemical level. If this is something that's interesting to you, then I recommend that you study my first textbook on battery management systems, Volume 1 on battery modeling. But for this specialization, it's sufficient to have a very simple understanding of this one concept that we talk about on this slide. You already learned in week 2 of the course that lithium can be absorbed into the negative electrode particles by entering into the empty spaces of their crystal structure. There is some maximum amount to how much lithium can possibly enter into those spaces before it's completely full. And we call this concentration CS max, C for concentration, S for the solid particles of the electrode, and max, of course, for the maximum value. So when the particle is completely full of lithium, the concentration of lithium in the particle will be CS max, and similarly, when the particle is completely empty of lithium, the concentration will be 0. At any other intermediate point, we have some other concentration, and when considering cell state of charge, the important quantity is not the local concentration at any point in the electrode or even at any point in a particle in the electrode, but instead it's actually the average concentration over the entire electrode, which I'm calling on the slide CS average, perhaps at time k. So we can normalize this present average concentration by dividing it by the maximum possible concentration to give us a value that's always between 0 and 1. And this value is called the stoichiometry of the electrode, and it's often denoted by the symbol theta, and here also with a subscript k, which refers to a point in time indexed by k. The stoichiometry is a number, as I said, between 0 and 1, and we can consider it to be a kind of an electrode state of charge. But we must understand that this electrode state of charge is different from what is reported to the user as a cell state of charge. You might remember that in some electrodes we're not permitted to charge above a certain concentration or discharge below a certain concentration, so the stoichiometry is not permitted to use the entire possible range between 0 and 1. There's a lower limit to the stoichiometry before the cell begins to deteriorate quickly or is unable to provide adequate power. Similarly with the upper limit, and so the cell is always operated above the stoichiometry of 0. So when a cell is at 0% state of charge for the whole cell, the stoichiometry for the electrode, which we call theta 0%, is actually a number bigger than 0. And correspondingly, when a cell is at 100% state of charge, the stoichiometry, or the electrode state of charge, is at some value less than 1 that we call theta 100%. So we're going to operate the cell not between a stoichiometry of 0 and 1, but rather between a stoichiometry of theta 0% and theta 100%. In other words, when the cell is at a stoichiometry of theta 0%, it actually has a cell level state of charge of 0%, even though the electrode state of charge is above 0. And when the cell stoichiometry is at theta 100%, the cell state of charge is at 100%, even though the electrode state of charge, or stoichiometry, is less than 1. So this might actually give you some insight into how it's possible to overcharge a battery cell or how it's possible to undercharge a battery cell. It's physically possible to remove more lithium than the theta 0% to get all the way down, at least in principle, to 0. And it's possible to charge above theta 100%, theoretically up until you get up to 1. But we don't operate out of those regions, at least we intend not to operate outside of those regions for safety purposes and for cell longevity purposes. So keeping the discussion in mind of what we've said so far, we can write the cell state of charge as equal to the present stoichiometry of the negative electrode minus the 0% value of that stoichiometry, all divided by the range between the 100% and 0% stoichiometries. And this relationship, while we've discussed it for the negative electrode, actually holds for the positive electrode as well, as indicated by the second equation. The cell state of charge is also equal to the stoichiometry of the positive electrode minus its 0% value, all divided by the range between the 0 and 100% values. The tricky bit which comes in when we're using positive electrode numbers is that the numerator and denominator of this equation will both be negative. We still result in a positive state of charge, but it's thinking about it a little bit differently. So the state of charge of a cell is actually a physical quantity. It's related to the average concentration of lithium in the entire negative electrode. It's also related to the average lithium concentration in the entire positive electrode. So if we were able to create a sensor that could measure this average concentration directly, then we could measure state of charge directly. But at least at this point in history, no such sensor exists. So it's natural to ask whether the concentration of lithium in the negative electrode is somehow directly related to things that we can measure, such as cell voltage. Well, it turns out that cell voltage depends on the concentration of lithium at the surface of the particles in the electrode, and in particular at the surface of the particles that are in direct contact with the negative current collector. Remember that lithium, as it diffuses into and out of the particles in the electrode, causes transient concentration differences between the surface and the bulk interior concentration of the particle. And these concentrations become the same only after time has elapsed, when the cell has been allowed to rest in an open circuit condition. So, remembering that state of charge depends on average concentration of lithium and that voltage depends on surface concentration at one point, we can see that there is not a direct relationship between state of charge and the voltage that we measure right now. The two things are not the same. So there's no immediate direct correspondence between cell voltage and cell state of charge. In fact, cell voltage can change for a number of reasons, even though the state of charge could be constant. For example, if we change the cell temperature, the cell voltage changes a little bit, but the state of charge does not change. If we have been using the cell and then allow it to rest, the voltage changes as it's resting, but the SOC doesn't change. And also, due to a phenomenon called hysteresis, cell voltage also depends not only on what's happening presently, but on the recent history of how the cell has been used, and that can lead to different steady state values even at the same SOC. And you're going to learn more about all of these effects during the second course of this specialization when we discuss modeling the behaviors of lithium-ion battery cells. So in summary, state of charge changes only when we change the average concentrations inside of an electrode, and these concentrations change only due to passage of current through the cell, either charging or discharging the cell, or due to self-discharge in the cell. So voltage does turn out actually to be very useful as an indirect indicator of state of charge and is very helpful in state of charge estimation, but it's not a good independent predictor of state of charge, that is, by itself. So state of charge changes only when current passes through this cell, either due to some external circuitry drawing that current or forcing that current, or due to self-discharge. Why don't we simply use measurements of cell current to estimate the state of charge? There's a perfectly valid equation that relates state of charge to cell current, which I've written on this slide. And if you look at it, it's saying that the present state of charge at time t is equal to some initial state of charge at time 0 minus the total net integrated amount of current that has passed through the cell, weighted by an efficiency factor eta and divided by the total charge capacity of this cell. What this equation is doing is integrating or counting the net number of coulombs of charge that have entered this cell and relating that to some initial charge level to update the present charge level. In this equation, electrical current is considered to have a positive sign when the cell is being discharged and a negative sign when the cell is being charged. In the equation also, the parameter eta, the Greek variable eta, is equal to the coulombic efficiency of the cell, which is usually approximately equal to 1 but is never greater than 1. And Q is the total capacity of the cell measured in ampere seconds or coulombs. This capacity, by the way, is a physical quantity. It measures the number of vacancies in the electrode structure, in that crystal structure, that could hold lithium between the stoichiometry of 0% and 100%. So this is not a function of temperature or rate or any other such thing. It's different from a discharge capacity, which is what is commonly put on a data sheet for a battery cell. It's a total capacity, it's a total charge capacity, if you will, and not a discharge capacity. And we're going to look at that in more detail as we pass through the specialization. This equation, I've said, is not very good for estimating state of charge, and yet it is actually an exact representation of state of charge of the battery cell. We run into some very serious problems if we try to use it as our only basis for estimating state of charge, though. Methods that do this are called Coulomb counting, because we're counting or measuring the number of coulombs that go into and out of a battery cell. But Coulomb counting suffers very serious inaccuracies when we can't measure current perfectly, which is always the case, or when we don't know coulombic efficiency perfectly, which is always the case, and when we don't have a perfect estimate of the total charge capacity, which is always the case, and when we don't know the initial state of charge at time 0, which is always the case. So for this reason, Coulomb counting should never be used in a battery management system as a primary state of charge estimation method. And you will learn that there are much better ways of estimating state of charge, and you will learn how to implement those in the third course in the specialization. So in this lesson, you've learned that cell state of charge is directly related to something that is truly physical in a battery cell. Oftentimes people talk about a battery pack state of charge and mean by that some quantity that relates collectively to many battery cells at the same time. So I'd like us to think for a few minutes about what is the battery pack state of charge. Let's consider the example illustrated by the 2-cell battery pack drawn on the right side of this slide. The drawing shows one battery cell that's fully charged and it's shaded green, and one battery cell that's empty and it's shaded red. And these cells are connected electrically in series so that charge passing through one cell must also pass through the other cell. And when we compute a battery pack state of charge, what should that value be? Should we define, for example, the battery pack state of charge to be 0% because we recognize that this configuration is not able to discharge? Notice that if we were to try to discharge, the current would flow out of this battery pack, and that would deplete the level of charge in the green cell, which would be fine, but it would also attempt to deplete the amount of charge in the red cell, which we could not, or at least should not do, because the state of charge of that cell is already 0%. So we should not really define a battery pack state of charge to be 0% because that implies that we are able to charge the battery pack, and we can't do that either. If we were to charge the battery pack, that would increase the level of charge in both cells. And if we increase the level of charge in the red cell, that would be fine. But if we increase the level of charge in the green cell, it would cause an overcharge situation, which we don't want to happen. So defining a battery pack state of charge of 0% does not make sense in this example. So maybe we should define the battery pack state of charge to be 100% because it's not possible to charge. But that's not really a good solution either, because that gives us the idea, oh, the battery pack state of charge is 100%, so I should be able to discharge, and we already know that we cannot do that. So how about reporting a battery pack state of charge that's the average of the cell states of charge, in other words, 50%. But we really can't do that either, because that implies that we're able to both charge and discharge the battery pack, and we can't do either one. So I propose to you that the term battery pack state of charge is something that frankly does not make sense. It is ill-defined, and in my opinion, it should never be used. One thing that this discussion points out is that the battery pack should never end up in the situation that I have drawn. It's a requirement that we perform cell balancing or cell equalization to avoid this situation. But if we don't balance a battery pack, it is actually physically possible for a pack to arrive in the state of charge configuration drawn on this slide. And if we even get close to this level of imbalance, we can see that the term or the concept of battery pack state of charge does not make sense. But people try to use it, and we might want to think about why someone would even care to know what a battery pack state of charge is. One reason is for set point control. For example, in a hybrid electric vehicle, we want to keep the states of charge of all the cells around or close to some set point so that we can guarantee that there will always be some margin for charging and some margin for discharging the battery cells in the pack. For that application, knowing the average state of charge of all the cells in the battery pack might work as a set point as long as none of the cells are at some extreme points. That is, a battery pack state of charge is not needed to perform set point control. Instead, battery pack average state of charge is needed. Adding that one term average there clarifies exactly what we mean and makes it a lot more precise. Another application for which we might want to know a battery state of charge is a distance to empty kind of calculation or a fuel gauge kind of calculation. But the true issue is not the state of charge of a battery pack, which I again argue does not make sense, but instead how much energy remains in the battery pack that might be used, and this is not the same thing as state of charge. So in my mind, there's no true application that demands knowledge of battery pack state of charge. And so my recommendation is that we don't even attempt to create an artificial quantity when other quantities might substitute better instead. So finally, to summarize this lesson, you've seen that a battery cell state of charge has a real physical basis that can be connected directly to something happening internal to the cell inside of its fundamental electrochemistry. If we somehow knew exactly the average lithium concentration in either the negative or the positive electrode, then we could compute the present stoichiometry of the electrode, and we can compute the cell state of charge given the equation that we've already seen. Generally, though, we don't know this concentration, and so we ask whether direct measurements of voltage or electrical current can be used to tell us what is the state of charge. And we've seen that it's not possible to use only voltage or only current to tell us what state of charge is. Somehow we must combine these measurements in an intelligent way and use them to help us to estimate state of charge. And you will learn how to do that in the third course in the specialization. Finally, battery pack state of charge is a concept that truly doesn't make sense, and I recommend that it not be used. Usually what people mean when they are talking about a battery pack state of charge is some kind of average of the states of charge of all of the cells in the battery pack. If that's what's truly meant, then instead we should refer to that as a battery pack average state of charge. And there are some real examples, real applications where a battery pack average state of charge is meaningful and a useful quantity, and we will see some of those as we progress through the specialization. In the meantime, though, we're going to think only about cell state of charge. And that brings us to the end of this lesson, but we're going to proceed in the upcoming lessons to think a little bit more about performance management. We're continuing to look at requirement 3 for battery management systems, which has to do with performance management. Two of the estimates that must be produced by the battery management system are the amounts of energy presently stored in the battery pack and the amount of power available over the near-term future. We're going to start our analysis of these requirements by first considering how much energy is available in a single cell in a battery. Remember that energy is an ability to do work which we can measure either in watt-hours or kilowatt-hours. We can compute the total energy in a cell in a fairly simple way. The energy is equal to the total charge capacity of the cell Q multiplied by the area under the open circuit voltage relationship between the present state of charge and the minimum state of charge permitted by the application. This integral might look difficult to compute, but in fact it's possible possible to pre-compute its values and store them in a table for easy lookup using a table lookup interpolation scheme as the battery management system operates, which you will learn how to do in a later lecture this week. So the total energy available in a cell has something to do with the voltage relationship between a minimum state of charge and the present state of charge and a total capacity. And this is sometimes adequately approximated by taking the nominal capacity and multiplying by the nominal voltage and multiplying that by the difference of state of charge between the present operating point and the minimum permitted state of charge. The figure on the right shows some example open circuit voltage relationships for 6 different varieties of lithium-ion battery cells that we've tested and calibrated in our laboratory. The lower 2 curves correspond to 2 different varieties of lithium iron phosphate battery cells, and you can see that these have the characteristic of a very flat open circuit voltage relationship between about 10% and 90% state of charge. So the true open circuit voltage is actually very well approximated by the nominal cell voltage in that range, and this approximate relationship on this slide would very likely work quite well for iron phosphate type of cells. The other 4 curves are for different varieties of lithium-ion cells that include lithium manganese oxide and lithium cobalt oxide and nickel manganese cobalt oxide cells. These voltage relationships are not quite as flat, and so the approximate energy computation would not be as adequate in this case, or as accurate, but still for some applications it might be sufficient depending on the nature of the application. Notice that the equation for energy is not a function of the magnitude of current used to withdraw that energy. In other words, it's not a function of rate. To the first order, it's also not a function of temperature. We have already noticed that the total charge capacity of a battery cell is not a function of temperature, and while the open circuit voltage relationship has a slight temperature dependence, it's not enough to change the available energy significantly. This statement might contradict your intuitive feel for how much energy is present if you have experience working with lithium-ion battery cells. You might already know that it's impossible to get as much energy out of a cold battery cell as it is to get out of a warm battery cell, even if both were to start with the same amount of charge in them. But we need to be careful with what we're defining to be the energy contained in a cell. If a cell has 1 unit of energy, it does not depend if the cell is warm or cold or how quickly we take the energy out of the cell. It has 1 unit of energy. If I warm up the cell, that doesn't appreciably change the energy, except maybe for some thermal vibration and some electrochemical bonds where that changes just a little bit. The amount of energy changes only slightly due to the differences in open circuit voltages in this cell. But if I try to extract this 1 unit of energy from a warm cell, I may be able to do so, and if I try to extract it from a cold cell, I may not be able to do so before encountering a lower voltage limit. And that's the key, encountering the lower voltage limit. This is because the cell resistance increases at cold temperatures, and when we're discharging, we encounter this voltage limit more quickly because of the ohmic voltage drop of this cell, which we'll learn in the second course of the specialization. We compute as current times resistance. If I have a cold cell, maybe I can extract only 0.5 units of energy from that cell. But then if I warm up that cold cell, it turns out I can extract the remaining 0.5 units of energy. So the energy was still there, it just wasn't available at that point in time because of the high resistance of this cell. So this equation on the slide shows you how to compute how much energy is physically present, but it does not tell you how to extract all of that energy. And that's why we need power estimates in addition to energy estimates, because the power estimate tells you how quickly we can extract energy at this point in time. Okay, so power limits state the maximum rate at which we're able to move energy into the battery cell or out of the battery cell without exceeding electronics design limits or some battery electrochemical design limits. If I attempt to discharge or charge a cell at too high a power level, I will accelerate the rate of degradation, and that will lead to a premature battery pack failure. So we've just reviewed energy, which is a total quantity that describes a total amount of work that can be done. Power instead is an instantaneous quantity that refers to the rate at which we can do work. Power is equal to voltage multiplied by current, and it's measured either in watts or in kilowatts. When we compute power limits, there's an immediate challenge. We understand that power is an instantaneous quantity. Power is what's happening right now, but the host application probably doesn't care what's happening right now. Instead, it wants to do some planning. It needs to know how much power will be available in the near future, not just what's happening right now. So when we compute the available power estimates, we're not computing how much power is being used at this moment, which we could do very simply as current times voltage, and we measure both of those. Instead, we're informing the host application how much power it may use at some constant level for some future time horizon, and we call this time horizon delta t. So at this point in time, we compute a value of how much power is available, and we pass that value to the host application, and we're saying to the host application, you may use a certain level of power for the next delta t seconds without causing any violation in electronics or chemical design limits. This time horizon delta t is often on the order of 10 or 20 seconds. The sample period of a battery management system is often once per second or even faster. And this power estimate is something that we update every sample. So I don't tell the host controller, you may use this much power for the next 10 seconds, and then wait 10 seconds before giving it another update on how much power is available. Instead, I say this is how much power is available for the next 10 seconds, and then maybe 1 second later I update that quantity with, oh, and by the way, now this is how much power is available for the next 10 seconds, and that will be a somewhat different number. And so we end up with what's called a moving window power limit estimate. I'm computing from now to a future 10-second value, and then 1 second later I compute from that point to a future 10-second value. And I keep on doing that, and this allows the host application to adjust a little bit more smoothly to changes in the available power as the host application draws power or instead sources power that will end up recharging the battery pack. There are some good methods and some poor methods for computing power. In this lesson, I will share with you one simple method to compute available power that's actually quite commonly used, but it does have some limitations, and so in the 5th course of the specialization, you will learn some better methods. The figure to the left illustrates this simple method, which is sufficient for you to understand right now. This method is known as the Hybrid Pulse Power Characterization, or HPPC method. It's based on performing a very simple test on a battery cell in the laboratory and measuring some quantities from that test that we later use to calculate power. The figure shows a profile of cell voltage versus time. The cell is initially allowed to rest until it has reached equilibrium, and in this slide that equilibrium voltage is shown to be 3.8 volts. The cell is then subjected to a discharge pulse that has exactly the same length as the time horizon delta t required for the power calculation. Then we allow the cell to rest again until it reaches equilibrium, or at least close to equilibrium, which I have abbreviated in this slide to also be only 10 seconds. The cell is then subjected to a charge pulse for the exact duration required when computing charge power. Finally, the cell is permitted to rest. Because we have designed this test and because we have implemented this test, we know the exact charging current and discharging currents used to create these pulses. And we also measure from the voltage profile, we can measure the maximum amount of voltage change due to the discharge pulse and the maximum amount of voltage change due to the charge pulse. The maximum voltage change to a discharge pulse is measured from the beginning of the discharge pulse just before the discharge pulse is applied when the cell is still in equilibrium to the end of the discharge pulse when the voltage is at its minimum. That is our delta V discharge. We do the same thing for the charge pulse. We measure the change in voltage due to the charge pulse from the equilibrium point just before we apply the pulse of current to the maximum voltage at the very end of the pulse of current, and that is our delta V charge. From these voltage changes, we can compute a charging effective resistance and a discharging effective resistance over the time horizons delta T that are required by the power calculations. The effective charging resistance is the absolute change in charging voltage divided by the charging current, and the effective discharge resistance is equal to the absolute change in the discharging voltage divided by the discharging current. These resistances are tabulated as functions of initial state of charge and temperature. Notice that if you are familiar with battery models already, please notice that the resistance we're calculating here is not the instantaneous or ohmic resistance of this cell. Instead, it's an effective resistance over the entire interval of delta T seconds, and it includes both the ohmic effects and also the diffusion effects as the voltage changes due to the slow time constants of the electrochemical processes in the cell. Once we have performed the laboratory tests and have calculated resistances at different states of charge set points and different temperatures and have stored these values in a table, we can use them in real time to compute available power estimates. In particular, we will use a mathematical model of how a battery cell works in order to predict how much power is available. We look in detail at creating circuit models of battery cells in the second course in the specialization, but here we need only a very simplified model, so I can introduce that quite quickly. The HPPC method assumes this circuit model that is drawn in the figure. In the model, the cell terminal voltage is described as an open circuit voltage at the present state of charge, along with a voltage drop across the effective resistance of the cell. In other words, the terminal voltage is equal to the open circuit voltage minus current times resistance. We can perform some simple algebra to find the electrical current in this equation, and this results in the relationship that current is equal to open circuit voltage minus terminal voltage, all divided by resistance. When we use the HPPC method to compute the amount of discharge power that's available, we assume that we're concerned only with keeping the cell terminal voltage between some Vmin and Vmax limits. And so for the maximum discharge power, this would be achieved if the terminal voltage were always equal to Vmin. So to compute discharge power, we replace R in the current equation with the discharge resistance we tabulated from our test, and we replace the terminal voltage with the value Vmin. Then discharge power is equal to voltage multiplied by current, which is equal to Vmin multiplying the quantity of open circuit voltage minus Vmin, all divided by the effective resistance of this cell. To compute the amount of charge power available, we repeat the entire procedure, but we use a different assumed terminal voltage and resistance. That is, we use the same simplified cell model, where current equals open circuit voltage minus terminal voltage, all divided by resistance. But to compute the charge power, we replace the resistance with the tabulated charge resistance, and we set the terminal voltage equal to the maximum permitted voltage. We compute charge power then as voltage multiplied by current, or as the maximum voltage multiplying the quantity of open circuit voltage minus the maximum voltage, all divided by the effective charge resistance. Notice that this quantity is negative. That is, open circuit voltage must always be less than the maximum voltage. So if we are required to report charge power as a positive number, we simply take the absolute value of this equation by multiplying this result by -1. Also note that this method, the HPPC method in general, uses a very simplified cell model that does not include all of the effects occurring inside of this cell. And furthermore, that when we computed the effective resistance from our cell test, we assumed that the cell was initially at rest before we begin the experiment. So these equations are not perfectly accurate in a dynamics scenario for the real battery cell, and it's a common practice to derate the estimates produced by these equations by multiplying the computed power value by some factor slightly less than 1. For example, if we compute an available discharge power of 1 kilowatt, we might multiply that by some factor like 0.9 and report that 900 watts is available instead. This gives us some safety margin, but it actually artificially limits the performance of the battery pack because we have used a poor estimation method. If we were to use a better estimation method, we might be able to actually extract the full performance of the battery pack, and that's one reason to spend more time thinking about this in the 5th course of the specialization. So to summarize this lesson, you've learned how to compute cell total energy and cell available power. Cell total energy is easily computed if we already know the cell state of charge, the total capacity, and the open circuit voltage relationship of this cell. Cell available power is estimated over a moving time horizon at this future window that allows the host application to know how much power is available in this near future time frame so that it can do some planning of how to use that power and then use the battery cell without causing damage to the cell or to the electronics connected to this cell. You've also learned about the HPPC method, which is a simple way to characterize this cell and to estimate power. But you've also learned that the HPPC method has some limitations, as we will examine in much more detail in the 5th course of this specialization. So the HPPC computations, if you choose to use them, should be derated in practice in order to ensure safe and robust operation of a battery pack. This concludes this lesson on computing energy and power for a single cell. In the next lesson, you will learn how to compute the energy and power for a multi-cell battery pack instead. In the previous lesson, you learned how to compute individual cell available energy and available power. The available energy computation was quite straightforward, but the available power calculation required a little bit more development. In this lesson, you're going to learn instead how to compute battery pack available power and available energy instead. That is, you will learn how to compute these quantities for a battery pack that comprises many cells wired together. You're going to see that computing available power for the battery pack is quite straightforward after you've learned how to compute the power for a single cell. Computing available energy involves a bit more of a thought process, but in the end it's still not very difficult. So let's begin. Let's begin by looking at how to compute battery pack available power. Remember from last lesson that the HPPC method to compute cell discharge power evaluated the expression that the discharge power is equal to the minimum permitted cell voltage multiplying the present open circuit voltage minus the minimum voltage, all divided by the effective discharge resistance. In this equation, I have slightly updated notation from what you saw in the last lesson by adding the subscript J so that we can remember that this is now a multi-cell battery pack, and this power is being computed at the cell level for the time being for a certain cell indexed by J in this battery pack. So I've had to update the voltage and the current symbols by now denoting them as V sub J and I sub J, and also the state of charge by denoting it as Z sub J. When computing power in a series-connected multi-cell battery pack, we still consider the limiting condition to be when any cell voltage encounters either the minimum cell voltage for discharge and the maximum cell voltage for charge. So for discharge, the value Vmin in the power equation does not change, but the allowed current can change because individual cells might have different limiting currents. And in a series-connected battery pack, the same current flows through every cell, and so we cannot permit more discharge current to flow through the battery pack than can be permitted by the weakest cell, if you will, the one that can permit the minimum amount of discharge current. So when computing pack power, we sum the individual cell powers. So we add up the power that is delivered as voltage times current for each cell when we recognize that the current is going to be the same for every cell, but must be the minimum for all of the currents that are permitted by the HPPC method for individual cells that we talked about last time. And so you can see in this equation here, the discharge power is the sum over all of the cells in series of the voltage of that cell, which we're setting to be Vmin, and the current for that cell, which we're setting to be the minimum over all of the currents allowed for all of the cells of OCV minus Vmin divided by the discharge resistance of that cell. Using the same reasoning for computing charge power for the battery pack, we compute the charge power as the sum over all cells of the maximum permitted voltage multiplying the current for that cell. And since charge power is negative and charge current is negative, instead of taking the minimum to get the minimum absolute value, we actually have to take the maximum. The maximum of two negative numbers has the minimum negative value, which is why you see the max in this equation on the slide. And that's all there is for computing battery pack power using the HPPC method. Now we move on to look at how do we compute battery pack total energy. Remember that cell total energy is computed as the full charge capacity of the cell multiplying the open circuit voltage relationship integrated between the minimum permitted state of charge and the present operating state of charge. Often we said this could be approximated simply as the capacity multiplying the nominal voltage multiplying change in state of charge. When computing total energy for a multi-cell battery pack, we have to remember that every cell could have a different total charge capacity and could have a different present state of charge. So computing battery pack available energy is a three-step process. First, we have to determine how much charge could be removed from the battery pack before any cell encounters its minimum state of charge. Consider the drawing on the right. The left part of the drawing shows the present condition of the battery pack. One of the cells in this drawing is fully charged and the other cell is at a slightly lower state of charge. What we're doing with this first step is performing a thought experiment, not a physical experiment. And in our thought experiment, we ask how much charge could be removed from this series-connected battery pack before any of these cells is discharged to the level Z-min. And that's the state that's shown on the right side of the drawing. To compute the amount of charge we can remove, we begin with the generic state of charge equation that we saw in the previous lesson that says that state of charge now is equal to some initial state of charge minus the quantity of ampere hours discharged, and then divided by the total charge capacity. Next in our thought experiment, we substitute the present state of charge for the initial state of charge because that's where the battery pack on the left side of the drawing is beginning, and then we set the final state of charge to be the minimum state of charge. And then we set the capacity equal to the capacity of this cell under consideration. This is in order to figure out how many ampere hours of charge can I remove from each cell, starting at its present state of charge to see how many it takes to get down to the minimum state of charge. We rearrange the expression to find that the ampere hours discharged are equal to the capacity multiplying the present state of charge minus the minimum state of charge for any of the cells. So the maximum amount of charge that could be withdrawn from the battery pack before the weakest of the cells is discharged to Z-min is the minimum of all these, which is given by this equation here. The equation tells us the maximum number of ampere hours that we can discharge before any cell encounters the minimum SOC limit. So that's how much charge is possible to remove from the battery pack. But if we were to remove this many ampere hours from the battery pack, only one cell would end up at state of charge Z-min. All of the other cells would end up at slightly higher states of charge. So to compute the amount of energy removed from each individual battery cell, we have to use the energy relationship from its own starting state of charge to its own ending state of charge using this accumulated number of ampere hours removed. And the ending state of charge is equal to the beginning state of charge minus the quantity of charge removed divided by the total capacity of that cell. So we're going to call that the Z-low, the low state of charge after this thought experiment, after removing as much charge as we can from the battery pack, where Z-low is going to be Z-min for one cell, but it's going to be somewhat above Z-min for the other cells. So now we can compute the amount of energy removed for each cell and the amount of energy for the battery pack. The amount of energy removed from the battery pack is the sum of all the energies removed from the cells, and this equation shows the computation. You can see that the pack energy is the summation over all of the cells in the battery pack of the quantity where we multiply the capacity of that cell by the integrated open circuit voltage relationship, where we integrate between the present state of charge and the low state of charge for that cell. Now remember, it's not possible to extract all of this energy at high rates and cold temperatures because of the resistances of this cell, and that's why we needed the power estimates as well to tell us how quickly we can extract this energy. When we compute the energy estimate, there's an integral equation involved that might look somewhat frightening, but this integral relationship can be pre-computed offline and stored in a lookup table for essentially instant computation in a real-time environment. On this slide you can see a block of code that's written in the programming environment for MATLAB or for Octave. This particular code will work in either. And this code has two sections. One section performs this integral approximation and stores it in a lookup table, and the second part of the code looks up a value from that table whenever we require it. In this code block, everything that has a percent symbol at the beginning of a line that's shaded in green is a comment to describe what's happening. It's not a functional line of code. It's there instead for the human being reading the code to understand better what the code is intended to do. So if we look at this, we see that in reality there are actually only 2 lines of code in what I'm showing you, and the rest is a description of what those 2 lines are doing. In the code, we're first assuming that a variable called zref exists in our workspace, and that a vector of state of charge points at which we want to compute values for the lookup table, that's what it is. So as an example, this vector might contain points between some minimum state of charge and 100% state of charge in increments of 1% state of charge. The variable OCVVec is a vector of open circuit voltage values that have been computed somewhere else for the cell that we're considering and correspond 1-to-1 with the state of charge points in zref as the open circuit voltage values at those states of charge. And based on those values, we would like to integrate the open circuit voltage relationship versus state of charge for that particular range of state of charge points. The code that performs that operation uses a command called cumtrapz, which performs a trapezoidal integration cumulatively over the points in OCVVec as related to the points in zref. The figure shows the result of this computation for the 6 different cells you saw earlier, where their OCV relationships were plotted for you at that point. In this graph, the 2 lines at the bottom correspond to the 2 iron phosphate cells that had slightly lower open circuit voltage than the other 4 cells. The other 4 lines that are nearly on top of each other in this integrated relationship are for the other 4 cells of lithium manganese oxide and lithium cobalt oxide and nickel manganese cobalt oxide. The integrated OCV relationships are nearly but not quite linear. So we see that the approximation to the integral of nominal voltage multiplying a change in state of charge would not always be very inaccurate. Sometimes it's a pretty good approximation. But if you were to hold a straight edge up to this slide, you would notice that there is some curvature, especially in the top 4. And for the best accuracy, you would perform the computation that now you see how to do using the code on this slide. So this first line using cumtrapz forms the integrated relationship, and if we want to use this integrated relationship in a lookup table, we use the next line of code that you see on this slide. We want to perform a table lookup into the table that has one column is zref, those are the state of charge points at which the table exists, and the other is the integrated values that we called IVZref. In MATLAB and in Octave, table lookup is performed by the interp1 function, which performs simple linear interpolation. And this command produces integrated voltage as a function of state of charge, or what I'm calling in the code IVZ, using interpolation with this table defined by zref on the horizontal axis and IVZ ref on the vertical axis. Since zref does not go below zmin, we have to be careful not to try interpolating into this table using arguments that are less than zmin, which is why you can see in the input to the interp1 command I have max zmin comma z to make sure that the input argument is never actually below zmin. You could also do something similar to make sure that the input argument was never greater than 1 by using a min of z max comma z or a min 1 comma z in there to enforce that it was always less than 1. So overall, I hope that now that you have seen this code, you agree that computing this integrated open circuit voltage is not especially difficult, and that using it is also not especially difficult in an application. To summarize what you've learned in this lesson, you can now compute estimates of battery pack power over some future time horizon, and you can also compute estimates of battery pack energy by expanding on the methods that you learned last lesson for single cells. You've also seen the first example written in MATLAB code or octave code that is able to implement a lookup table, and while we applied it to the example of computing energy, the basic principle of computing and implementing a lookup table is quite general, and we will find it to be very useful throughout the specialization. This lesson has brought you to the end of our discussion of requirement 3 placed on battery management systems of performance management. We'll spend much more time examining other methods to estimate state of charge and available power in the battery pack in courses 3 through 5 of the specialization. And the methods that you learn turn out to be better than what you've learned so far. But the methods that you have learned so far give you a good basis for understanding the general ideas involved and are sometimes used in practice even now. So the remainder of this week will be devoted to considering the battery management system requirement, which has to do with diagnostics. So far in this course, you've learned about battery management system requirements 1 through 4. In this lesson, you will learn about the final requirement, number 5, which has to do with diagnostics. Diagnostics involve abuse detection, state of health estimation, and state of life estimation. In many and maybe even most applications, the battery management system is not in control of its own destiny. That is, the battery management system provides advice or guidance to the host application regarding what are the maximum power limits of the battery pack and how much energy is available and so forth. But the host application might choose to ignore those limits or might fail in some way that causes those limits to be violated. The battery management system must detect and log external abuse conditions. These might include a violation of voltage limits or a violation of current limits or a violation of power limits or of temperature limits. Any of these abuse conditions could result in severe damage to the battery cells and to safety concerns. The photograph on this page shows a mobile phone battery that has been overcharged. In this case, that has caused the electrolyte to break down and to form gases, which then cause the cell to expand in volume. These gases sometimes include hydrogen gas, which is flammable, and so if this cell is punctured, it could cause a fire hazard. All of the abuse conditions that are detected, whatever they happen to be, must be logged, as we talked about under Requirement 3, for warranty and for post-mortem diagnostics. In addition to external abuse, the battery management system must be able to detect and to log failures of its own algorithms and components. These include detecting failures in the sensors that measure voltage and current and temperature. It includes being able to detect a failure in the balancing or the equalization system of the battery pack. It must be able to detect failures in the contactors or of the thermal management system. It must also be able to detect loss of communications with the host controller or frequent and repeated garbled or missed messages with the host controller. The photograph on this page simply shows some failed components on the circuit board of a random electronic device that were caused by bad capacitor design. These capacitors have become swollen and the electrolyte has leaked out of the cases, causing the capacitors to fail. The failure of an electronic component like this could cause any one of the internal failures I mentioned on this slide, and it's important to be able to detect these failures so that they can be communicated to the external host and to diagnostics so the battery pack can be repaired and used safely. Finally, the battery management system must be able to compute and report an estimate of the state of health of the cells of the battery pack. Earlier we saw that state of charge of a battery cell is tied very directly to physical quantities inside this cell, particularly to the average concentration of lithium in an electrode. State of health is not defined quite so precisely. State of health is generally trying to quantify how much a cell has aged to this point in its life. And so we could say that a state of health indicates a brand new healthy cell, and a state of health of 0% indicates a cell that has reached its end of life. There are two measurable indicators that are frequently used when people talk about state of health. And over cell lifetime, one of these is capacity, which starts out at 100% and decreases by about 20 or sometimes 30% before we consider that cell to have reached its end of life. Now, the still cell has 70% of its capacity remaining, so the cell might be still very useful in a secondary application, but it's not considered to be useful any longer in its primary application. Similarly, the resistance of a battery cell starts at some value and might increase 50% to 100% over the lifetime of the battery cell. We refer to the first measure of aging as capacity fade because we're losing capacity over time. We refer to the second method of aging as power fade because when resistance increases, the ability to extract power from the cell decreases. So when we learn how to estimate cell resistance as it changes over time, and how we estimate the total capacity of a cell as it changes over time, we will then be able to provide a state of health measure to the host application, and that's the topic of study in the fourth course of this specialization. It's also possible to define a state of life indicator which tries to predict how much life remains as a percentage or as an absolute value in terms of calendar time. Notice the fundamental difference, though, between state of health and state of life. State of health is an estimate, whereas state of life is a prediction. State of health uses all past and present data to estimate a current condition of the cell. State of life attempts to predict instead what will happen in the future with that cell, and we don't have the luxury of knowing how that cell will be used in the future. So the issue is that the future rate of cell abuse and cell aging may differ from how the cell has been used in the past, so state of life predictions tend to be quite inaccurate at best. So at this point, you've been introduced to the 5 basic battery management system requirements. And the one that you learned about in this lesson has to do with diagnostics. You've seen that a battery management system must be able to detect and to log external failures that impact the battery. The BMS must also be able to detect and to log internal failures that impact the battery. Also, the BMS must be able to monitor normal degradation as reflected by a state of health metric. And in some applications, we may also wish to predict a state of life metric. This brings us to the end of our discussion of BMS requirements. The next lesson will summarize very quickly what you've learned in this week, and will set the stage for what comes after that. This past week, you've learned quite a lot about the requirements imposed on battery management systems. You've learned about the protection requirements of the battery pack. You've learned about the interface requirements of the battery pack. And you've learned about the performance management requirements of the battery pack. There was a special emphasis placed on understanding the physical meaning of state of charge and connecting an intuitive understanding of what state of charge is to something that's physically happening in the battery cell, and to giving an intuitive idea of what state of health is and how it relates to the two quantities of resistance and capacity that we can estimate with some reliability. There was also a focus on understanding in a physical way how much energy and power is available in a battery pack. And as we continue through the specialization, we're going to spend much of our time going into greater detail of how to estimate state of health, how to estimate state of charge, how to estimate state of power. And by the way, I don't think I've mentioned it, but sometimes people talk about state of function, or SOF, and they usually mean state of power when they do that. Finally, we looked at requirement 5, which has to do with diagnostics in a battery pack. This brings us to the end of the standard version of Course 1 in the specialization on algorithms in battery management systems. At this point, you get to make a decision. As the diagram shows, you are at a fork in the road. You might decide simply to continue with the non-honors version of the specialization. However, if you're interested in the honors version of the Certificate in Battery Management System Algorithms, there's one additional week of lessons in this course. The honors track has a week 5 that discusses how lithium-ion cells are manufactured and talks in a little bit more detail than we've seen so far on how they age and how they fail. Whether you decide to take the honors track or not, you may proceed to the remaining courses in the specialization which focus on how to estimate the battery internal state and how to control battery operation. If you decide to follow the honors track, then there's one more week, as I mentioned, and I do encourage you to at least take a look at that week. I think you'll learn some things that are quite valuable and quite interesting. After that, you move into Course 2 of the specialization, and all future discussion moves towards learning how to design and implement battery management system monitoring and control algorithms. To be able to do this, we need a way to describe in a mathematical, precise, defined way how a battery cell operates and how it behaves. So the second course in the specialization introduces some helpful battery models. It also addresses how to find the parameter values for these models. You will learn methods, and you will use example code to be able to simulate battery cells and battery packs in either MATLAB or in Octave. And you will also learn how to simulate a battery load. One final note before we continue. It's important, I think, for you to understand that many or even most of the methods that I teach in this specialization have been patented and are owned by battery application companies such as vehicle companies. That could be disappointing to you because I'm sure that you're really very eager to be able to implement these methods for yourself. But it's also important to understand that if you read about any other method found in the literature, that method probably is going to be patented as well. All of these methods that you read about in journal articles and other places have been developed by companies, usually for their own use, and they're also patented. So this bit of insight strongly motivates research to develop methods that are sufficiently different from those that have been patented, so either they may be implemented freely and distributed to the public domain, or I suppose so that you could patent them if you choose to do so. But it also means that you may not use these methods commercially without license from the patent owner. And this is nothing new. It's simply a matter of common engineering practice that when you use a method, you are required to perform due diligence and to search the patent literature to make sure that you are not infringing on the intellectual property of someone else. There's nothing really different about battery management systems in that regard, but I'm bringing it up so that it's in your attention for you to be able to do so. So congratulations for making it to the end of the first course in this specialization. I hope that you have learned interesting and valuable things, and I sure hope to see you again in the second course. Welcome to the honors section of this course. I'm so pleased that you decided to investigate this as well. In this lesson, you're going to learn more about how battery cells are fabricated, especially lithium-ion battery cells. And I believe this will help you to understand how the cells actually work. Some of what you see in this lesson will be a review from what we've talked about already earlier in the course, but quite a bit will be new, and as we proceed through this week, there will be a lot of new material. Remember that lithium-ion battery cells are made in a number of different form factors. Cylindrical cells look like cylinders, and you can see some examples in the picture on this slide, and they're formed by wrapping an electrode structure in a spiral called a jelly roll. The second photo shows some prismatic cells, which are packaged in a rectangular container, and these are formed by wrapping electrodes again in a jelly roll, but in a flatter, longer jelly roll instead. And finally, pouch cells are also flat, but instead of having an internal wrapped or spiral structure, instead they comprise electrode plates stacked on top of each other. Even though cells can be packaged in different external form factors, the electrodes used inside of these cells are of a very similar form and are made by very similar processes on similar or even identical equipment. When creating an electrode structure, we start with the current collector materials, which are metal foils, and we coat both sides of these metal foils with layers of the electrode materials. The top diagram shows a positive electrode current collector in gray to remind you that it's usually made from aluminum, and underneath that you see a negative electrode current collector in orange to remind you that it's usually made from copper. Notice that both sides of the current collector are coated with active materials, and you will see that when a cell is formed, either by spiral winding or by stacking plates, the electrode materials are on both sides of the current collectors, and both sides are utilized. And by coating both sides instead of just one side, we get a reduction in the total volume required for the same total capacity of battery cell by not wasting one side of the current collector. The colors I use to represent the active materials are purely for illustration purposes. I consistently use the color purple when talking about positive electrodes and green when talking about negative electrodes, but that's for illustrative purposes in the specialization, whereas in the real battery cell these materials look pretty much like a black powder, and it would be very difficult to distinguish between them with just your naked eye. As a reminder, the negative electrode active material is usually some form of graphite, and the image on this slide shows you a scanning electron microscope or SEM image of graphite used in a lithium-ion battery cell. As you've already learned, the electrode is not composed of a single solid piece of the active material, but instead of tiny particles, because that increases the overall surface area of the electrode and it allows higher power. In general, some kind of lithium metal oxide is used as the active material in the positive electrode, and in the second photograph I show you an SEM image of lithium manganese oxide or LMO material, which is one of the candidate materials to be used in a positive electrode. Again, to the naked eye, both of these materials would simply look like a black powder, but under the microscope we can see that there are distinctive shapes and patterns, and so it is actually possible often to distinguish optically what the material is, at least if you've got a small list to choose from. But it's also important when we manufacture the cell not to mix these materials together or to mix them up, because contamination between the materials will ruin the cell. And so for that reason, the negative and the positive electrodes themselves are usually fabricated in different rooms when the cell is being constructed, so there's no airborne contamination. You've also learned that the particle size and the shape are important when fabricating an electrode. We desire that the particles be small in order to maximize the surface area so we can have a high current cell, a high power cell. On the other hand, we also desire smooth spherical shapes if possible, since sharp edges are susceptible to higher electrical stresses and cause faster decomposition of the solid electrolyte interface layer, which we'll talk about later on again this week. So sharp edges and pointy edges can lead to premature aging and failure in the cell, and even possible thermal runaway after extended periods of degradation. When we're fabricating this cell, we begin with the electrodes, and when we fabricate the electrodes, we begin with just foils of current collector material that are usually delivered in large spiral reels up to perhaps a half a meter in width. The negative electrode current collector again is usually made from copper, and the positive current collector is usually made from aluminum. The reels of current collector foil are mounted directly on a machine that unwinds the foil and coats the reels of foil with the electrode active materials. You can see on this diagram to the left how the reel is initially mounted and how the reel is unwound by the unwinding machine. And then you can see that there's a coater that coats the electrode materials onto both sides of this foil, and then the foil passes through other stages that we'll look at. Let's think about the coating process in a little more detail. When we coat the current collector foil, we don't simply put on the active materials, but we include with those some conductive agents like carbon black perhaps, and some binding agents like PVDF, for example. And all of these are mixed together, and then added to that mixture is a solvent that makes this mixture into a slurry or a paste that can be spread on top of the foils. Now, this solvent that we're adding at this point is simply for the manufacture of the electrode, and it has nothing to do with the operation of the battery cell later on in life. So once the slurry is prepared, it is spread on both sides of the foil, and there's a blade, a knife edge, that's located just above the foil that scrapes off the excess materials in order to control the thickness of the electrode coating. And the thickness is designed quite carefully so that the energy storage capabilities of the negative and positive electrodes match each other, so that we will not be wasting material or volume or weight by having an excess of one material versus another. After the foil has been coated, the coated foil moves into a drying oven. And this oven bakes the electrode material onto the foil, and it also evaporates the solvent that was added in the previous step to form the slurry. And at the end of this step, the electrode materials have a good mechanical connection to the foil. When the foil is completely dry, it exits the oven, and it's wound onto a reel on the right-hand side of the drawing. And we are finished with this particular piece of equipment, and we move on to the next step. The next step in processing the electrode is to perform an operation known as calendaring. This means pressing, to compress something. So the reel of coated foil from the previous machine is removed from that machine, and it's placed on the left-hand side of the machine that's shown in the illustration on this slide. And the electrode-coated foils are once again passed through an unwinding device, and then they're passed through large rollers that press the electrodes down to a highly calibrated thickness. And so this process is known as pressing or calendaring the electrode. The purpose of performing this calendaring is to compress the electrodes, to compact out extra spaces or voids between the particles, and pressing the porosity down to a calibrated level to ensure a more consistent density of particles throughout the entire electrode. It also helps to ensure electronic contact between the particles that might otherwise be relatively disconnected at the end of the previous processing step. The electrode material then passes through a machine that slits the electrodes lengthwise, and these narrower electrode strips are wound onto individual coils at the output of this machine, having the final desired widths. All of the processes in cell manufacturing are carefully regulated and inspected at every step. In this case, we might inspect the thickness after pressing operations to make sure that the thickness is within tolerance. The slitting operation must also be done with very sharp knives and must be carefully monitored, because any ragged edge, any sharp burrs on the edges of the foil strips could eventually work their way through separator material and cause short circuits inside of a cell. So that's a really dangerous situation that must be avoided. And so also this calendaring and slitting machine must be very precisely manufactured and maintained. At this point in discussing how the lithium-ion battery cell is fabricated, you have learned how the electrodes themselves are fabricated. You've learned that the metal current collector foils are first unrolled. A slurry of the electrode solid materials plus additives is deposited onto the foils. Dryers evaporate the solvents and adhere the electrode active materials onto the current collectors. A calendaring process produces the desired porosity and ensures contact of the active materials with each other. And finally, the electrodes are split to their final widths, and the narrower electrode foils are re-reeled in preparation for the next steps of cell manufacture. So at this point, you understand how the electrodes are prepared when fabricating a lithium-ion battery cell. The next step is to understand how we take those electrodes and package them in their final packaging, and that's what we look at next. In the previous lesson, you learned how electrodes for lithium-ion battery cells are fabricated, and in this lesson we continue to discuss how the remaining parts of the fabrication process proceed. This process might be performed on a machine like the one shown in this illustration here. The cell assembly process involves steps such as building the electrode sub-assemblies and putting these sub-assemblies into packages and filling the cells with electrolyte and performing some final operations of making sure that the package is sealed and perhaps welding the container and inspection of the cells. Some of the details of how this is done vary depending on whether we are talking about building a prismatic or a cylindrical or a pouch cell, but many of the details are fairly similar, and this illustration shows the process as it would apply to a cylindrical cell or even to a prismatic cell. In this drawing, you can see that the foils are already coated with the calendared electrode materials produced from the previous steps, and these foils are mounted on the left side of the machine. The foils are then unwound from the large roll, and they're passed into a machine that winds these foils into either the cylindrical shaped jelly roll or the prismatic shaped flattened jelly roll shape. The strips are then cut to the desired length to separate the jelly roll from the electrode foils that come into the machine, and the jelly rolls are placed inside empty metal cans, which are the containers for the cells, and then these metal cans are then welded closed except for a small opening. Electrolyte is added into this opening, and then the final sealing of the cell packaging is done by welding it closed. The cell is inspected, and the packaged cell is sent off to the next process in its assembly, which is a formation process, and we'll talk about that later on in this lesson. Several of the details in the process that were shown on the previous slide are different depending on whether a pouch cell or a cylindrical or a prismatic cell is being constructed. So here we think about pouch cells. Pouch cells are often used for high-capacity battery applications because there's very little wasted space inside the packaging of this cell. And furthermore, the cells are basically rectangular in shape themselves, and so there's very little wasted space when we put multiple cells together to form a battery pack as well. pouch designs start with electrodes fabricated in the way that you saw in the previous lesson, and then the electrode structures are stamped out of these reels of electrode material in the shape as shown on this slide, of basically a rectangular structure with a tab coming out of that structure that will be eventually connected to the cell terminals. So these individual electrode structures are stacked on top of each other as shown in this illustration. So, for example, we might start with a separator material and stack on top of that a positive electrode material, and then a separator, and then a negative electrode. And that whole subassembly would be repeated multiple times so that there would be many negative electrodes and many positive electrodes overall inside of one pouch container. The separator may be cut or stamped to essentially the same size as the electrodes, probably a little larger so that there would be some extra space around the edge to make sure that any shifting of the packaging did not result in a short circuit. Or alternately, the separator could be wound in kind of a zigzag shape between the different electrodes of different types that would give further assurance that there would be no possibility of short circuit if the electrodes actually shifted in the package. Notice in this diagram that the negative electrodes have their current collectors coming out of tabs on one side of the drawing, the top right in this case, and the positive electrodes all have their current collectors coming out of the same place, the bottom right of the drawing in this case. All of these individual negative electrode current collector tabs are welded together, and the positive electrode tabs are also welded together to make one large cell out of these individual small cells by putting them effectively in parallel electrically. And so we have one virtual large negative electrode and one virtual large positive electrode that are the sums of the areas of the negative and positive electrodes themselves. And then these two welded current collector tabs are themselves welded to some kind of a tab that extends outside of the cell packaging and forms the overall cell negative and positive terminals. Cylindrical and prismatic cells are formed in a different way. For cylindrical cells, the negative and positive electrode foils are cut into two quite long strips, and then one of the electrodes is placed on top of a separator, which is placed on the other electrode, which is placed on a separator, and this overall long subassembly is wound around a small diameter rod, a metal shaft. And the shaft is usually removed when the cell is packaged, leaving a really tiny cylindrical vacancy right in the center, actually. The electrodes ultimately end up with the structure that's shown on this diagram, where you can see that a spiral forms from concentric layers of negative and positive, negative, positive, all separated by the separator materials. The prismatic cells are constructed in a very similar way, but the winding is done around a flat, thin flat mandrel instead of around a cylindrical mandrel, which makes for an overall flatter package that's inserted into a prismatic can instead. To connect to the outside world, these current collectors that are cut long have little tabs at different locations that come outside from them as well. And so one or more tabs from the positive electrode are welded to the positive terminal of this cell, and one or more tabs from the negative electrode are welded to the negative terminal of this cell. If the purpose is to construct a high power cell, then there are often multiple tabs per electrode that are welded to external terminals in order to allow more current paths and therefore more uniform utilization of the electrodes. Whether we are constructing a pouch or a cylindrical or a prismatic cell, the next step involves filling the cell with electrolyte in any of those cases. We add our safety devices like internal fusing, for example, first. Then we insert the subassembly into the package, but at this point the cell is completely dry. The package is sealed except for a small opening, it's often sealed by laser welding. For a pouch cell, it could be sealed by heating some materials and effectively making a hot glue connection. But after this initial sealing process, we still leave a small opening through which we will insert the electrolyte. This is done in a very interesting way. The cell is first subjected to a vacuum through this small opening, which removes most of the air from the inside of the cell, from the pores in the porous electrode structure. And then a small amount of electrolyte is injected into the cell, and then the vacuum is released so that the atmospheric pressure forces the electrolyte into this cell and into those small pores and small pore openings. This can be done multiple times so that the electrode porous structure is filled as full as possible with this electrolyte. It's interesting that even at this point, the cell may not be completely wet with the electrolyte material, and it may take several charge-discharge cycles for that to happen. And so it's not uncommon to see the first several cycles of a brand new lithium-ion cell appear to increase in capacity as this electrolyte makes its way into all of the pores and then allows the lithium ions to flow to all of the solid active material. And then after these initial cycles where the capacity appears to be going up, then it starts to go down as this cell ages. In any case, after we have filled the cell with as much electrolyte as we're able to, we seal the remaining opening using, for example, a laser weld or some kind of a heating process. The electrolyte fill operation must be done in an environment known as a dry room. A dry room uses a very high capacity dehumidifier to remove as much moisture from the atmosphere as possible. And this is really important because the electrolytes used in lithium-ion battery cells often have salts that react chemically with water. So any moisture in the electrolyte will cause the electrolyte to decompose, and this can cause them to emit toxic gases. And furthermore, lithium hexafluorophosphate, or LiPF6, which is one of the most commonly used electrolyte salts, reacts with water and forms toxic hydrofluoric or HF acid when it does so. And this HF acid can cause the electrode materials to dissolve or disintegrate inside the cell over time, which leads to capacity loss. So we highly desire to avoid that, or at least to minimize that, and we do so by injecting the electrolyte into the cell inside of a dry room environment. So at this point, the cell is completely constructed, and some remaining tasks might include things like printing a cell serial number on the cell and maybe some other identifying information on the packaging. But now this cell is ready for its very first charge. Before we discuss this charging process, it's important to talk a little bit about something that's known as the solid electrolyte interface layer in a lithium-ion battery cell, otherwise known as SEI. It turns out that when lithium intercalates into graphite in the negative electrode, the lithiated graphite reacts with solvents in the electrolyte and forms this SEI layer, the solid electrolyte interface layer, which is a film coating the particles of the negative electrode. This process of SEI formation and growth consumes lithium, so it results in capacity that's lost. The film also impedes ions, lithium ions, that want to travel from the electrolyte into the electrode and vice versa, which results in a higher resistance for this cell and therefore results in a power loss. And neither of these is desirable. But on the other hand, this SEI layer also turns out to stabilize the graphite against further reaction with the solvent, which is a positive feature. So it tends to be a self-limiting reaction. When the lithium-ion battery cells are assembled, they are done so in a fully discharged state at 0 volts. All of the lithium begins in the positive electrode. The negative electrode is pure graphite with no lithium in it whatsoever. So at the beginning point of the manufacturing process, no SEI has formed. But when we build this battery cell, we must put it through at least one precisely controlled charging process. And during this first charging process, the graphite is lithiated for the first time, and this causes this chemical reaction that forms the SEI layer. And because of this formation of an SEI layer, the first charging process is called the formation process. We would like this SEI layer to be as thin as possible because we don't want to have excessive capacity loss. We want it to be as uniform in thickness as possible so that it doesn't easily break down at a later point in time. And this is most easily achieved if we form this layer slowly. So we form the layer by charging the cell very slowly for its very first time. And then after that, it may turn out to be valuable to gently charge and discharge, otherwise known as cycle, the battery cell a few times to stabilize the SEI layer before this cell is delivered to the consumer. If the formation process is badly done, then this SEI layer will be thick and non-uniform, and it may be brittle, and it may easily break down as the battery cell is being operated in the consumer application. Anytime the SEI layer breaks down, it exposes more graphite to the solvent, and at that point the solvent will react to the graphite and form additional SEI products, which will reduce capacity and increase resistance. So while the SEI layer is formed for the first time when we charge the battery cell for the first time, it actually does tend to grow somewhat over time due to failure of the existing SEI layer and building of additional SEI layer. So good battery cells are formed, have a formation cycle that produces a good SEI layer. And the difference between a good battery cell and a bad battery cell might be your manufacturing edge when you're trying to market your cells to the consumer. And because of that, the formation processes used by different manufacturers are proprietary. They're trade secrets. Most likely the manufacturer does not do a normal constant current, constant voltage charge, and the process used may take several days or even several weeks and may include steps that hold the cell voltage constant for periods of time at different voltage levels. They may rest the cell at different open circuit conditions for different periods of time at different temperatures and so forth. And for this reason and for other possible variations in the processing steps we've seen throughout this week already, cells from different manufacturers can have very different operating characteristics and especially life characteristics, even though they share supposedly the same chemistry. The way the cell is manufactured has a critical influence on how long that cell will last in the application. And so having tight controls on the manufacturing steps is very important to be able to create the best cell possible. During this formation process, cell performance data are gathered and recorded in order to be able to perform some quality analysis. If we notice during formation that a cell has a high self-discharge rate, that points to some manufacturing defect, and that cell will be recycled. It will not be sold to the consumer. If the cell has capacity that's very different from what's expected or has impedance that's higher than what's expected, that could indicate that there's a manufacturing process that's not under control, and that will lead to a lot of creative detective work to find and correct the process that is causing this problem. Many times, even when cells do have parameters that fall within the desired tolerance band, the cells that come out of production are sorted into different lots according to their capacity and resistance, so that different lots of cells can be matched to each other for certain applications that require all of its cells to have very close capacities or resistances and so forth. And this process is called matching, or sometimes binning, as you put cells in different bins so that the cells could be used together in this type of high specification environment. All of this testing, by the way, is done inside the manufacturing facility, including other quality control measures that I have not even mentioned in every step of manufacture. And we strongly desire that all of the manufacturing defects are identified either before or during formation and not after formation. Certainly not after the battery cells have been sold to the consumer and battery packs have been assembled and it's in some product. So in order to avoid a low yield, it's important to enforce tight tolerances and strict process controls. We need to avoid contamination of the raw materials. We need to avoid physical damage. We need to avoid things like burrs, the sharp edges on the electrodes, because all of these are extremely dangerous and can cause serious problems when the cell is in operation. In order to reduce contamination, cells are normally manufactured in a clean room condition similar to what's used when manufacturing semiconductor parts. So to summarize this lesson, you've learned that cell construction comprises building the electrode subassemblies first, then packaging them, then filling the package with electrolyte, and then sealing and welding and inspection. After construction, the cell undergoes a precisely controlled formation cycle to charge it and to grow a thin, uniform layer of SEI. A byproduct of this formation cycle is that we can measure a set of data that enable us to perform acceptance testing and even binning or sorting of cells for highly calibrated applications. And finally, the cells are put in boxes and they're shipped to the end purchaser of the cells. This is usually done at a low state of charge to a middle state of charge range, so that some of the degradation processes that we'll look at later this week will be minimized, and so that the energy stored in this cell is also at a fairly low level in case some safety event happens during shipping. So at this point, you've learned how lithium-ion battery cells are manufactured and how they are put into their packages and the formation cycle and so forth. What we're going to look at for the rest of the week is the other end of the life spectrum. Here we've seen the beginning of life, but what causes a cell to age and degrade and break down, and what are the consequences of these aging mechanisms? And so that's what we will look at next. This specialization does not study cell electrochemistry in detail, but understanding the causes and effects of cell aging, how they fail, and what that means to your application has real value when thinking about battery management system algorithms. For example, it motivates the need for state of health estimation algorithms and also for computing power limits in order to slow down degradation. There are many possible causes of failures in lithium-ion battery cells, and these include things like design faults and poorly controlled manufacturing processes, or some normal aging mechanisms, or some abnormal aging or degradation due to uncontrolled operations and abuse. Battery management systems can't do very much about the first two, about design faults or manufacturing faults. It's too late to worry about them because the battery management system is using cells that are already manufactured and already in this product. So they can protect against some safety events, but they can't really do anything proactive at this point. However, it is possible, in some cases, even compensate for other causes of failure of the battery cells. And so in this lesson, we're going to look at what are the normal lithium-ion aging processes, and in the next lesson we'll look at some abnormal causes due to abuse. Lithium-ion cell performance generally deteriorates gradually over time due to unwanted chemical reactions that happen inside this cell, and also due to physical changes to the active materials in this cell. We already know about the desired chemical reaction where lithium exits one electrode and enters into the electrolyte and then into the other electrode, and vice versa when charging and discharging the cell. However, there are other chemical reactions that happen inside the cell that we do not desire to happen. And you've seen one of them already, which we learned about in the last lesson, was the formation of an SEI layer due to a side reaction between the solvent in the electrolyte and the graphite particles in the negative electrode. The processes that result in aging are usually not reversible, and they eventually result in the cell reaching a point where it's no longer considered capable of performing its duty in an application. So we look at a few example causes. One general mechanism of aging is known as corrosion. Corrosion is really a generic term that talks about any undesired chemical reaction that takes place with the environment. Corrosion can refer to corrosion of the current collectors in the cells, for example, when the current collectors react with the electrolyte. It can also refer to corrosion of the electrode active materials when they react with the electrolyte. Corrosion in general will consume some of the active chemicals of this cell and lead to increased impedance and usually also to capacity loss. Now, corrosion in a lithium-ion battery cell is fairly difficult to visualize, so I include a photograph of something that we see more commonly in everyday life as an illustration. In this case, we can see that a metal chain is undergoing an undesired chemical reaction with its environment, which is forming this rust layer on top of the chain on the surface. This layer of rust can eventually cause the chain to fail. And similarly, corrosion in a lithium-ion battery cell can eventually cause the cell to fail. Another process of degradation is known as crystal formation. You have learned already that the electrode active materials are built from crystal structures in small particles. Crystal structures have a tendency to grow over time and to join together, forming larger crystals. Remember that we desire these small particles in the electrodes in order to achieve large effective surface area so that a cell can carry a high level of electrical current or of power. But when small particles merge together to form larger particles, the effective surface area of the electrode is reduced. And when we reduce this effective surface area, we reduce the amount of current that can flow in the cell. And in some cases, we can even isolate some parts of the electrode from the electrically conductive path, and so we lose some storage capacity. Now again, the photograph on this slide is not one of a lithium-ion battery cell, but it does show the formation of crystals, in this case of ice crystals. I've included this photograph because it's something that all of us can relate to a little bit more easily than crystal formation in a battery cell, because probably all of us have seen ice crystals form over time. And it's a very similar idea to what is happening inside the battery cell, except there we have crystals of positive electrode materials forming, for example, over time. Another process of aging has to do with something called dendrite growth. This is similar in a way to crystal formation, but in crystal formation we're usually thinking about the active materials themselves somehow merging together and forming larger crystals. When we're talking about dendrites, we're talking about growth of undesirable crystals that are not the active materials. So for example, it's possible if I try to charge a battery cell at too high a rate or too cold a temperature, for lithium metal to, instead of intercalating in the negative electrode, to actually smash onto the surface of the negative electrode and plate lithium metal onto the surface of the electrode particles. And once this metal annealing site is present on the surface of the particle, it's simpler for other metals to attach to it. And overall, the metals grow into these tree-like structures that look very similar to what's shown on this photograph. Now, once again, this photograph is of ice crystals because I don't have a handy photograph of lithium dendrites, but the lithium dendrites do tend to look similar to this, of lithium forming these really thin tree-like structures that can penetrate through the separator of the battery cell and make an electrical connection between positive and negative electrodes, causing a short circuit and causing cell failure. So this is a really possibly very dangerous degradation mechanism. Another process of aging is when we lose chemicals required for the battery cell to operate through evaporation. This is very common for cells made of different chemistries, for example, lead-acid battery cells, because the water in the solvent, or that is the solvent in the electrolyte, can decompose into hydrogen and oxygen gases when the cell is fully charged, and then these gases can escape through small openings or large openings in the packaging, and so the electrolyte can dry out. This results in increased resistance of the battery cell and ultimately in failure of this cell. Chemical loss through evaporation is perhaps less common with lithium-ion battery cells, but it can still happen. If, for example, the lithium-ion cell is overcharged or over-discharged, the electrolyte can break down and form gases, including hydrogen gas and methane gas and others. If the packaging of the cell is somehow compromised, these gases can then escape. And even if it's not compromised, these gases generally do not recombine to form the electrolyte and its solvents, and so the lithium-ion battery cell can dry out over time, and that results in increased resistance of this cell. Another process of aging is known as passivation, and you've learned about one type of passivation, which is the formation of an SEI film layer. This film layer is known as a passivation layer because when it forms on the surface of the negative electrode particle, it impedes the further formation of SEI layer, and so it passivates or isolates that layer from more chemical reactions. However, if the SEI layer is somehow dissolved or cracked, then SEI will form where fresh graphite has been exposed, and so the SEI, even though it is formed during the first charging cycle, it does tend to gradually grow over time. I really liked this photograph to illustrate film formation because it shows a film that has to do with aging. Another aging process that we might see has to do with the development of an internal short circuit inside of the cell. A lithium-ion cell that appeared acceptable when it was new, or might have been marginally acceptable when it was new, may have contained some latent, invisible defect that becomes apparent only as the aging process unfolds over time. There might have been a poor cell construction or contamination or some metal sharp edges called burrs on the current collectors, and over time, because of the stresses and strains of each charging and discharging cycle, these wear their way through the separator and lead to some contact between the electrodes through this separator, and that of course is a very dangerous situation with a short circuit that could result in a fire. A final process of aging that we think about has to do with electrode or electrolyte cracking. Some lithium-ion battery cells use a solid material for their electrolyte, which is some plastic-like lithium polymer material. And over time, this solid electrolyte can crack due to stresses and strains. And that can cause resistance of the cell to increase because it's not possible for that part of the separator to conduct ions any longer. It can even cause short circuits if the crack is large enough to allow the negative and positive electrodes to contact each other. The electrode structures themselves, as you know, are held together with binders and have conductive agents added to improve their electronic conductivity. And over time, the stresses and strains of charging and discharging can also lead to cracking of these binders and making the overall electrode structures brittle. And this brittleness of the electrode can cause some of the particles to become electrically disconnected, so that even though they're still perfectly capable of holding lithium, there's no way for the compensating electron to make it to the outside circuit, and so you lose that capacity and end up also increasing resistance of the cells. It's helpful to have some idea of the aging mechanisms and to understand why they age and why they degrade and why they don't last forever. But what is the net result of any one of these aging mechanisms? So one result is increased internal impedance. As larger crystals form, the effective surface area of the electrode is reduced. This increases impedance. When films form on the electrode particles, then it's harder for the ions to get into and out of the particles, and so the impedance increases. When electrolyte is lost, or when current collectors are corroded and so forth, it makes it harder for either electrons to move or for ions to move, and therefore there's increased impedance or increased resistance of your cell. A second undesirable effect is reduced capacity. When the active materials disintegrate or deteriorate, they lose vacancies that could have held lithium. Or we could lose charge carriers from the electrolyte when side reactions occur. In some battery chemistries, this is partially recoverable through reconditioning the cell using one or more deep discharges, but this is not the case in most lithium-ion chemistries. A third effect of aging in cells is manifested in an increased rate of self-discharge. As electrodes swell, that increases the pressure on the separator, and as a consequence decreases the resistance of the separator and can lead to increased self-discharge rates. Any one of the aging processes is usually accelerated by higher temperatures, and aging processes that result are not necessarily noticed right away. There's a rule of thumb that says batteries die in the summer, but you hold the funeral in the winter. The aging mechanism that caused the failure was probably accelerated by the hot temperatures in the summer, but the hot temperature also results in a lower cell resistance, as you'll learn about in the second course in this specialization. Cell resistances are usually lower at warm temperatures and higher at cold temperatures. So even though the effective resistance of the cell is increasing due to these aging properties, you don't notice it because you're operating in a region where the resistance is temporarily lower because of the temperature. It's only in winter, when the cold temperatures cause the overall resistance of the cell to rise, that you realize that the resistance this winter is a lot higher than the resistance was last winter, and that this cell has actually failed. So to summarize this lesson, you've learned that it can be valuable to understand the causes of aging, and it's important at least to motivate the need for state of health algorithms and for being able to compute power limits in such a way that avoids degradation as much as possible, and we will discuss that later in the specialization. You've learned that some of the causes of cell aging at the internal level have to do with corrosion and crystal formation and dendrite formation and growth and chemical loss and passivation and shorted cells and electrode and electrolyte cracking. You've also learned that some of the effects of aging are manifested as an increased resistance and a decreased capacity, which are known as power fade and capacity fade, and also at an accelerated rate of self-discharge of the cells. So that summarizes the normal causes of aging. Obviously, at a fairly shallow level, we'll talk a little bit more about them in the fourth course of this specialization. But now we're going to move on in the next lesson to talk about some abnormal causes of aging. In the previous lesson, you learned about some normal causes of battery aging and degradation, and now we're going to look at what happens to a battery cell when it is abused. Some bad things to do to a battery cell include overcharging it or undercharging it or subjecting it to temperatures that are too high. And when I'm talking about overcharge and undercharge and overtemperature, I can be referring to what's happening to the entire cell, but the real problem really is what's happening locally at some point internal to that cell. So it's possible actually to have local overcharge or undercharge or over temperature at some point in the cell when it may not be obvious that this is happening by simply looking at what's happening measured outside of this cell. And that's one reason why present-day battery management system algorithms are conservative in how a battery pack is operated, and how perhaps some physics-based methods in the future might be able to extend that operating range to give more performance. If we violate a temperature or a voltage specification, that can cause a number of things to happen. One of them might be electrolyte breakdown. One of them might be electrode plating, or we could have penetration of the separator where one electrode contacts the other, or we could have gases forming or swelling of the packaging and even venting of the packaging. We can even have overheating and thermal runaway. And you've seen some of these before in the previous lesson and when we talked about thermal management, but here we're talking about them in an extreme way due to some abuse. Most of these conditions, one way or another, end up with the cell overheating, and that's what ultimately causes it to fail. In addition to all of those things, mechanical or physical abuse is also a bad thing. Physical abuse of a battery cell might include dropping it or crushing it or penetrating the package or impacting it or immersing it in fluids or freezing it or placing it in contact with fire. Any of these things could appear in an automotive battery pack. So for example, if a vehicle is involved in an accident, the battery pack could be physically damaged in severe ways. And so the photograph on this slide I thought was really interesting. It's an early electric vehicle that has been obviously in a minor traffic accident. And unfortunately, the early electric vehicles did not catch on because the lead-acid battery cells of the time were not capable of supplying the kind of range needed and could not compete against gasoline vehicles. But today we're seeing a comeback that I'm very excited about. And so even though electric vehicles took a vacation for about 100 years, I think that we'll see more and more of them on the road. So when your battery pack encounters some kind of physical abuse, it's generally accepted that the battery pack is not required to survive these trials and still be perfectly operational. But the battery pack itself should not cause an increased hazard to the user, to the person who is perhaps driving the vehicle, if the battery pack is subjected to any of these physical abuses. When a battery ages normally, or when it's abused and ultimately fails, one of three different failure modes will become apparent, and it's generally not possible to predict in advance which one will occur. It depends very much on the circumstances of the failure. The first type of failure mode is that of open circuit. This is in some ways the safest of all of the different modes of failure, but it might not be the safest for the application. That is, it's the safest for the cell, but not for the application necessarily. So I've drawn a knife switch here in the open position, and you can imagine your battery cell coming to the same condition, that instead of supplying a voltage, supplying energy to the load, instead it opens up a circuit. It causes an infinite resistance between the two terminals of the cell and no voltage being generated by this cell. So once this current path is cut by the internal open circuit, the cell is isolated and the possibility of further damage to this cell is very limited. But if I have a whole lot of series connected battery cells in my battery pack and one of the cells fails in an open circuit condition, then the whole battery pack is open circuit even though all of the other cells may be perfectly healthy, and the battery pack is no longer able to provide power. The second failure mode is due to an internal short circuit, and there are two varieties of short circuit that are often talked about. One is what we call a hard short circuit, where a solid connection is formed between the positive and negative electrode of this cell, and this allows an extremely high level of current to flow the moment that the short circuit occurs, and it completely discharges the battery cell and results in permanent damage to this cell. The second type of short circuit is called a soft short. And this happens when there is localized contact between the electrodes somewhere internal to the battery cell, but not global contact, and really a fairly high resistance local contact even. In some cases, this is self-correcting because locally the battery cell heats up and it might melt the separator material and then eliminate the contact between the two electrodes as the separator fills that area. Other times the short circuit results in simply an elevated rate of self-discharge, but where the battery cell is still fairly functional. It still can be charged and it can still deliver energy to the load. It just has a self-discharge rate that's much higher perhaps than the other cells in a battery pack. In either case, in either the hard short or the soft short case, a battery pack, if it's kept cool enough when the short circuit event occurs, may not enter thermal runaway. The cell itself will eventually or quickly discharge down to 0 volts, but will still be able to conduct current. And if the battery cell can be drawn down to 0 volts safely, then a series-connected battery pack is still able to conduct current through it because the one cell is acting just like a resistor at that point. It can't really charge it, can't really discharge it. It increases the resistance of your battery pack. It slightly reduces the voltage of your battery pack because that cell does not produce voltage any longer, but you can still operate your device. So in that case, the soft short circuit can be more desirable than the open circuit in some applications. The picture on this slide shows some steps in a process where we can see aging of different causes happening, that maybe there's some SEI formation after the cell is formed, and maybe this SEI decomposes and has some products in it that lead to dissolution of the copper current collector, and then we're starting to cycle copper through the battery cell in addition to trying to cycle lithium through the battery cell, and this can cause metal dendrites to form that join the electrodes together, which can lead to a mild internal short with very thin dendrites that have a very high resistance. But if this keeps on happening, we form thicker and thicker short circuit wiring, if you will, with these dendrites penetrating the separator that can lead to moderate and severe short circuits as well. The third failure mode after open circuit and short circuit is most severe. It's a fire or an explosion. And you might know from your background in chemistry that the rate of most chemical reactions tends to double for every 10 degrees Celsius increase in temperature. So if the heat produced by a short circuit or some other failure cannot be removed as quickly as it's generated, then this can set up a self-sustaining and uncontrolled positive feedback loop known as thermal runaway. The generated heat causes the temperature to increase. The temperature increase causes the cause of temperature increase to be generated more quickly, so there's more heat generated more quickly. And so this spirals until there's a resulting fire and sometimes an explosion. Of course, we must avoid this if at all possible. So in this short lesson, you've learned that cells can fail due to improper controls. They can also fail due to physical abuse. The failures manifest themselves externally either as open circuit or short circuit and or a thermal runaway event. And we must take every precaution to avoid increased safety hazards by putting in protection mechanisms on our battery packs, by carefully building the battery pack enclosures to protect the enclosures themselves from penetration and crushing and so forth, and many other things. So there's a lot of engineering analysis and design that goes into the construction of a battery pack in order to protect the user as much as possible. But our focus is on algorithms for battery management and control, and I think it's about time that we started to move on and look at that in much more detail. So this brings us to the end of the content of this bonus honors week of the course. There's one more lesson that summarizes everything and then points you forward into the second course in the specialization, and that's what we'll do next, but get prepared. The next step after that is course number 2. I'm illustrating how we can charge an individual battery cell. When we're charging a battery pack that comprises multiple cells, there are some extra details that we'll need to be careful about, and we'll talk about those later on in this course when we look at requirements on a battery management system and how it manages the battery pack charger. Also, many of the details of why the battery cell responds exactly the way it responds in these pictures is something that's beyond the scope of what we can talk about at this point, but we will study those details in the second course of the specialization, and you will learn how to write Octave or MATLAB code to simulate and reproduce the results on the slide for yourself. And so to summarize this lecture topic, battery cells store energy as electrochemical potential energy. And whenever an external circuit is completed, this provides a pathway for that electrochemical potential energy to be converted into electrical energy. The negative electrode supplies electrons to the external circuit, and the positive electrode sinks electrons from the circuit, thus powering the load and discharging the battery cell. In a rechargeable or a secondary battery cell, whenever the charger provides electrical energy to the cell, that energy is stored as electrochemical potential energy again that can be used at a later date. When we charge a battery cell, we must be careful to maintain the cell within manufacturer-specified voltage limits to ensure safety and to ensure long life as long as possible. And there are 2 commonly used modalities for charging a battery cell, and these are known as constant current, constant voltage, and constant power, constant voltage. And you will encounter both of those in applications.